So, ladies and gentlemen, welcome at the Brno Observatory and Planetarium, and of course in city of Brno. I'm very glad to open this conference tribute to Kurt Gödel, Brno 2020. First of all, thank you very much, all of you, because conference needs the visitors. I have to say thank you very much to all speakers, because the conference needs the speakers. And of course, I have to say thank you very much to the donors or sponsors, because conference needs money. So thank you very much, Tescan Orsay Holding, company Tescan Orsay Holding, company UNIS, Japanese Chamber of Commerce and Industry, South Moravian Region, City of Brno, Masaryk University, and Kurt Gödel Society. I hope that you will enjoy this 3 days in our planetarium, and let's start. So first speaker, the Dean of Faculty of Informatics from Masaryk University, Professor Zlatuška.
Yeah. Thank you. Thank you for inviting me. I'm not sure how to. Does it work? Okay. Thanks for inviting me. It's a pleasure to be able to address you here at the beginning of the conference. When I was invited, I was a bit horrified that I saw half an hour slot for the welcome talk. So I thought I should say something about the relationship which I feel Kurt Gödel has to my discipline, that is informatics, instead of just saying some ceremonial social welcomes. Actually, the history of formal reasoning, even though within today's educational curricula in mathematics it doesn't seem so, was rather strange. Aristotle, more than 2,000 years ago, used deductive proofs as demonstration arguments in Euclidean geometry. Apart from that, he's known for logic system, but this was just a system of syllogisms, and these were not used in connection with any mathematical reasoning. So what we now refer to logic in Aristotelian sense did not have anything to do with mathematical reasoning. And all of this was essentially sufficient for mathematicians for over 2 millennia. And it brought even such a progress in using mathematics like Galileo's revolution, or the development of differential calculus by Newton or Leibniz. When the situation started to change, that was associated with the coming of the so-called logicism. Sometimes you would see Leibniz mentioned in this context, but I think that this can be traced down mostly to Kant, who basically studied the reasoning in arithmetics and geometry within his system of a priori and a posteriori knowledge and synthetic and analytic knowledge. He basically put the mathematical reasoning on the same level of metaphysics, even though mathematicians would usually look very strange on metaphysics and vice versa. Dedekind was another person who somehow culminated or was associated with culmination of the attempts of arithmetization of both arithmetic and geometry. It's really transforming it into a system which is based on numerical quantities. But still, there was just arithmetization of mathematics, not really of systems of logical deduction. Gottlob Frege, German logician who came with the development of many key concepts which we use up to today. And basically, he thought about the analytical part of arithmetic truths. He encoded explicitly the mathematical quantities so that certain relationships suddenly started to be derivable from the properties of those. And given sort of repeated example, 7 plus 5 equals 12, there was equation which Kant would consider as synthetic, because he would have no way how to somehow go inside the quantities 7 and 5 and derive the quantity 12 from that. While Frege, with notation of successor, was able to define these relationships. Suddenly, that class of truths became analytical, contrary to Kant, and he was able to develop further steps in sense, reference, and semantics as we use today, and to use symbolic language for expressing each of those properties explicitly so that could be handled down. Brno was another important figure. He's known for piano arithmetics, but what he did actually as well was formalization of logical inference. He divided the objects, mathematical objects he used to work with, to axioms and derivations of other formula using modus ponens, using implication, and when you have A implies B and you have A, then you derive B as a derivation from that. That happened sometime around 1890. Bertrand Russell, when started to develop Principia Mathematica with Whitehead, this was published 1910 to 13, basically based his work on that piano system, deriving the truth, and on Frege's system of encoding of objects. Then came David Hilbert, well-known mathematician of the turn of the century and beginning of 20th century. And he came in his work, Grundlagen der Geometrie, with 4 foundational problems. There should be 4, not FOR, but FOUR. Formalization of mathematical theory as a formal expression, formal system with that derivation using modus ponens and axioms. Then the task of providing proof of consistency of the axioms. Another task was proving independence and completeness of the axioms. And the fourth was so-called decision problem. That is a question whether there is a method answering any question in such a theory. David Hilbert was extremely influential, so his way of expressing mathematics and formalizing mathematics became de facto standard. This is something which was called Hilbert-style axiomatic approach, and it dominated around the 20s of last century. One successful result of this was proving completeness of propositional logic, and also decidability of propositional logic. That is a unique result to every question posed within propositional logic and the way of evaluating that. Predicate logic was formalized by in Hilbert style by Ackermann around the same time, but there was still some work needed. Around 1920, David Hilbert formalized the so-called Hilbert program, that was the task of expressing higher mathematics in terms of elementary arithmetics, and formalizing all mathematics in axiomatic form together with a proof of completeness. The co-workers of Hilbert were Bernays, Ackermann, von Neumann, and Herbrand, well-known figures from foundational mathematical logic from this history. Ackermann and von Neumann worked on proof of consistency of number theory, and Ackermann thought he was near completion of this proof, also for analysis. David Hilbert announced during a big mathematical congress in Bologna in 1928 that it's a matter of just final few touches to complete the proofs, but essentially everything is completed. This is the situation when Kurt Gödel started to work on his doctoral thesis, and his task at that time in Vienna was completing proving completeness of first-order predicate logic. As a result, sort of pushing the knowledge one step above the propositional. The Kurt Gödel tackled this based on the formulation by Hilbert and Ackermann, provided in 1928. And he proved within his doctoral thesis theorem that every logical expression is either satisfiable or refutable, which is the same as saying that every valid logical expression is provable. This result from his thesis he presented in September 1930 at a small gathering in Königsberg. As an aside to this presentation of his thesis in Königsberg, he also presented some other results which were not in his doctoral thesis, but which he found during his work, and these are the famous incompleteness theorems. The first incompleteness theorem showing that arithmetic showing arithmetic formula which is not refutable in piano arithmetic, and the second incompleteness theorem showing that consistency of arithmetic cannot be proved in arithmetic itself, which meant basically just working with the expression that consistency of theory P is the same as negation of provability that 0 equals 1 within the encoding. In Königsberg, John von Neumann was present there, And when he returned to Berlin, that had interesting consequence, because he, at that time, had a full semester lecture concerning the Hilbert foundations of the theory of mathematics. When he returned from Königsberg, he stopped the program of his talks and started to work instead with Gödel's result, because he basically saw that what Gödel presented in Königsberg meant complete destruction of Hilbert program. That is impossibility of proving consistence of formal system inside of such a formal system. This is the well-known result, which then led to consequences which can be viewed from one side as complete destruction of the attempts to build the foundations of formal mathematics using Hilbert program, but at the same time as something which actually allowed to give rise informatics as discipline by itself. The other extremely important logician at that time, who is not mentioned very often, was Gerhard Gentzen, who worked on similar topics as Gödel in some correspondence. They did have some communication about these problems. And basically Gerhard Gentzen, together, that is in parallel with Gödel, independently each other, showed translation of Peano arithmetic to intuitionistic Heyting arithmetics during the years 1932 and 33. Gerhard Gentzen is similarly interesting person as Kurt Gödel with respect to Czech Republic. He was not born in Czech Republic, did not live in Brno, but he was invited to Charles University, or to the German Prague University during Second World War. His life ended actually in 1945 in a sort of seemingly similar way as Gödel's. He also died of starvation, but Gödel starved himself to death while Gerhard Gentzen was starved to death by Russian soldiers, because he was German at German university, German professor, and as such was considered sort of one of the Germans assumed to be sort of terminated. Gerhard Gentzen did, during 1934 till 35, analysis of mathematical proofs, introduced two extremely important tools for proof analysis. One of them, so-called natural deduction, based on introduction and elimination rules for logical connectives. And another formalism, which he called sequence calcul. Nowadays it's called sequence calculus. The name is by Kleene. And there are operations of simplifying proofs within these systems based on normalization and cut elimination. Normalization means simplifying the proof structure, looking for structures where introduction is immediately followed by elimination, and sort of compressing the structure of proofs. cut elimination means essentially expanding mathematical lemmas used within proofs into the structure of proof and simplifying the complexity of the proof. Gödel and Gensen, they both worked within proof of consistency of Peano arithmetics. Gensen proved this by providing alternative proof to incompleteness theorem. That was written in 1939, published in 1943. And he showed formula unprovable in Peano arithmetic constructively. And this also meant that he showed consistency of Peano arithmetic. Because if that formula would be contradictory, then that would allow to prove any outcome. So the counter argument to that was that Peano arithmetic is complete, is consistent. Gödel's proof of consistency used different mechanisms, of so-called dialectica interpretation. It is not known whether those two actually communicated about this problem among themselves. They did meet in 1939, but it's not known whether this was a topic which they discussed together. With these results and the Hilbert's decision problem, we can find connection with another school of building foundations of mathematics, and there was American logician Alonzo Church, who tried different formalism than Hilbert systems for formulating the formal basis for mathematics, the so-called lambda calculus, which is basically functional mechanism with functional transformations within the formal apparatus. And he also at that time worked together with Alan Turing, who visited Alonzo Church in Princeton already after formulating his Turing machines. Alonzo Church was the first who proved the existence of undecidable problems, proved that the decision problem is the positive answer doesn't exist. Nowadays, this result is usually associated with Alan Turing, who came with this result just a couple of weeks later, independently based on different formalism. But this was also interesting parallel way of proving the existence of undecidable problems of informatics. In some sense, this is similar to the impossibility of proving consistency within a theory of itself, something which cannot possibly done here within computable processes. We have also a class of problems where we can prove that the solution actually does not exist, no matter how we try. Church, Turing, and Gödel met together with their work with formalizing the computability issues. Church used lambda calculus as formalizing as a formal tool for mathematics, when he learned about Gödel's result, he claimed his first reaction was that that result does not apply to lambda calculus, because that's completely different system. In a sense, he was right, because lambda calculus did have contradiction inside of itself. So everything was provable, including consistency of the system. When these contradictions were removed, there were two doctoral students who developed different parts stemming from this: Kleene with recursive functions and Rosser with systems of reductions, one-way transformations. Church-Turing thesis for computable functions then unified approaches of these three men to computability, claiming that actually whenever we try to formalize mechanical computability, then these mechanisms are equivalent, and any other will be. Turing machines, lambda definability, and Gödel's general recursive functions. As a consequence of this, the kind of simplifying the use of formal mechanism, using it more for mechanical computability than for full-scale formalization of mathematics. That came in the 60s of last century with the so-called Curry-Howard correspondence or formula as type paradigm, where intuitionistic logic was actually shown that it provides computational semantics. That computations are normalizations from the system of natural deduction, which I mentioned with Gensen, or the process of cut elimination within sequence systems. And intuitionistic logic is actually not tied to any philosophy of mathematics, but corresponds to program execution. Another development in this is Girard's linear logic, which is generalization of sequence calculus capable of describing even parallel systems. This is actually a direct consequence of the problem identified by Gensen, by Gödel, when he showed that there was no way how to continue with full-scale mathematics, that the arithmetics actually has to be cut off from that, and the structural properties of proofs, which remained as a task for logicians, came directly as a structure of algorithmic computations. This is a side result of what Kurt Gödel achieved. Does anybody know what is the time? Yeah, almost. What could be added, especially here at the Observatory, is another stream of development which is not directly linked to Gödel, but I feel that it's in a very similar spirit. If you take information in Claude Shannon's formulation as a measure of difference, and entropy as a measure of uncertainty within the bit values, this actually leads to thermodynamics in physics and the second law of thermodynamics. And in 1961, Rolf Landauer actually found that this work with information has very deep physical meaning in the sense of dissipation of energy within providing one-way computational transformations. Any logical, irreversible manipulation of information, that is any one-way computation, must be accompanied by corresponding entropy increase in information processing apparatus or environment. This goes to not to the limits of formal systems, but the limits of computations. Here at the observatory, again, the first bullet is the Bekenstein bound is linked to Jacob Bekenstein, who was Mexican physicist who derived at the end of 70s the analogy of entropy within the surface of black holes. I have very nostalgic recollections to this, especially at this place, because I used to lecture here about black holes, and I would send requests for reprints from which were related to that. Jacob Bekenstein, when I was still at high school, at gymnasium, sent me, he was the first who sent me a reply addressing me as Dr. Zlatuska, so I felt somehow. Based on Bekenstein's result, Stephen Hawking, there was one part which was used by Stephen Hawking when actually discovering the Hawking radiation and evaporation of black holes. But Bekenstein found that whenever we work with event horizon, there is just a limited amount of information which can be sort of stored on the horizon. It came with quantification of this. From that, based on the previous slide, we can actually derive the limits of the amount of information which can be described by a given physical system. A human brain with volume 1.2 thousand square centimeters has Bekenstein bound about 3 times to 10 to 42nd bits. Seth Lloyd, this is the last point, derived the limit of possible quantity of computations which can happen within observable universe, within the age of universe, and came to conclusion that the universe could not perform, no matter how you organize these computational processes, more than 10 to 120 operations on 10 to 90 bits. So here we have some kind of, again, limitation in the physical sense for what can conceivably computed by any feasible computational mechanism. And it seems to me that it's very similar to the results of actually having formal theories. Within the theories, the space of proofs simply does not include certain formulas because they are outside of the limits. Here we can see that certain computational processes, even certain numbers which can be evaluated, are simply outside any reach of any possible mechanical process to reach. And most likely, even some of the mathematical objects which were envisioned by Kurt Gödel may actually lay outside of the reach of any feasible way of calculation. By this, I felt that it would be appropriate to mention it here. I would conclude and wish you more interesting talks after me. Thank you.
Thank you. Ladies and gentlemen, it's my pleasure to open the, more technical part of the conference. We have several contributed talks and several invited talks. And now we have the first invited talk, Professor Rosický. The title of his talk is From First Order Logic to Accessible Categories.
So, thank you for the privilege to give the first talk here, although this privilege was a little bit stolen by Jiří Zlatuška, who instead of ceremonial speech gave a real talk with content. But this is good because in some sense it gave some kind of impression how logic developed and what are the applications. So logic always had two parts, so it's syntactic and semantical one. So syntactic means that some language which speaks about something, and this something is semantics. And the Gödel completeness theorem, which was mentioned, is exactly that syntax corresponds to semantics, so you can prove exactly what is true. So I will be more on the semantical side. In fact, I will be very brutally on the semantical side. And this semantical part of logic is called model theory. So logic speaks about some structures. So those structures, so that you have some set, it's very set-based. And on this set you have some either operations, like in a group, you have multiplication, or some relations like in ordered sets, you have a relation of less or equal to. And in some sense you want to show, of course you can prove something about groups, something about those ordered sets and so on, but you would like to prove something which is true for anything which can be formalized in the predicate logic. And it's a very strong limitation to formalize something in predicate logic, because you have strong tool, for instance, compactness theorem, which tells you that if you have any set of axioms, say that any finite subset has a model, so the whole set has a model. But not all structures which are interesting can be described in predicate logic. So there was, since the beginning, there were attempts to go to something more general. And in fact, I want to somewhat survey this development. So, no, this lecture was in some sense for me a black box, because I didn't know what I can expect from audience here. So I tried to be as understandable as possible. So now here you immediately see some technical things. So first order theory. So this is something which can be axiomatized by this predicate logic. So in some language, the language, this is a list of those operations and relations you are speaking about. And you immediately get from it something which is called a category. So the category consists of objects. Those objects are structures. And then consists of, say, allowed transformations between them. So in structures, these are mappings which preserves those operation relations. So for instance, in vector spaces, those transformations are just linear mappings. In ordered sets, they are just mappings which preserve order, so isotone mappings. So and this forms some abstract things called a category, which means that you only want to have those objects, those morphisms between them, you can compose them. If you go from one object to another, from another to third one, so you can compose it. And then you have something like identities, which are transformations which don't do anything. So that's a category. In fact, categories were, one can say, invented in 1945 in a foundational paper of Eilenberg and MacLean, so topologists and algebraists. And since then, it became a language which is used in many, many areas of mathematics. So what I meant under this brutal elimination of syntax, is that I take this category, the category of models of this theory T, and I take this category just as an abstract category, so just object and morphisms. And so this is, in fact, somewhat pure semantics. And I would like to say something using this language, and also those generalizations I mentioned before. So this category, or if you don't like this word categories, you can take this word of those structures you are interested about, has another important property, which is called the downward-levelized column theorem. So this means that you have your structure. It could be very big, and you take a small subset, so you can always generate small substructure on a subset. And this substructure is such that this inclusion of the whole structure preserves everything and reflects everything. So it's something which is called elementary embedding. But before coming to elementary embedding, I just take those models and homomorphisms, and then I know that for some size, some cardinality, which is big enough, you can, like any set is a union of, say any set is a union of finite subsets. And this union is directed, which means that having finitely many finite subsets, so the union is again finite. So if you go up to an irregular cardinal, so in that way, you can show, this is this downward-levelized column theorem, that any structure is such union of its substructures. This union is not only directed, but lambda directed, which means that having less than lambda, though small, so that the union is again small. So this will be important technical tool. I will need the whole talk, yes. So now a little bit of syntax. I am still thinking of this category of models. So formulas are those formulas of predicate logic. So which means that you can use logical connectiveness like conjunction, disjunction, implication, and also quantification as an existential one. And you call a formula positive primitive if it is existential quantification or a conjunction of atomic formulas. And you call it positive existential if it is a disjunction of those. And now basic axiom is that you take implications, universally quantified implications between those positive existential formulas. So this is a very general way how to describe structures. For instance, any equation, like in a group associative law, is such thing when on the left side this phi is true, and it implies this equation. Or if you're in ordered sets, you have transitivity of order. So again, this is this kind of this formula. And the property of those theories consisting of those basic formulas, they are called basic theories, is that they are closed under unions and directed unions. So which means that if you have a category of models of those basic theories, so you have two properties. So one is that anything can be glued in a nice way from small subthings, and then any possible of gluing can be done there. And this is in fact something which can be taken as axioms, as properties of a category. So just here it's what I told you, that those something given by equations or by implications is basic, yes. And this is what I told you there. So, and the definition is accessible category. So accessible category is category. It means we have objects and morphisms, and you can compose them. And this category has two properties. This first one is that you can take all these possible unions, but in this case you have to choose regular cardinal lambda, and you have those lambda-directed unions, which should be called lambda-directed colimits. I think you can imagine just unions. I don't need to go technically to that. And the second thing is smallest condition, that anything can be taken in this way as a lambda-directed colimit of lambda small subthings. So this is definition. Then but something is missing, because how I formulate this is small, because in structures it's easy, because I take structure, its underlying set, and I measure its cardinality, and if it's smaller than lambda, so it's lambda small. But having an abstract category, I don't have underlying sets. So but it can be done internally. And it can be done internally, again, is language of those lambda-directed colimits. So an object is lambda presentable if its home functor presents lambda-directed colimits. Well, technical, but you can imagine it that way. So you take lambda-directed union of finite things, and you take element in the union. So it belongs to some of those finite. So it is very similar. So if you have a morphism into this union, so it factorizes through some of those which constitute the union and instantiate uniquely. So this is an abstract way how to formalize smallness just using a category, and it works. It works in the sense, just accessible means lambda accessible for some lambda. It works in the sense that this abstract definition of smallness coincides with this concrete definition of smallness in important situations. Yes, I want to say that this concept introduced by Mackay and Paré in 1989 didn't come out of blue, yes, because it had some predecessors. The first one was Gabriel and Ulmer in 1971, when they introduced locally presentable categories, which are exactly those, but instead of one, you have all colimits. So not only the special constructions, but all constructions. And then also some kind of anticipation of this structure was in Grothendieck. That was a famous name who somewhat revolutionized geometry. And in this seminar, Geometry Algebraique, in fact, he had something which was a kind of attempt to do that, yes. And that also, there were some isolated steps to go from those Gabriel Ulmer to this definition. One done by Christian Lehr, the other was done by me. And basically now what I try to explain you at the beginning is that this category of models of a basic theory, basic forest theory, is accessible. Because you take this lambda, which I had before, you have those lambda-directed unions, because it's basic, and also you have this, by Leibniz-Coulomb theorem, you have this second axiom that anything can be expressed from small ones, and the small ones corresponds to that abstractly small. Well, but good example, so just I mentioned structure like sets. It means that no structure, just set, no relations, no functions, or partially ordered sets, which means ordered sets, so you have less or equal relation, or groups, you have multiplication. So these are all examples of absolute categories, and always this lambda presentable corresponds to the size smaller than lambda, so it fits. So in fact, this Gabriel Ulmer formalization of size, in fact, fits with usual usage. But there are also some other interesting examples, and now it starts to think that not everything what mathematicians or people who use mathematics need is first order. Metric spaces, just spaces where there are given distances, which are real numbers. So, and as a transformation between them, you take contractions, which means that if 2 points have distance, so the images cannot have greater distance. The distance of images is less or equal to the distance of those starting 2 points. Or Banach spaces, so famous mathematical structure needed in functional analysis. So again, here those morphisms are linear contractions. So the same thing, but also it should preserve the vector structure of a Banach space. Or Hilbert spaces, so famous thing which is, for instance, needed in formalization of quantum mechanics. So again, with the contractions. So in these examples, the meaning of this abstract presentability is different, because in a metric space, it doesn't measure the coordinate of underlying set, but it measures the so-called density character, which is the coordinate of smallest dense subset. The same in Banach spaces. It's even more natural in Hilbert spaces when then this abstract size actually corresponds to the size of orthogonal base, which generates the Hilbert space. Oh, sorry, I go other way. Yes, so, but now I would like to get rid of this limitation that my theory T should be basic, because this is very general but still special. So if you want to do it, so then you have to change your morphisms in your category. Not all homomorphisms, but only element embeddings. In fact, in model theory, it means the semantical side of logic, these are exactly the right things, these elementary embeddings. So again, now I take category different notation, which consists of those models of this theory, but morphisms are elementary embeddings now. And this category is always accessible for any first order theory. You don't need basic for this. And in fact, it's true even for something that was the first generalization of first order logic, that you allow also infinitary operation relations. For instance, in a well-ordered set, if you want to say there's no decreasing countable chain, so you cannot do it with finite quantification. So you need more general, you need conjunctions of not only finite, but less than on an arbitrary number of formulas. And also you can quantify not only over finite set of variables, but over also infinite. So these are infinity logic. So this L kappa lambda means that kappa limits propositional things, it means conjunction disjunctions, and lambda limits quantification. So L kappa kappa means that the both are the same, yes. So, and instead of elementary embeddings, you take kappa elementary embeddings, so those which are appropriate for this logic. And then again, you get the same thing. This category is accessible. And in fact, one can say that any accessible category appears in this way. So any accessible category can be presented as a category of models of some infinitary, now first order logic, and elementary embeddings as morphisms. So now here you see this correspondence, and the book of Mackay-Paré was called Accessible Categories, the Foundation of Categorical Model Theory. So really that was this one-to-one correspondence between, come to say, syntax, which is now infinitary first order logic, and semantics, which now is this accessible category. But I repeat, in this accessible category, in general, I don't have these underlying sets and relations operations. But it can be somewhat found that these two things are as categories the same. So that was the first step. The second major step, how to generalize, was Damai-Shelach. So I don't know, this name should be mentioned in any historical description of model theory. And in 1987, he introduced abstract elementary classes. So what's an abstract elementary class? So still you keep a part of syntax because you still have your language. So you have some list of operational relations which are finitary, yes? So you have some language like in first order theory. But you don't have formulas now, yes? And instead, I have to say, my description uses category theory, which Shelach never have done, yes? But that's just another language. So now he doesn't choose those structures by some axioms, but just he takes some collection of structures. He doesn't choose some morphism preserving some operations or elementary and so on, but he chooses some of those. So they call it strong embedding. So for me, just it is a category, which is a subcategory of the category of all sigma structures. So it means that you have some choice of objects, and it means structures, and some choice of morphisms. No, but it should now satisfy something. So at first it should be category, so it should be closed under composition. But also, you have the third thing is still it should be closed under directed colimits in structures. Like if you had this basic theory elementary bending. So it should be closed under directed colimits in structures. The second thing is, this is called coherence. If you have 1, 2, 3, so a composition of two, say, homomorphismal structures. So if the composition is strong, so it's chosen, and the second one is strong because it's chosen, so the first one, which is obvious property of both embeddings and elementary embeddings. So it should be coherent. And then that's abstract formulation of Leibniz-Coulomb theorem, that you can find some lambda such that any lambda small thing has a lambda small substructure. So this is the definition of an abstract elementary class, which now you see this syntax is limited only to language and no formulas, just properties you want, yes? And he somewhat started to do model theory for such things. And from this definition, it's basically visible that, again, any such abstract class gives you an accessible category. Because you have this Leibniz-Coulomb thing, that was the last axiom. You have this first one, which tells this to these lambda colimits. But of course, you have something more, because you should know, because in the definition, maybe that was written, I didn't point it up, those strong embeddings were always embeddings, which means that they were in category 3 monomorphisms. So I will not give a definition of that. So here, another specialty was that morphisms are monomorphisms. So, and a typical example of an abstract elementary class is something which can be axiomatized by infinitary conjunct disjunction, but only finite quantifications. This is called L kappa omega. So this finite quantification exactly gives you that it's closed under directed colimits. So this is an abstract elementary class. This previous category, LMT, is an abstract elementary class. Then here I have two technical things. So the first is coherent. I mentioned that. The first one, which follows on the definition, is isofull. It means that any isomorphism of structure is strong, is chosen. which is very natural axiom because any isomorphism is an embedding, any isomorphism is elementary embedding. And now that's a theorem which in some sense characterizes abstract many classes as categories. You see, this theorem was found independently by me and Tibor Becke and by Mike Lieberman, basically at the same time. But you see, you have strong time difference between definition of elementary class and this theorem, but it doesn't mean this is something difficult or deep. Simply, these two communities were so distant that nobody looked at this. But this is interesting things which in some sense link this, say, model theoretical fashion, how to do abstract model theory and say this categorical approach. This characterization again tells you have a category. There's no mention of some structures or underlying sets, but you want to embed it into something which are basically structures. So in fact, in the formation of that theorem, this language sigma is encoded in this, what is here called finite flexible category. So still this is very, very similar to the starting definition that you don't get these underlying sets and operational relations just from the abstract category, but from this representation or this embedding. But now it appears a question. Is it really a generalization? Which means, is this abstract elementary class really more general than something which can be axiomatized by infinitary conjunction, disjunction, and finite quantification? So is there an abstract elementary class which is not the same as this category of LMT, that is of L kappa omega? You see, for model theories, this is an easy thing because if you have a given signature, so that's easy to give example in that signature, which is not an abstract elementary class in this signature. But it opens a way that this could be done in a different signature. It looks a little bit obsolete or strange from a model theoretical point of view, but it's quite natural. I will try to argue why. So that was a kind of frustrating question, which was quite recently solved. That's a kind of breakthrough by Simon Henry. He was a postdoc in Brno, now he got permanent position in Ottawa. And he showed something which everybody expected, that it's not the same. And an example of an abstract elementary class which cannot be axiomatized by finite quantification, that simply take uncountable sets. So objects are uncountable sets, and morphisms are injective mappings. So this is clear that you cannot axiomatize it by finite quantification in sets because you cannot say uncountable using finite quantification. But the question is whether it cannot be done in some different language. I have to say that we tried to do it with Makai in 2014. That was a very natural example which should serve, but we were not able to do it. So it's in fact a deep question. And Simon Henry did it by really introducing new tools, new techniques, which I try to describe a little later, having time. So now come to this question of size, which I started to talk at first. So I told you there's an abstract categorical way how to describe size, which is called its presentability, which means that this technical thing that home functor presentability co-limits. And you can take the smallest lambda, such as the object is lambda small. And you can hope that this smallest cardinal is successor. Then you would be in the same situations like in sets, for instance, where then this, so if the small is a lambda plus, then lambda would be cardinality, would be the size. And this is indeed true if you have an abstract accessible category with directed colimits, so then always the smallest thing is a successor. Under GCH, and general content hypothesis, that's true in general because some kind of arithmetics enters there. But if you directed colimit, so it doesn't. So you have now this abstract notion of size. Once I mentioned those Hilbert spaces where this is the kind of orthonormal base. So this is the first thing, that you have just abstract category, just object and morphisms, nothing more, and out of nothing you get size. You don't have underlying sets, but you have those sizes which more corresponds to something like dimension of your object in some sense, like dimension of Hilbert space is the size of its orthonormal base. This is just an example. I don't know whether I should spend time with that. That in Banach spaces, the precise notion is here, you have arbitrarily large gaps of cardinalities, like in Hilbert spaces. This is just kind of, say, cardinal arithmetics. So which is something one cannot have with first order theory because you don't have large gaps, large holes in underlying sets. But in Hilbert space, in Banach space, you have it. But it disappears when you go to this internal size. It's much smoother thing. Typically in Hilbert spaces, for any cardinal, you have a space which is not on the basis of this cardinal. And in some sense, this is just something which you can ignore what happens with number of elements of this Hilbert space. So this is the advantage of these abstract sizes. And I will say that in abstract elementary classes, these abstract sizes from some moment start to coincide with cardinalities. So in studied situations, this is the same, but if you go to something really infinitary, so then you should go with these little sizes. And with Tibor Beke, we showed that if you have an accessible category with directly colimits, so this is what I told you, these presentability ranks are always successor, you have sizes, and then this is so that just I recalled. So now we ask ourselves a question whether you can have in accessible category arbitrary large gaps of sizes. So we saw that there is something easy that you can get easy counter examples, but that's not true. This is open, yes? Now there are some attempts to do it, so that's not clear. So if it doesn't happen, so we called it LS, leavenized column accessible. It means that just you don't have large gaps of sizes. And under some assumptions, you can prove it. So that's one thing, that if you have explicit colimits, but those direct colimits are calculated like in sets. So your category now, in fact, has underlying sets. It's equipped with a functor going to sets, which plays direct colimits. So in that case, you cannot have large gaps of sizes. So this is more general in abstract elementary class, and still it is true here. Another condition by me and Lieberman is that now you don't have underlying sets, but morphisms are monomorphisms, and you have directed colimits still. So again, it's smooth. It cannot happen. Those are large gaps of sizes. Now, here in this situation, there's a question which might look silly. So you take Hilbert spaces, and now with not linear contraction as before with isometries. So there's isometric bearings one Hilbert and another space. So if you take the forgetful functor to sets, so then it preserves either one directed colimits, but not directed colimits. Because if you take, say, finite things, you say union, so you have to take also limits of sequences there because it should be complete. So those behave badly. So one would expect that you cannot find a functor Gaussian Hilbert spaces to sets, which is faithful. It means that two different things go to different things. Otherwise, you could take some not interesting functors, which doesn't preserve directed colimits. And using a part of this technology invented by Simon Henry, we could show that simply it cannot happen. And it cannot happen for commutative C-star algebras, which as a consequence has, you see here now this was joint work with Lieberman and Sebastian Vasse, that this category of commutative C-star algebras cannot be axiomatized in a first order theory. Something more special was conjectured by Bengtsson and independently solved by Banaszewski and me, so that this is a kind of ultimate solution to the Bengtsson problem, following from this result I mentioned. So now let me to try to a little bit to describe the situation. So you have a category, abstract category, object and morphisms, and you would like to read which relational operation can be interpreted there. Like, for instance, it was the problem with uncountable sets I mentioned, because you can change everything, and you would like to say how you could describe uncountability in a changed environment. So having underlying sets, so having a functor into sets, then you can read those possible operation relations out of that. Well, I don't know whether I should be a little more technical, but that, for instance, if you have a homomorphism from group, so you take two elements, you take multiplication, take image, or you take images of elements and multiplication, it is the same, which basically means that this homomorphism is a natural transformation from, say, the square of sets to sets. So this is that was Bill O'Weir, so one of founder of modern category theory, who in his PhD thesis, in fact, introduced algebraic theories based just on this idea. And you can do these things also in relation. So whenever I have underlying sets, so I know in some sense the biggest possible language in which your category can embed. And if it can be axiomatized in some language, so it is in the biggest language. But what you do if you don't have this functor? Because then the problem is having a category, what are those possible candidates for those underlying set functors? So here it is technically described for those who wanted how I can describe those relations which can be defined by your category, equipped with forgetful functor, equipped with underlying sets. So that's I told you that we would like to understand all those possible interpretations. That was Simon Henry, which I mentioned, and my PhD student Ivan Di Liberti, who in fact assigned to any accessible category with directed colimits, so something which is very general, all possible functors to sets, not only faithful, all possible functors which preserve directed colimits. So one can view it as all possible attempts how to get underlying sets, and from that relational operations. And this is a category, the category of those functors explaining co-limits and transformation. And this category organizes into something very powerful because it's a Grothendieck topos. I mentioned the name of Grothendieck, in fact, who in some sense really, he was an algebraic geometer. He was not category theorist, but he was one of those who contributed at most to category theory. The other one was Kahn, who did something comparable with algebraic topology. So Grothendieck toposes, there should be some replacements for topological spaces. And he wanted to create on them some general cohomology theory which would be able to prove Weil conjecture. So that was something famous. That was realized by his student Deligne, who got Fields Medal for that. That's Fields Medal, that's just Nobel Prize for mathematics. So this is a very important structure which links logic, geometry, and category theory, the concept of Grothendieck topos. So those all possible attempts to, now you see, probably it could look a little bit, how to say, subjective or why I want to get rid of underlying sets and operational relations and so on. So in some sense, the point is that you get something which is, say, more general, and it really is something which is in mainstream mathematics. And external categories are clearly mainstream mathematics. For instance, modern homotopy theory is very much based on external categories, or higher category theory, which is now something which is the most fashionable part of category theory, again has their concepts of accessible categories. So this is something which is important. And it's interesting to link, say, model theory, which is always very special because aims of model theory is to classify structures. And model theory developed very fancy tools to do this classification of structures. So it would be nice to have it, whether it could also be used some in other areas, which are not directly, say, model theoretic. So here you get this Grothendieck topos. And on the other hand, having any Grothendieck topos, you can go back. You can take so-called points, which are functors preserving co-limits and finite limits to sets. And in some sense, if you take this Grothendieck topos as a kind of big theory, so those points correspond somehow to models of this theory. And so you get, in fact, correspondence between these well-flexible categories co-limits and Grothendieck toposes and geometry morphisms, which is in fact an adjunction. So that's technical thing, this adjunction which is here. So I think now you can read what I explained or try to explain. And now I haven't avoided any category theory up to now basically, but here this is unit of example. It means you take a look at the co-limits, you go to its topos, you go to its points, so it embeds into it. So that's like you embed your category into the category of models of its full L infinity omega theory. And this is a way how you can recognize whether it can be axiomatized or not. And this is the way how Simon already did it, yes? So for instance, if this unit, this comparison functor is faithful, so it means that's a faithful functor going to your category, to sets from your category, presented co-limits. And also from that you can read whether it can be axiomatized. Yes, so this technology put, say, a tool how to recognize that your category co-limits can be axiomatized by finite theory with finite quantifications. And now this is how we treated uncountable sets, because if you take uncountable sets, so the corresponding topos is the same as that for finite sets. Even has the names called Chanel topos. So this is why you cannot axiomatize uncountable sets, because basically they give the same kind of general theory as finite sets. So this is the way how you can show this is the result. Good. So I'm now coming to my last thing I want to mention. So now I'm coming to something which was main line of development in model theory from first order logic to abstract elementary classes, and it was the question of categoricity. So a theory is categorical in some cardinal if in that cardinality has exactly one up to isomorphism model. And that was famous Morley theorem in 60s last century, who reopened model theory. He showed a countable theory which is categorical in some uncountable cardinalities, so it's categorical in all uncountable cardinalities. So that was quite deep technique to prove this Morley theorem, and people tried to generalize it. It was mostly Schellach who tried to generalize it to infinitary logic and to abstract elementary classes. And this is famous Schellach's eventual categoricity conjecture, which in some sense claims that for an abstract elementary class this is true again. But now let me to say one point. Of course, if you want to formulate this, you need underlying sets because you want to speak about cardinalities. But you can just replace underlying sets by those internal sizes. So you can formulate this conjecture in an absolute category, as we call it, without any notion of underlying set. Well, we never dared to formulate it because it cannot be true, but nobody found counterexample yet. So it could be a set theoretical such questions. So here I mentioned this loss, this loss theorem, this Morley solution, then this development of the Schellach conjecture. Now explaining that it can be done without notional underlying set. Of course, that was meant that we would like to give some limits of this categoricity conjecture. That if you go a little bit more general, you go abstract elementary class, so it is not true. That would show that really this insight of Schellach was just perfect grasp of where you should ask this question. But this is not known. Something is known because Sebastian Vasse, in fact, he proved this Schellach conjecture for universal abstract elementary classes, and together with Schellach, they did it assuming some large kind of axiom that's a proper class of strongly compact cardinals. And very recently, Christian Espindola, so another postdoc in Brno, so try to approach this question using this topos theory. It means that but I want to say that these are hundreds of thousands of pages in the proof of these things, a very delicate technology, including, for instance, abstract independence relation and so on. So that would be very interesting if somebody could translate or replace this intricate model theoretic technology by some results by Grothendieck topos by some category theory. So Christian in his papers gave away to this. Thank you. That's all.
Thank you. So please, we have time for questions and comments. Please, Albert.
Okay, yes. I wanted to ask you for examples of transfer of insights from one subject to another, right? So random spaces, first approaching, I think, and the categoricity example is in fact an example of transfer of insights, but maybe there are others.
No, Banach spaces, of course, cannot be accelerated transfer logic. But there is line of logic of continued model theory. where 1, 2, 3 metric spaces or Banach spaces. And 2, even this is something called metric asymmetry classes, which is actually class for metric spaces. And then for those size bits that always stay density characters and not make sense. So in some sense, this general category point of view, this is the same thing. Of course, the question of can you category theory is not a tool to prove something, yes, it's a tool to conceptualize.
Yeah, but
But on the other hand, for instance, it's quite promising, this passage from those model theories, all the thousands of pages, to rotate properties, to interesting something. It goes back to very old thing that this property of being counterly categorical corresponds to properties of classified.
right. Okay, so
And then I would like to push up when we are in the
that's really an example of transformation.
Yes, it is.
And a rather striking example that we would recognize.
Yes, yes. So that sometimes it's good to forget something you have, to get something which you can use tools which you wouldn't see thinking only. So sometimes abstraction is good because sometimes if you are too concrete, you could overlook some ways. Because for instance, this protein topos is hard to imagine just from the classical model calculation.
I saw the results for L kappa kappa and for L kappa omega, not generally for L kappa lambda. So what's wrong with
Yes.
the arbitrary?
No, that's nothing wrong. You can do it, but in some sense, I made it less fancy. Yes. But you see this L kappa omega, this is really something conceptual. Yes. So, but if you go, even he has some paper along model theory for really big pedagogy, that things disappear if you go to kappa on application side. And so this is a kind of way how you can handle it. That, for instance, this is easy to show that have these gaps in underlying set. This is simply something just for finality omega, so it's kind of omega is bigger than R is, something like these gaps in this very counter operation immediately. But not decisive. So in some sense, it is something which is a new point of view. To change the notion of this invariant, which is much smoother. Then of course you don't change the situation, but you can ask it in more general sense, taking a different example to understand it.
Maybe I can have a live question. I know nothing about categories, but is there something that is dependent on set theory, on the axioms of set theory?
Yes. Quite a lot. I mentioned it just at the end that this shell after inspector's nature was grouped under the proper class of planetarium. So which might indicate that this is maybe set theoretic. So you see, always when you formulate something very general, so you take the risk that it will depend on set theory. So for some people, it's a sign that it's a bad question. For other people, they just show that was the situation. So set theory entered, not only as a discarded, but also as considered finance.
Thank you. So if there are no other questions, let's take the meeting. Ladies and gentlemen, our first afternoon speaker is Alfred from the University of Utrecht, and he will speak about Gödel's second incompleteness theorem in general.
Okay. Well, I'm of course extremely honored and extremely happy that I was invited to speak here. Yeah, Gödel's work was always one of my favorite things in logic, and so yeah, it's great to be able to speak about this here. Yeah, so I will be suffering from also from the problem, of course, that I can only give you an impression, right? It's so there's too many notions, there's too many things, and so yeah. So many of you will only get a kind of impression of the kind of thing I'm trying to explain, but I'll do my best to make it as clear as possible. Okay, so yeah, so my talk is called Gödel's second incompleteness theorem in general, and this is because I'm going to try to explain to you a kind of general versions of the theorem. So what is the second incompleteness theorem? So yeah, what one usually sees and hears is that it's a sufficiently strong theory does not prove its own consistency. But yeah, this is really not an acceptable statement. But what is an acceptable statement of the theory? And so yeah, in this talk I will speak specifically about the question: can we give a decent statement of the theorem that does justice to the generality of our understanding? And secondly, so how general is this phenomenon? So this question about generality was in fact already posed by Hilbert and Bernays in Grundlagen. So it's an old question, but it's still moving, and yeah, in some sense there is you can see that there can be no really definite answer to this. There's never a most general form of any mathematical theorem. Yeah, so I think the problem of the decent statement is really, in some sense, a sub-problem of the generality problem, because the defects of the decent statement is in fact that they are not general enough. Okay. Well, yeah. So there's at least two approaches to generality, and then probably more. Yeah. One can do only so much in a 1-hour talk, so I will completely omit saying anything about the kind of development around the loop conditions. In a sense, that's a bit silly, because I did a lot of work on the loop conditions, but yeah, so I simply do not really have time. Okay, so I will follow a different line. And so this line I will discuss 3 stages of generality. Namely, I will discuss the quantification over interpretations. I will discuss the quantification over axiomatizations, and then, in some sense, the garbage bin, because there's a lot hidden there, is variations in the arithmetizations, and so how we represent things like syntax and provability in the arithmetical series. So these questions are also related to philosophical questions, because if you look at the statement of the theorem, so it says a theory cannot prove a sentence that expresses its consistency, right? But the notion of expressing is not really a mathematical notion; it's a philosophical notion. And so, what do we mean when we say that an arithmetical statement expresses the consistency of a theory? Something could be said about that. And also, we will come to that point later, can we get some grip on the totality of all these sentences well, assuming that that you can sensibly say that the sentence in, let's say, an arithmetical theory expresses the consistency of a theory, can we get a grip on the totality of those things? Okay, so the thing that I first want to explain is the interpretation version of the second incompleteness theorem. And to explain this version, I have to hand wave about what is an interpretation, right? So the full definition would use several pages, but yeah, I can hand-wavingly explain it. So an interpretation of one theory in another theory is based on translation between the languages of these theories. And so an interpretation is a rather dull kind of translation because we demand that it commutes with the logical connectives. For example, the translation of a conjunction should be the conjunction of the translations, and the translation of a universal quantification should be the universal quantification of the translations. So it's a kind of dull thing. So the main thing is that if you have a predicate symbol of the translated theory, of the translated language, that goes into a formula of the translating language. Yeah, so that's the idea. But there's all kinds of extra features. So you know, if you buy a basic program, computer program, etc., then it's simple. But then you get all kinds of extras, and it makes it more complicated. And the same holds for interpretations or translations. So we add features. For example, one important feature is that it commutes with quantification, but we also have a domain formula. You say not for every x translates to for every x, but for every x translates to for every x in some specified domain. And there's many more features. So that they could be multidimensional. So one object from the translated theory could go to a sequence of the translating theory. They could have parameters. So there's a lot of extra features that you could think of, but I think for this talk it's important to keep in mind it's something that commutes with the connectors of logic and things like domain, relativization, etc. So given that then we have a translation between languages, we have then interpretation between theories, and so when do we say that K is an interpretation of V in K is an interpretation of V in U, or U interprets V using K. That means that for all V sentences A, if you have that V proves A, then the interpreting theory proves the translation. So that's the main thing. So it's really a reduction between theories. And in some sense, you could view it like this. So here we have, in a kind of picture, here you have the interpreting theory, and in some sense, the interpreted theory exists inside the interpreting theory. And in fact, what we are going to be discussing is, so there could be many copies of V sitting. There could be many interpretations of the same of V sitting inside U. Okay. And so we will write, well, you see the notation and you read it, of course, as U. V is interpretable in U, or U interprets V. Okay, so the second ingredient, so I need as an ingredient for the general statement interpretations, and I need as an ingredient for the general statement the notion of a weak theory, right? So the more general the theory is, then you want to have a weak theory in the role of what the theorem holds for, in a sense. And so, there is a kind of weak theory that is in some sense best from the consumer's test, and that's, I think, Buss's theory S12. So that's a theory of that was specifically designed to study p-time computability, and so it's an extremely weak theory. It has very little induction, and you cannot prove in this theory of all kinds of functions that they are total. Specifically, you can not prove that exponentiation is total, right? So for the people working on p-time provability, things like exponentiation is in some sense bad, right? So totality of exponentiation is a taboo. So now the nice thing is, so suppose that we want to prove do the usual proof of Gödel's theorem in S12. Then it turns out that it's better than the strong theory piano arithmetic to do that. So why is it better? So in piano arithmetic you have many more resources to prove the second incompleteness theorem than in the weaker theory S12. Well, if you can do more foolish things. And so, for example, you can use very crazy Gödel numberings, and people in fact did use very crazy Gödel numbering. If you just have S12, it more or less guides you to see what are the natural ways of doing things, and so so to do the usual proof of the second incompleteness theorem in S12 is in many senses better. Of course, okay, we still have one. So we can go even weaker than S12, but then you need special pleading, right? So in some sense, the intuitive thesis is that S12 is that's not really a mathematical thesis, but in some sense, it seems to be the weakest theory where you can do this in a really natural way without ever having to really think about what you're doing, right? If you want to do it in I delta 0, for example, you really have to think and need kind of special arithmetization of syntax, etc., etc. But in S12 you don't have to think because everything is, as I said, natural. So now I can formulate the interpretation version of the second completeness theorem. So consider any consistent recursively enumerable theory in a finite signature. Well, it's not really needed, but it's easy for the statement. And so let alpha u be a formula that represents the axiom set of u. And of course there's a kind of official definition of what representation means, of numerates, you could say, but I'm not going to give that. But so it represents in an intuitive way the axiom set, and then I have to say what sigma 1b is. Sigma 1b is in some sense NP, so it's so you have to read simple here, so a very simple representation of an axiomatization. But every theory that you will ever, every natural theory you will ever encounter will have such an axiomatization. So so then what you cannot do is that U interprets S12 plus the consistency statement of U, right? And so I really, because you should think, so we are not saying these things themselves, right? We're trying to think inside the theory U. And so how can the theory U talk about its own axioms? So what is essential is that it has some representation of itself, right? So it's the consistency statement is in some sense not really about the theory U as given by God. sub specie aeternitatis. It's not falling from heaven. It has to be given using some representation. Okay, so now, but what is con? So con is your favorite arithmetization of consistency using your favorite coding scheme, and for the moment we are going to fix this. So that's really, that approach was the approach taken by Sol Faferman in his famous arithmetization paper. So I will return to this point. So this is the kind of very general statement, right? So note that the statement doesn't put any conditions on you, right? So the conditions on weakness and strongness of the theory are really on the other side, right? It just says that you does not interpret that very weak theory, right? And so the point is, so the weaker we can make the theory that's there on the right hand side, the stronger the theorem will be. So it's an extremely strong version that in some sense says that no theory can prove its own consistency, at least not in the environment of this very weak theory, you could say. Yeah, so the relevant, maybe I should. So the interesting point is, and so this was never so much discussed in the literature. So here we have the theory U, but so you can find a great number, usually a great number of representations, in fact, an infinity of representations of the natural numbers in the given theory. So these things are at a lot of places. And so you could ask yourself, so what is the relation between given U, or between the consistency statement here and the consistency statement there, and the consistency statement there, and the consistency statement there? So what is the relation? And so for a large amount, for a large class of theories like piano arithmetic, primitive recursive arithmetic, I sigma 1, ZF set theory, for a large class of theories, what we find is that you can find two of these things where the consistency statement of this one doesn't prove the consistency statement of that one, and vice versa, right? So you can find consistency statements that are completely independent. Also, in general, there's no best one. So if you have piano arithmetic, then there is a kind of best one that implies all the others. But in general, you do not have that, right? For a large class of theories like S12, elementary arithmetic, primitive recursive arithmetic, ACA 0, Gödel-Bernay set theory. So you cannot find any A that is in some sense, you cannot find a sentence A that is still independent of U, that is not proved by U, but that is proved by every consistency statement here, right? So you cannot define in the series something like the infinite disjunction of all these consistency statements. We will return to that later. So now there's, so as I said, so the theorem, let's move back to the theorem for a moment. Right, the theorem gets better when we can replace S12 by weaker series, but you do need some special pleading. So we can improve it, and in fact, one such way is due to Pavel Putlak. So it's namely that you can put Q in the place. So called the Robinson's arithmetic from the Tarski, Mostovsky, Robinson's book in place of S12. But to prove that, you need to not simply follow Gödel's original argument naively in the context of S12, but you really have to do a little bit of extra work using some technology that was invented by Robert Solovay. well, there's an equally or almost as weak series PA minus that works. That you can simply adapt Pavel's argument. It works the same for PA minus. Yeah, there's an. So can we still get weaker? So now I quote Fedor, who's also here. So take any true pi01 sentence then, and take any theory. So this is not correctly stated. I should have said any theory that does interpret R. So take the theory R. So that's also one of Tarski, Mostovsky, Robinson series, but it's still weaker, a lot weaker than Q. And so the result doesn't work for R. So take any theory, and I should have said, so a theory that does interpret R. So Fedor's observation is that any such theory also will interpret R plus P for any true pi01 sentence. So for any sentence of the form, for every X something decidedly is true. And so a fortiori we have that U will interpret R plus its own consistency, right? So if you substitute R for S12 or Q in the interpretation version, then you don't get the second incompleteness. And in fact, Fedor did a lot more in a recent archive preprint. He produced a very natural and consistent theory W that in fact does not prove the consistency in a non-contrived set of numbers of the theory, right? So that's maybe the best way to say it. Yeah, so now the philosophical remarks on this. So this question about what is it for a sentence to express the consistency of a theory. So I think it really has two phases, right? So if, for example, we are thinking about the arithmetical language, so the arithmetical language has a kind of intended semantics. It's a language that is about numbers, right? That's a non-first order way of looking at it. So if we think of this sentence with the standard semantics, so that as being about numbers, then we can ask our statement, so what does it for an arithmetical sentence where the arithmetical quantifiers are really over numbers, etc. What does it mean for that to express consistency? So that's one question. But also, so many people have thought that no, it's really something about the theory, right? What is it about the theory that makes the arithmetical statement express consistency? Okay, so this is a controversial philosophical statement. So my 2 cents in this discussion is that, so this second question is a red herring. It's a wrong idea, right? So it rests on the impression, the mistaken impression that merely formal theories, in some sense, by their rules, generate meaning, and I don't think that's true, right? It's what we do with the theory that makes it meaningful. It's not the meaningfulness of the statements are not produced by the theory, and so nothing about the theory can, by my lights, but I think again it's very controversial. By my lights, nothing about the theory can make any sentence in the theory express whatever. So you really need to ask it for the standard thing. And so now you could view the interpretation version really, so we can read it of course as giving a relation between two merely formal series, but why shouldn't we read the second one, S12, as a meaningful theory that is about numbers, right? So, so my idea was to address the question of expression. You should view the statement of the theorem as expressing a relation between any formal theory whatsoever. So that theory by itself doesn't have to be meaningful, and it's a relation between that and meaningful theories like S12 plus con alpha u. And so if you view it this way, then we only need to face question A, which of course, well, that question faces considerable problems, but at least we reduce the problem to just one question. Yeah, so I think it's even better when we, and when I was writing these slides, I got my feeling became stronger and stronger that that's the right way to go. That it's even better when we replace S12 by a weak syntactic theory, because then you eliminate the detour over Gödel numbering, and so you can sidestep the worry. So how can numbers talk about syntax, right? No, you reduce it to the question then, how can syntax talk about syntax, which seems to be a more logical thing. But I think that then there's, well, it doesn't really solve all our problems, because with syntax theory, and even given the syntax theory, then there's still a question of how to codify your formulas and proofs. There are still many conventional choices, and you're still quantifying over these, so there's definitely something that is not yet quite understood. Yeah, so Michael Detlefsen, in the context of Hilbert's program, insisted that to really refute Hilbert's program, we really should that no sentence that expresses the consistency would be provable in the given theory. So there's a quantifier, so not this one chosen one, but there's a quantifier on all things expressing. And so so our interpretation version quantifies over sentences that are presumably expressing consistency, but is that enough, right? So, but because we restricted us to certain axiomatizations, we restricted ourselves to a fixed arithmetization, and can we eliminate this? So one problem is, of course, that the quantifier over all reasonable arithmetizations is not a mathematical quantifier, right? Because the reasonable is a philosophical notion. So yeah, there's still some work to do. Okay, so now the next step is, but we can eliminate this restriction to RE series, and we can eliminate this restriction to simple formulas in an amazingly, I showed you the interpretation version, and now I'm going to give this seemingly hugely large generalization of it, but the argument is extremely simple, right? So it's kind of lazy man's improvement, but it seems to be extremely strong. So consider any consistent theory U. And now let X be the set of Gödel numbers of axioms of U. So we do not put any constraints on the complexity of the axiom set here, right? So it could be pi 117, it could be pi 175, it could be non-arithmetical, it could be non-analytical, it could be, well, it could be anything. And so now let let x of k be the elements of x that are smaller or equal than k, right? So the Gödel numbers of axioms that are smaller or equal than k, and let uk be the theory axiomatized by x of k. So now suppose we fix some interpretation of our favorite weak theory in U, and then we say that a U formula psi uniformly semi-numerates X with respect to n, if for every number n you can find a larger number such that Um proves that that I is an axiom of UN, right? So that it's not, so it's a little bit more than simply numeration. It should be uniform, namely that the axioms that you can always find a sufficiently large finite series that proves for every n you can find a sufficiently large finite series that includes the first n axioms that proves that psi enumerates the first m axioms, where the m is the axioms of the theory itself, right? So that's the uniformity. And then we get the following form of the theorem. So suppose psi uniformly semi-numerates the axioms of U with respect to some fixed n, then U does not prove the consistency of its own consistency as represented by psi, right? So yeah, I put square brackets there because I want to emphasize that psi could be any formula, right? It does not need to be relativized to n. So it's an arbitrary formula. Now, yeah. So the first thing I would want to say is that so this constraint on uniformity is really needed. Because one of the most celebrated and studied examples of an axiomatization where the theory does prove its own consistency is due to Sol-Pfefferman. So Sol found an axiomatization of piano arithmetic. I call it pi. Is this an asterisk or a star? Well, let's say it's an asterisk. So I call it pi asterisk. And this pi01 axiomatization has the property that PA proves its own consistency with respect to that axiomatization. So that for the formula pi numerates the axioms of PA and PA, but it does not do so uniformly, right? So that's there is the escape route. So it's not contradicting the second incompleteness theorem as formulated in this strong form, because it's the definition is not uniform. So positive examples are all kinds of oracle provability, and so for example you could think of provability with an oracle for pi01 truths, and yeah, such forms of provability provide alternative formulations of partial reflection principles. So I think Pavel is going to say a little bit more about reflection principles. So such provability, such oracle provability predicates play an important role in Lev Bekremish's program to do proof theory using provability logic, right? So so 2 points about this general version. So first, the constraints that we put on the axioms are really needed, because if you drop the uniformity, the whole thing blows up. And secondly, it's not a kind of idling generalization, because really important examples really fall under this generalization, right? So like the things, the provability predicates studied by Lev. Okay, so now the last round. Yeah, it's a pity that I cannot. It's yeah. You should forgive me that I do. This is yeah. Look at this more or less phenomenologically, so you get a kind of impression of what's going on. So of course now the major pain of Gödel's theorem is really the design choices, right? So of course we know the problem of design choices in all of mathematics. right? So if you think about Stokes and Gauss theorem, so I think so. Suppose you want to know what Stokes' theorem is or Gauss's theorem, and go to a contemporary mathematician, you will discover that it's not one thing, but rather a kind of cloud of versions. And also, you will discover that those theorems are not coding free, right? So if it's stated in terms of the real numbers, so are these the delicate numbers are defined by Cauchy sequences? There's all kinds of coding going on, and there's also all kinds of indeterminacy going on in any great theorem of mathematics. But I think so the problem for the second incompleteness theorem is that you have two rounds of this vagueness, right? We have the cloud-like character both at the meta level, but we also have it in our representation of what's going on in the meta level in the series itself, right? And so, of course, so this question, can we find coordinate-free series? So it's not the illusion that we can eliminate all design choices, because I think it's impossible. So our Platonic cravings can never be quite fulfilled in this world. But we want to eliminate them in the transition of syntax, meta syntax to object syntax, right? So that at that level we want to find. We don't want this. We don't want this dependency on the chosen Gödel numbering. And of course the problem. So if you look in a textbook, so what is the second incompleteness theorem? So you find a neat introduction, you find a Gödel numbering, a development of things, but of course, and then you have a consistency statement, and in the book it's said that the theory does not prove that consistency statement, right? But it's but then I think that statement is the same one as in another textbook where they use another Gödel numbering. But what makes it the same theorem? Well, we know this and we see this, but can we also, in some sense, explicate this? Okay, so yeah, so there's several approaches to try to do that, and in fact I invented two of them. So I'm going to describe one. And so so if you look here, what you see is that so in general we do not have the big disjunction of all the consistency statements here. It's not first order definable. But we could step out of the language and simply look in the richer language at this infinite disjunction, because model theoretically this is really a meaningful statement. And now the interesting discovery is the following. So, look at all models. Look at all models of the theory U. And now we can look. So usually people look at the models as a set, but you could also look at the models as a kind of more structured thing. And so what I want to look at them as a set with morphism between them, of course, so that people do look at them as a more structured thing. But so we want to look at it as a Kripke model. And so now it turns out that you can define an accessibility relation on the Kripke model that doesn't talk about Gödel numberings. There's no conventional choices of that kind at all. So you can define this a big Kripke model, and then simply, as in modal logic, we define necessity and possibility in this big Kripke model. And you can do that in such a way that you get the possibility operator, and it turns out that in every model the possibility of true is equivalent with this big infinite disjunction of all the consistency statements, right? So yeah, so there are a few a few conditions. We need that U has enough coding, and we need that U is axiomatized by a scheme to make this work. I will make some further remarks about that. And so this diamond T, the gray diamond of T, does really depend on the scheme, right? So it's not abstracting away from the axiomatization. So in this sense, here we really just keep the axiomatization, a fixed scheme, and we are abstracting away from all the possible axiommatizations. And so now the second incompleteness theorem takes this form: U over U, the consistency statement is not valid. So that means that there is a model in which you prove the gray box of falsity, in which the gray box of falsity is true. So yeah, remarkably, so if you think about Gödel's theorem, it has to do with arithmetization, etc. And so, but remarkably, the modal setup of the models doesn't use sequentiality. It already works for pair series. So series in which we can, the only thing that is demanded is that you can define non-extensional unordered pairing in the series. And so you, even then you have this. So and this uses an idea that is due to Fedor again, but many details of Fedor's idea were provided by Max Bonnet in a master's project. So interestingly, this also gives us a kind of form of the second incompleteness theorem in a place where the second incompleteness theorem could not go, right? So this, yeah, so it's in some sense a generalization. Okay, so the scope of the result is much larger than you would think, because there's a theorem by Vogt that says that every recursively enumerable pair theory can be axiomatized by a scheme. And so, the possibilities for schematic axiomatization are far larger than you would think. Okay, so is this now really a solution of the problem? Okay, we still have here in this result the dependence on the specific choice of the axiom set, point 1. But of course we do not have it definitely, so every more or less natural for arithmetization of consistency that you could think of is implied by the gray diamond of true, right? So in that sense, it shows that all these sentences that we are naturally considering form a natural theory, right? They're implied by this independent gray diamond. But on the other hand, of course, we do not have a kind of intuitively, informally rigorous argument that everything that would, in some sense, intuitively express a consistency statement does follow from it, right? So every specific example, it's clear. But the general informally rigorous argument isn't there. And so I'm really do suspect that you cannot do this as long as we are interpreting S12. So we really should go go on to look at syntax theories, and then not any syntax theory, but a syntax theory that really prescribes how, for example, we are going to axiomatize, represent provability, etc. Right? So I think there's yeah, so that what I sketch here is not quite going to work. You have to try something else. I do think it's not completely impossible that it is going to succeed, but also it could very well fail. So that's the open-ended end of my talk. So yeah, of course, lots of people are thinking about this kind of thing now, right? So Balthasar Grabmaier is thinking about, so what is a good Gödel numbering? Volker Halbach and Graham Lee are thinking about what is a syntax theory that contains a number of the ingredients that I mentioned, right? So the syntax theory should have a certain richness, but we are still clearly facing many loose ends on the philosophical problem. Maybe also a small confession. For very long I was a complete skeptic with respect to this philosophical problem. I tended to think that all this talk about expressing inconsistency was merely heuristic. So, but yeah, I think boredom is an extremely strong force in philosophy, and so eventually I became bored of my own idea, and so I said to myself, let's give the alternative a chance, and so let's try to really think it through whether we can make sense of this idea of something expressing something. So that's it.
Questions and comments?
So, going back to your third point of the philosophy, I think with the injection of the Notre Dame journal editor. So, could one not see it from another side? The proving the consistencies on the part of the points to prove consistencies, eliminate ideal statements from the proof of real statements. Now, in the Hebrew, the original sense is useless because Hebrew thought that the real statements are decidable and therefore the consistency is because if you have
Yes, precisely. Yes, yes.
now, try to give them a more reasonable meaning,
Yes.
which is anachronistic by saying that the consistency in the usual sense is equivalent to the reflection for universal formulas.
Right.
And if you say that the real statements are universal formulas, then if you could prove the consistency of the strong system, you could also prove all the universal formulas. Of course, it's a counterfactual.
Right, right,
But
right.
under that circumstances, you would have an explanation that you want to have a consistency statement which is implying all other consistency statements.
Yes.
At least.
Yes.
What do you think?
Yeah, so, yeah. So wait a moment, let's try to get a grip on what you're saying. So you think that this line of argument, so Kreisel's idea, really is an argument why we want a consistency statement. Yeah, so of course I applaud that, right? But only the point is, as you see, you cannot have it in first order world. At least not.
Yeah, but then it would be in the sense of Christ very remarkable. I mean, this is a counterfactual statement.
Okay, so the counterfactual says that
If we could prove the consistency in the sense of the traditional sense, then by the reflection principle we really could prove all universal
right,
statements.
yes, of course.
And so in the counterfactual sense one could say only this type of consistency.
Right. So you would want to say that in the end, of course, the point is that you cannot prove all universal statements. Yeah. Yeah. So yeah. Okay. That's a very good point, and so maybe my answer should be so. In the case of my motivate, so I mentioned Detlefsen's program, right? So yeah, my interest is not, of course, not really motivated by the Hilbert program. Yeah, so it's just that historically this question about expressing, so at least Detlefsen's work was really directed at trying to save the Hilbert problem. Yes. No. So yeah. So in that sense, I agree with you, but it's yeah. But for me at least, I think this problem of understanding how this business of the consistency statement works has an interest independent, of course, of the Hilbert stuff. Yes. Okay, good question. I really had to think about how to answer it. Absolutely, yes. A very good question, Fedor. Yeah, I have been thinking about Boolean morphisms, and but then with some extra properties, and yeah, I do think that we could go further. But I also thought about what is next after interpretation. So what is the next good class? But I don't have a. So we of course have forcing. There's lots of things, and in intuitionistic intuitionistic logic we have realizability. There's lots of other things that are not interpretation, right? So for example, the double negation translation doesn't commute with disjunction, and yeah. So there's two answers I can give, right? I do think, but I have to take this business of the Boolean morphisms up again. I do think we can have some kind of generalization, definitely, for some well-defined class. But on the other hand, at some moment, I wrote a very silly paper trying to generalize the notion of interpretation by getting using as little properties as possible, but somehow this didn't give me a natural category. And so, so maybe I should simply throw the question back. Give me a kind of natural category of Schmidt interpretations, and we can think about it. Yeah, so I don't have, in some sense, I don't have a good answer because I have no good class. But I think the Boolean morphisms with some extra properties are probably maybe a fairly natural class, but I have to study it further to really know.
Ladies and gentlemen, our next speaker is Pavel Pudlák from Prague. He will speak about Gödel's second incompleteness theorem and its variations. Please.
First, I would like to thank to the organizers for inviting me here, and I'm glad that such actions are taking place here, because it's important to remember that Kurt Gödel was born here and he's connected with our country. And it's nice that so many people accepted invitations and other people registered to come here. I should say that I was not sure about the concept of this conference So what I prepared is very elementary, and I'm sorry that it may be boring for people who know logic, who are expert in proof theory, but maybe people who are not so familiar with these things may find something interesting in my talk. So here is an overview. The first item is a small joke, of course, that the overview refers to itself. Interestingly, if you look at the table of contents of books, they contain all the parts of the book, but they never mention the table of content. So what I would like to talk about are a few topics. The first one is about sentences that are stronger than consistency, because consistency is not the whole story. There has been a lot of work done on stronger sentences, different sentences, and so on. That there is not enough time to cover everything, so I will focus basically on reflection principles. After this, I mention a little bit about this unfortunate case of Lucas and Penrose trying to use the Gödel theorem to prove something about human mind. And next, I will talk about proofs without of Gödel's second incompleteness theorem, which do not use self-reference, but you may argue that the self-reference is hidden somewhere in the proofs. And finally, I will talk about what the finite incompleteness theorem should be. So I said that my talk will be very elementary, but eventually I ended up including some proofs, but the proofs will be very elementary, so I hope you will be able to follow it. I will consider the probability predicate. So it's a formula, arithmetical formula that formalizes probability in Peano arithmetic. I will start with Peano arithmetic to be more specific, not talking generally about any theory, but later on I will talk about other theories. So let this be the predicate. Then con PA, I'm using slightly different notation than Albert, is the formalization of the fact that PA is consistent. Once we have the probability predicate, then con PA is defined simply as non-probability of some standard contradictory statements, which traditionally is taken to be 0 equals 1, but it can be any other contradictory statement. Sorry, okay. First I consider the iterated consistency statements. So if we have PA plus con PA, so we know that by a second Gödel incompleteness theorem, con PA is not provable in PA. So we can ask about the consistency statements of this theory that is extended by PA, by consistency of PA. And this is clearly stronger than con PA, because here is a short proof, because if it followed, let's consider this sentence, consistency of what I'm claiming is that this sentence is stronger than the consistency. So this is the first example of a sentence that is stronger than pure consistency. So suppose it was derivable from consistency. So we would get that PA proves that consistency implies consistency of PA plus con PA. But this is the same as saying that PA plus consistency of PA, the theory extended by the consistency of PA, proves consistency of PA plus consistency of PA. But now if you look at it, you see that on the left-hand side you have a theory PA plus con PA, and on the right-hand side you have the consistency of this theory. So now we can apply Gödel's incompleteness theorem to this, and you see that this violates the second incompleteness theorem, and therefore this is not possible. So this is an example of a theorem stronger than this. And of course you can iterate it by adding more and more statements like this. So you take this theory and then again consider a consistency of PA plus the consistency of PA plus consistency PA, and so on. Is this clear what this means? Please stop me if you want to explain something. It's not trying to cover a lot of things, so I can stop any time and explain. Now let's express the consistency of PA plus consistency of PA, the consistency of the theory PA plus consistency of PA, in the following way: that it's not provable in PA that PA is not consistent. Okay, so I don't have proof of this. This is an easy exercise. Reflection principles are stronger examples of something that is unprovable, in the sense that we will see that they are even stronger than iterated consistency. What is a reflection principle? The reflection principle for a formula phi is a statement that says that if phi is provable, then phi is true. But how do we say that phi is true? Well, we simply write phi, and phi is provable. We represent by this formula provable in piano phi. We get different sentences taking different phi's. So if phi is just a contradiction, 0 equals to 1, and then it turns out the reflection principle is equivalent to con PA. So we don't get anything stronger, but we get at least as strong as consistency of PA. But there are sentences which do not follow from consistency. So let's take phi to be non-con PA. Then the reflection principle for phi is, by definition, if non-con PA is provable, then it should be true. Or equivalently, if con PA, then it's not provable that non-con PA. But recall by lemma, by previous lemma, that this formula is equivalent to this formula, con PA plus con PA. So so we get that con PA implies con PA plus con PA. But this is something that we actually already considered, because suppose the reflection were provable from, well, it's very similar as we showed that con PA plus con PA is stronger, because suppose that it's derivable from con PA, then we get the following formula: con PA implies con PA implies this, but this is again the same thing as PA plus con PA implies con PA plus con PA. And we get a contradiction with the second incompleteness theorem as in the previous case. So we know that there are instances of reflection principle that are stronger than consistency. But we have different formulas for representing reflection principles for different formulas. There is a way to do something more uniformly, but we cannot completely state the reflection principle for all formulas as a single formula. But if you restrict the complexity of a formula, then we can do it. Because if you consider formulas of certain complexity, sigma k, if you don't know it, doesn't matter much, but it's a restriction to the number of quantifiers used in the definition of the formula. Then we can write a sentence that for every sigma k sentence phi, if phi is provable in PA, then it is true. And this is because we can define a partial truth predicate. We can define a formula that expresses the truth of sigma k formulas uniformly. That if you substitute a Gödel number for the formula, then it says that the formula is true. And it turns out that already sigma 1 uniform reflection principle implies all iterated consistency statements. So here you see that there is a hierarchy of principles that get stronger and stronger. And what people who just learn the second incompleteness theorem learn next is that you can iterate it and equal this progression of theories by adding consistency, and they think that these theories are strong. They are not strong, not very strong. In fact, you can easily formulate a principle that is stronger than all these principles at the same time. And the proof is not much more complicated than what I presented, and this can be, once you have seen the proof before, you can do it yourself. By the way, this sigma 1 reflection principle, that is the where it's not the lowest. The lowest is pi 1, which is equivalent to consistency. But this one is appears in several contexts, and one of these is concrete independent sentences that were discovered first by Paris and Harrington, and this finite-Ramsey version of the finite-Ramsey theorem that they showed to be independent actually is equivalent to sigma 1 reflection for PA. Now, we want to go beyond reflection principles, or if you want to state the reflection principle for all formulas, we cannot do it in the theory itself. We have to step outside and talk in a meta theory, and then in the meta theory we can define what are true arithmetical sentences. And this is not an arithmetical sentence anymore. But for instance, if our meta theory is Zermelo-Fraenkel set theory is usually accepted as the meta theory in most cases, then we can say what is a true arithmetical sentence. We can say that these are the sentences true in the standard model, and then we can state this principle, but it's not an arithmetical sentence. And this sentence implies, of course, all special cases of reflection principles. As I said, you can do it in Zermelo-Fraenkel, And not only that you can express it, but you can also show that that the sentence is true. And the reason is very simple, because you have a model of Brno arithmetic, and this shows that and you can show that all axioms of Brno arithmetic are true in this model, and that the rules of the calculus preserve it. Thermal-Frankel set theory proves that Brno arithmetic is sound. So now let's switch to something that seems unrelated, but we will use what we have defined so far to argue a little bit about these arguments. So the story roughly is that the British logician Lucas published a paper in which he claimed that he showed that human mind is superior to machines, because Gödel theorem is applicable to all formal systems. In particular, if you have a machine, then what it does, it's something that you can describe by a formal system, and then this system is not able to prove its own consistency. But if you look at it, then we see that it's consistent, so we know something more. But this argument is very vague. You see that the argument is of the form which we can see to be true. But a serious scientist should ask himself or herself, how do we see that it's true? So it's not just that it's not enough to say that we see that it's true. And it should be a formal argument, because if you want to use a mathematical theorem to prove something, you should argue formally. You cannot just refer to some vague concepts. If you refer to vague concepts, you don't need to use a mathematical theorem to prove anything. But I'm afraid that if you ask them, they would just say, because we are different from machines, and this is, of course, a circular argument. So what is really wrong with these arguments? So these arguments were never accepted by logicians, and they were criticized. But usually they were criticized by arguing that human mind is not a formal system, so you cannot apply Gödel theorem to it, and therefore you cannot use this argument. Or, of course, we also know that would we know if we would write down everything that we believe in, then this will be certainly a contradictory system. So it's like when Gödel went to an exam about the U.S. Constitution in order to get U.S. citizenship. So the first thing he said that the Constitution is contradictory. So things are contradictory, but this is not the point. The point is that we are talking about mathematical statements. So we can ask what do we believe is true in mathematics, and this is something that is not so vague. In fact, if you take an average mathematician, then you can upper bound or approximate what his or her beliefs, what are true mathematical statements by Thermal-Frankel theory plus an accessible cardinal. And the reason is that they work in Thermal-Frankel theory, so they accept these axioms, but they also think that this is a true theory in a sense, or at least it proves only true arithmetical sentences if we are not sure about sentences of set theory, like the continuum hypothesis or other. So if you add an inaccessible cardinal, then you get arithmetical soundness of thermal Frankel, and this definitely covers what people believe is true. So what is wrong is something different. But what is wrong is a very simple thing. These are simple logical errors. So what they present are not logical deduction, but they are simply logically wrong arguments. And the problem, of course, is that if you argue with those people, and I tried to argue with Penrose, but he was very arrogant, so I gave up very soon. They change these arguments many times. So they start with an argument that using an assumption and then introduce another assumption, and when you point to the error, then they come up with another presentation of the proof which has a different error. But there is it's like if somebody who committed a crime defends himself at the court, then he presents different stories, and if one story becomes inconsistent, then he presents a different story. I want to mention just one common error, which is the failure to distinguish between consistency and soundness. So we know that consistency is much weaker than soundness. So if you confuse it, then of course you may derive very different things. So let's take as an example a quotation from Dukas. What he says, I interpret that you start with some system, and then you add consistency statements, as we did with piano arithmetic. So you start with piano arithmetic, for instance, and you add consistency, and then you add the consistency of the system consisting of piano arithmetic plus consistency, and you iterate this. And he wondered that how is it possible that all these infinite set of axioms, we still see that they are consistent, while the system itself is not able to see this. So this is how I interpret what he says. But the point is that what he says, the rational being thinks that or believes that it is consistent because it assumes that S, it does not only assume that S is consistent, but it assumes that S is sound. And we know that already a very weak form of soundness, that is the sigma 1 reflection principle for the system, implies all these consistency statements. So there is then nothing surprising on what we see, that if you assume that the theory is sound, then you can add arbitrary many consistency statements in this way. But what about Gödel? What did he think about it? Actually, Gödel thought that it is possible, and maybe even believed that human mind is superior to machines. But contrary to Lucas and Penrose, he was aware of the fact that you cannot derive it from his incompleteness theorem. This is something that is known as Gödel's dichotomy. Maybe this quotation is not the best one, and I'm sorry that I did not quote it completely, but this whole sentence is a little bit convoluted, so people just prefer to quote it with things omitted. And you see this is a disjunction. Either human mind infinitely surpasses the power of any final machine, or there exists absolutely unsolvable Diophantine equation. Let's now not discuss what absolutely unsolvable. So let's interpret it in the way that there is a human being, and what it can solve is what we are now discussing. So for this particular person, if at some point he or she can always solve only a certain number of problems, because if we consider humanity evolving in time, then maybe people will find new axioms and so on. So he stated this only as a disjunction, the possibility, either this or this. But how can Lucas and Penrose believe that Gödel himself overlooked such a very simple argument as they presented that would eliminate one part of this disjunction, that only the first one would remain? So this is definitely ridiculous. So this was very briefly describing this, and I try to say more about it in my book on logical foundations. This book is not about it, but it's mentioned there in more detail. Okay, let's get to what I promised: proof without self-reference. One of the presumptions about Gödel theorem or popular misinterpretation of Gödel theorems is that these are just the basis is self-reference. So Gödel theorem equals self-reference. Of course, self-reference, self-referential sentences are important. They are a basic tool to prove the theorem, but they are just a tool. So the essence of Gödel theorem is not in self-reference. In fact, what the Gödel theorem says is that you cannot prove the consistency not only of the theory but also stronger theories. So you don't refer to stronger theories. Okay, so here's an example of an argument that at least not explicitly uses self-reference. So this will be a bit more technical, but not very difficult. Consider a universal Turing machine. This is something that you know very well, but just let's fix some notation. This is a machine that can simulate any other machine. It can simulate in the sense that if you want to simulate the machine, you take some string, and then this will be like a program for the simulated machine, and then you extend the string by inputs, and the machine will output what the machine M will do on X. Given this machine, we define the Kolmogorov complexity of a binary string as the least number, such that there is a string of length n, such that the machine on string X produces Y. This is called also a descriptive complexity. So it's the, loosely speaking, it means that Kolmogorov complexity is the shortest description of the string. So the question is how short a description you can have for a string. So definitely you can describe the string by writing it down, but if the string has some regularities, you can use this to describe the string more formally. Basic thing about it is that there are strings that whose Kolmogorov complexity is at least the length of the string, because you just use a simple counting argument. You cannot encode all 2 to the n plus 1 minus 1 strings by strings of length shorter than n. The following theorem says that if you have a consistent, recursively axiomatized theory T, then there exists a constant such that the theory is not able to prove for any concrete string that its Kolmogorov complexity is larger than this constant. So this looks a bit paradoxical because we know that that there are strings that have Kolmogorov complexity at least as big as their length, and this is a very elementary proof. So every theory can prove this. But the point is that if you take a specific, concrete string, then the theory is not able to prove this. So this is a very non-constructive concept that you can prove only for finitely many strings that they have large Kolmogorov complexity. And here is why. So if you take K sufficiently large, namely sufficiently larger than the description of theory T, and then suppose that T would prove for a string A that its Kolmogorov complexity is larger than K, then we actually can describe the string by a relatively short program. Namely, we can systematically generate all proofs in the theory T and then stop and output A if we find a proof that Kolmogorov complexity of A is larger than K. So so we don't know A, but we will just run the program, and because we know that there is a string that has Kolmogorov complexity larger than K, if we try all proofs, then we will eventually hit one string that for which the theory proves this. But this program is described purely in terms of the theory T, plus some other lines in the proof. So if K is sufficiently larger than the description of theory T, we would get a description of A, definition of A, only of this length. So basically, you can think of Kolmogorov complexity of this A to be Kolmogorov to be the at most encoding of T plus say logarithm of K. So this contradiction shows that for K sufficiently large, it's not possible that T would prove that the string is Kolmogorov complex. So this is, say, the first incompleteness theorem, that we can show that something is unprovable in T, namely many unprovable sentences for all sufficiently long strings with sufficiently large Kolmogorov complexity, but it's not. It's very non-constructive because we don't know which these strings are. And I said it's not based on self-reference, but you can view it as something based on Berry's paradox. Let's just know that these numbers are monotonic with respect to theories, that if you take a larger theory, then this inequality should go in the other direction. That if S is stronger than T, then this should be smaller, because you have more proofs. And from the proof we see that this number kt is about Kolmogorov complexity of the theory plus a constant, but it may be much smaller because you may have a different representation of the theory, or you may have a stronger theory which has shorter representation. So this is just an upper bound. And it's hopeless to, of course, to compute this k. We can only upper bound it. Now, what's more interesting is the proof of the second incompleteness theorem based on Kolmogorov complexity. So I will try to present it. This is a result of Kritschmann and Raas from the paper called The Surprise Examination Paradox and the Second Incompleteness Theorem. So let's call strings whose Kolmogorov complexity is at least n Kolmogorov random. There is a good reason to call them Kolmogorov random, because they definitely cannot have some very regular structure, because if they had a regular structure, then you could use it to define them by shorter strings. Let R sub n be the number of Kolmogorov random strings of length n. We need the following lemma. If T is a consistent recursively axiomatized theory that contains Q, and if n is sufficiently larger than this constant kt, kt is this constant that bounds where the theory is able to prove Kolmogorov randomness of any string. So then, if T proves that there are at least m Kolmogorov random strings, then m is definitely not the largest number. It's less than the actual number of Kolmogorov random strings. So for n sufficiently larger, this what the theory can prove is always smaller than. And here is the proof of the lemma. First, we know that for every Kolmogorov non-random string, T can prove that the string is Kolmogorov non-random. What does it mean to be non-random? It means that there is a program, that there is a string, or you can view it as a program to output string A, whose length is less than the length of A. If we know that there is such a program, then we can systematically, well, we don't have to search systematically. We just take this program and run this program and take the run of this program. And this is something that we can represent in the theory. So the theory, if it is, in fact, it suffices that it contains Robinson arithmetic, is able to see that this program produces the string A, and the program is less than the length of A. So the theory is able to prove that the string is non-random. And we can do it for all Kolmogorov non-random strings. So the theory can actually prove an upper bound on Rn. So the theory cannot prove that m is larger than Rn, because then it would be inconsistent. So the only option is that m would be equal to Rn. If m is equal to Rn, and we know that it proves that all strings that there are 2 to the n minus. This number is maybe not not good. Well, let's take it plus minus 1. That are non-random, and prove that there are at least m, which is now Rn, Kolmogorov random strings. Then it actually proves that X is Kolmogorov non-random for every k that is non-random, because for non-random it can prove that they are non-random, and it knows that these are all strings that are non-random, so the rest must be random. So if we take any Kolmogorov random string, then T would prove that it is Kolmogorov random. But we have taken n larger than kt, so it's not possible that it proves. So we proved this lemma that whenever T proves that there are m Kolmogorov random strings, then m is less than Rn. So now we can do the proof of the second incompleteness theorem. The proof is just by formalizing the lemma in theory T. So what does the lemma say? The lemma says that if theory is consistent, then there are more Kolmogorov random strings than it can prove. But if T proved its own consistency, then it would actually prove that there are more Kolmogorov random strings than it can prove. And this would be a contradiction, because on the one hand it would say that there are m Kolmogorov strings, and then it would say that there are more. So so this is not possible. Okay, so this is the whole proof, and I have just a couple of remarks concerning this. What the proof also does is that if T is consistent and n is larger than kt, then the sentence that there are exactly R and Kolmogorov random strings is not provable in T. So Rn is some concrete number, of course impossible to compute, but this is a sentence that is meaningful and unprovable. And this suggests the question, how many Kolmogorov random strings of length are there actually? By the counting argument, we know that there is at least one. So we observed at the beginning that that there are Kolmogorov random strings, so there must be at least one. But if there is at least one, then there should be at least two. Because if there was only one, then we could search for, we would take this one, and then we would be able to search all the other strings, and we would get an algorithm to actually define the string. So more precisely, what we would do, we would run in parallel ux on all strings less than xn, and after all of them except for one, after you would stop on all of them except for one, we would know that these are all Kolmogorov non-random strings. So the remaining one should be Kolmogorov random. But again, we have a program that only uses very few instructions, namely the complexity would basically be logarithm of n. We need to describe n, and then plus a few more lines of the program. So we get at least 2. And by the same argument, we get at least 3, and so on. So at first it looks like that we could run into contradiction, but the point is that as the number increases, then the numbers becomes more complex. So at some point already the number of strings for which we prove that they are Kolmogorov random would be so complex that we cannot use this argument anymore. And this implies that actually the number of Kolmogorov random strings of length n must be almost Kolmogorov random, must be close to n. Okay, so this is about proof of second Gödel theorem not based on self-reference, but of course you can argue that there was a lot of self-reference in it. It was just hidden. Now, I'm afraid everybody fell asleep by now, so I'm not sure I should continue. So this room is very nice, and it has very comfortable seats, but if you combine comfortable seats with darkness and with a boring lecture, then everybody falls asleep. So, but let me say just a few things more. So there is this program of finitism that people say that it's not important what we can prove about infinite objects, it's important what we can prove about finite. And or another thing is that one can say, okay, we don't care whether our theories are consistent or not, but we only care whether this if there is a contradiction, that it is not small. And there is a good reason for that, because Parik showed that if a contradiction is very, very large, then we can still use the theory and prove true sentences. We don't get sentences that are not true. So therefore, it's natural to ask what is the length of proof that there is no contradiction of length n in T. So can we prove at least, we cannot prove that theory is not consistent in itself. We cannot prove by finite means that Zermelo-Frankel is consistent, but maybe we can prove that it's consistent up to what people will ever write proofs, and then it would be something. So how difficult is this? So let's write conti n as an arithmetical sentence expressing that T is that there is no proof of contradiction of length n. Now we will represent n as a term of length logarithm of n by using binary representation and addition and constant. Let's denote by norm of phi the length of the shortest proof in T. So con Tn just says that the shortest proof of contradiction of T is in T is larger than n. And con T, the consistency of the theorem just means that there is no proof, so it's that for all n we know that the contradiction must be larger. It's surprising that people did not notice it sooner, because this is a very natural question, and it's not difficult to prove it that actually this statement doesn't have short proof in T. So the shortest proof of the consistency of T up to n, in theory T is n, not quite n, but n to some epsilon. One can actually show that the lower bound which is very close to n. So this, by the way, implies Gödel. One can show that the proof of because what the Gödel theorem says is that it's consistent to add that to the theory to add a statement that the theory is inconsistent. So we can say that there is a number, Gödel number of proof of inconsistency in T, and we still have the consistent theory. Using this, one can show that in many cases we can actually argue that this proof of inconsistency may be small in some sense. So I just sketched the idea of this lower bound. This is for people who have some experience with who teach, say, logic, so they know how the second Gödel incompleteness is proved in the standard way. So the standard proof of second incompleteness theorem is that you define the sentence that says that it is unprovable, and prove that the sentence, if T is consistent, then then theory doesn't prove this sentence. This is a very simple argument by as in the liar paradox. And then the next step is to formalize this in T, which means that formally that gamma is not provable means that if T is consistent, then gamma is not provable. So I am referring to this. But by definition, not provable is equivalent to gamma. So this means that T proves that if T is consistent, then gamma. But we've shown that gamma is unprovable, so must be con T also not provable. And now the lower bound on finite consistency is just almost isomorphic, except that we use some bounds. It's so to say. Now I missed the right word. So instead of saying that the sentence is unprovable, defining the sentence that says that it is unprovable, we just define that the sentence says that it doesn't have proof of length shorter or equal than n. Prove that if T is consistent, then the sentence actually doesn't have such a short proof. And then we formalize and show that if theory is consistent up to not just n, but a little bit further, then this is indeed true. And in this way, we get that consistency of T up to something a little bit larger than n implies this sentence, and therefore we get a lower bound on this. Now, the question is, what is whether this is the finite Gödel theorem. When Friedman wrote his preprint, he conjectured that actually this bound is not good enough, and maybe this was the reason why he did not publish it, because this should grow exponentially, and this is false. But it's still possible that this grows exponentially if we take a stronger theory. And the standard way to take a stronger theory is to take T plus consistency of T. And therefore, the following conjecture is plausible, that if we add the consistency to theory T, then this must grow exponentially. But the safest way to state this conjecture is that it grows exponentially for a theory S that is sufficiently stronger than T. Now you cannot play too much with it because one would think that if you just make a little bit stronger the theory, then you already have exponential growth. But Pavel Hrubesch observed that actually one can construct the pi1 sentence such that which is not provable in the theory, but if you add it to the theory, then this is still polynomial bounded. But we don't have means to prove anything like that, because these conjectures imply P unequal and P in fact more. And we don't have any idea how to prove P unequal and P, and the less statements like this. Thank you, and I should finish with some picture of Gödel. Okay. Mm-hmm.
But basically, so this of course the sketches, it's again it's more or less the same, but with much more details.
Mm-hmm.
But could you do it nicely? It's possible to do something like maybe so basically yes, I think
You mean the nice proof of this finite Friedman's theorem? And what is what you don't like on it? I think it's very. Oh, you mean you mean in model logic? I see. Okay. Mm-hmm. I see. Okay, I got your question. So as I understand you, so we have these proofs of Gödel theorem in modal logic. We just take Loeb's axioms and we prove Gödel theorem. So we would need some modalities that would be with numerical parameters. And I don't know, so you guys probably know more about such things, or maybe people from fuzzy logic, or I don't know. But I don't know such systems that. I am. Does it work? views correspond very much to Stephen Hawking's. I don't know if you've read a recent book by Stephen Hawking where he has a chapter about it. So he believes that it's just a matter of time when artificial intelligence will take over, and that we actually have to be worried a little bit about it. So I believe that that this is going to happen. And if you see what happened in past 10 years, programs, the chess programs beat people very easily. Now we have programs for Go, and we have a program that learned playing chess just by himself, and so these things progress very much. And of course, the question is consciousness, whether there will be a machine that will be conscious, and this is for a longer discussion. But I believe this will also happen. Right.
Ladies and gentlemen, the block of contributed lectures is starting. Our first speaker is Professor Bogdan Hejna from Prague. So it's my pleasure to start to begin with this talk, which is devoted to the relation of Gödel theorems to category theorems.
At first, I thank the organizers for invitation me here. And now my paper. This paper, Common Logical Meaning of Gödel and Category Theorems, is based on the leading idea of logical positivism or physicalism. Yes. The founders of which were Karnap and Dr. von Werath in Vienna Circle in years 1931-1935. This idea said that any scientifically meaningful statement is expressible in physical terms about a movement in the observed space and time, or if the statement is not expressible this way, it is meaningful scientifically when it is convertible to a statement about a language, otherwise it is of no scientific meaning. This idea inspired my considerations about mutual relations among structures and languages of thermodynamics, which is dealing with energy transformation. Especially it is now the heat energy transformation in Carnot machine, which is Carnot cycle. Information theory dealing with message and information transfer processes, which are running in Shannon transfer chain with its transfer channel, and computing theory and computing inference processes, which are running in the Turing machine with its finite state control unit. I have constructed a common point of view based on information theory and adiabatic theory, which is dealing with state developments in so-called adiabatic system. Processes in all these structures, Turing machine, Shannon transfer chain, and Carnot machine, run in the finite physical world and follow its laws. I will model them by the state trajectories within the heat-isolated, also called adiabatic system, for which is valid category common formulation of the second principle of thermodynamics. In the arbitrary vicinity of every state of the state space, QL, of the adiabatic system L, exist states not reachable from the starting states adiabatically, or the states which are not reachable by the system at all. I am trying to show that analog is valid for the consistency of the Peano arithmetic theory, and this analog is expressed by Gödel incompleteness theorems. The first theorem says that for the Peano arithmetic theory exists to claim that either this claim and its negation is not provable within the system P, especially within the Plano arithmetic theory, which is constructed within the system P by the means of the system TPA, by the means of the Plano arithmetic theory. The second theorem says that the claim saying the theory, the Plano arithmetic theory is consistent, is not provable by its means, by itself. This picture shows the adiabatic trajectories within the certain system, adiabatic system L with its space QL, and is showing that these adiabatic trajectories of these various types are missing certain states within the system, and also it shows that certain states which are the members of the hierarchically higher adiabatic system are also not achievable. This figure also shows that this adiabatic system is constructible only at the detriment of the energy of the hierarchically higher system L dash with its state space Q L dash until the system which is constructed is enclosed. I am dealing with Plano arithmetic inference within the system P, which is equipped with these Plano axioms and inference rules, generalization and modus ponens, where modus ponens is saying that when B is inferable and B implies C is inferable, then immediate consequence C of B is also inferable. The system P is the set of always valid arithmetic formulas, not only of the Plano arithmetic type. The arithmeticity of the system P will be modeled by adiabacity of the adiabatic system L, and consistent Plano arithmetic inference within the system P will be modeled by moving along trajectories, along adiabatic trajectories within the given state space. The states on the adiabatic trajectories will then be models of the consistently inferred or inferable formulas. Any adiabatic trajectory is defined by its complement within the given state space. This complement is also the definition space of this trajectory, and this complement is also not reachable within the adiabatic trajectory itself. For the trajectory, adiabatic trajectory could prove by itself its own adiabatic property. It should have to contain its own definition as its own status. This adiabatic trajectory then could be autoreferential or autoconstructive, and as the adiabatic one, it should be able to construct, but not adiabatically, the adiabatic spaces QL and its own component QL minus LQL, and define by this way itself as its own status. In fact, such an attempt is the Klein-Potter building from the original's inside. The original's outer surface defines its inner surface, which is now the model of the adiabatic trajectory, and its outer surface is the model of its complement. Within the inner surface of the original bottle, now we want to prove its internality by reaching its outer surface with an inner curve. Within the Klein-Potter, constructible only by the outer manipulation with the original bottle, one curve is possible, but this crossing now contradictorily against the original bottle, its inner and outer space simultaneously. Only we, as the outer constructors of the original bottle, know its own properties, and only we, as the outer constructors of the system L or inference system B, know their properties, adiabacity or consistency. As I said, the adiabatic trajectory does not contain itself as the object of its own, it does not know its own properties, and it itself, by its means, does not reveal it. Information transfer channel. It is the tripartite structure X, epsilon, Y, where X is the stochastic quantity, so-called transmitter of input messages, Y is the receiver of output messages, and on their selected spaces these probability distributions are defined, and by these probability distributions these Shannon entropies are defined. Also, these real are these entropies. Also, we can define the loss and noise entropy, noise entropy, by the same way, but using the simultaneous and conditional probabilities. For the so-called transit formation, the xy or dyx are on the same value, and they are defined by these differences: input entropy minus loss entropy, output entropy minus noise entropy. The general equation is valid, saying that this difference is equal to this difference. The tripartite structure x, k, epsilon is the Shannon transfer chain. Carnot machine. Carnot machine is also the tripartite structure consistent with this ether A with temperature Tw, cooler B with the temperature T0, and the working medium L which is going through this Carnot cycle. Now it is considered as reversible by producing the zero friction or noise heat. It is the ideal medium. At this phase, it is the Bezoar expansion. The heat delta QW is delivered to the medium, and this piece of work is done, is produced, and this adiabatic, not adiabatic, isothermic compression is pumping out from the medium L the loss heat delta Q0 at the temperature T0 of the core. This adiabatic expansion is cooling the medium, and this adiabatic compression encloses the cycle. The resulting output work of the reversible Carnot cycle is then given by this algebraic sum of all works which are produced or constructed along the cycle, which means that it is equal to the difference between the input heat and the loss heat delta Q0. And Kelvin's theorem of the second principle of thermodynamics for the reversible case is valid, saying that the algebraic sum of all heats along this cycle reduced by the relevant temperatures is equal to 0. Thomson-Planck formulation of the second principle of thermodynamics says that it is impossible to construct a heat cycle transforming all heat delivered to the medium L, going through this cycle into the equivalent amount of work or amount of the work delta A, mechanical work delta A. For this, the first principle of thermodynamics is valid, saying that the transformation efficiency must be less than 1. Recording, transmitting, computing an information amount delta I at the temperature theta requires certain energy W, which energy is greater or weaker than this expression, where K is the Boltzmann constant, theta is temperature, delta I is the worked out piece of information. Now this delta W will be our input delta QW. For this case, the changes of entropies along the medium L is the Carnot cycle O are now considered informationally as entropies of a certain channel K, but defined thermodynamically. Input entropy is given by the input heat reduced by this temperature. Hy is given by the work delta I, reduced also by the temperature of the heater, and we see that this Hy is under this condition given by the ideal case of the medium L is equal to the worked out pieces of information. Channel equation is valid on the channel K, and now with this thermodynamic substitutions of these values, we are deriving very easily that this loss entropy is given by the loss heat. This figure shows the flow of entropy during the run of the Carnot cycle within the whole Carnot machine. Important is the change delta SAB of the entropy of the system A and B, heater and cooler, within the change delta SC of the global entropy SC of the whole environment in which the Carnot cycle is running, and is equal to the algebraic sum of these members. It is given by the heat delta Q0, but reduced by the temperature TW here, and reduced by the temperature T0 just here. We see that this change of entropy within the system NAP is then defining this output information Hy. The change delta SL, which is the change of entropy SL within the working medium L, is then following the Kelvin's formulation of the second principle of turbulence equal to 0, and thus the resultant change delta SC of the global entropy SC of the whole Carnot machine and the output delta I are bound by this equality. Delta SC is now equal, or this all is defining through by this Boltzmann constant output information amount or entropy, better said average amount HY. This case is in convenience with the Brillouin extended form of the second principle of thermodynamics, now with this equal sign. In this extended formulation, what is new is this information member. Now we have created analogy or certain type of equivalence among these structures. The reversible Carnot cycle O is considerable as thermodynamic model for the information transfer tau without noise through the channel K. The medium L going through this cycle O is the model for the channel K with its transfer process tau, and the whole Carnot machine is then the model of this Shannon transfer chain. Turing machine is also the tripartite structure consisting with input and output onto input-output tape, and this control unit with this retry head. This control unit is driven by program eta vector, and each instruction of this eta vector is containing these values or variables. SI is the status of Turing machine's control unit in the actual step P of the activity of Turing machine. XK is the input symbol on the input-output tape in the step P. YL is the output symbol which is overwriting XK in the step P. And SJ is the defined status of the control unit of the Turing machine for the next step P plus 1 of the activity of the machine. D is the definition of retry head moving in the left-right direction along the input-output tape after YL has been written instead of the input XK in the step P. With the I/O input-output transformations XK to YL, the Turing machine's control unit states transitions are performed, defining this way the regular grammar of the language of the control unit. This regular grammar is using these special terminal symbols. Also, we can consider the regular language for the whole Turing machine, which is the language of the configurations, set of configurations, which the Turing machine has gone through so far. Here is this special terminal symbol, where sigma vector is the part of the input-output tape, not having not been processed so far, as I is the inner status of the control unit, and rho vector is the part of the input-output tape which is to be processed. The right Turing machine's program, eta vector, generates the resultative Turing machine's configuration sequence, and similar is to be valid for information transfer act and the Shannon transfer chains configuration. Now the inferred claim AI is the last member of the input vector X vector, and this AI's Peano arithmetic inference by modus ponens is realized as the wise information transfer tau in the channel K. A0 is now the axiom, A1, A2, and so on to AI-1 are the formulas which have been inferred so far from this axiom A0, and AI is the formula which is to be inferred. Entropies for this AI's arithmetic inference from this given X vector realized by the information transfer from this X vector to the channel K in its status X under the condition Y vector, which is everything what was stated and inferred so far, are based on the given numbers of these chains, and the output information entropy is also given by the difference between this Hx and this Hx under condition y, where now this Hx under condition y is the entropy of the interstate of the modeling channel. This figure shows the similarity between the inference, the arithmetic inference, and the information transfer. At first, we are setting the channel K to its starting state of state 0, which is the equivalent of choosing the axial for our further inference. After the A0 is set, on the input of the channel, the vector A0 and 1 is put, when AI is the formula which is to be inferred. When this formula A1 is inferable, it is also transferable so the channel K as this y, and we have the positive information entropy on the output. At this moment, we are setting the channel K to the next status, which is the chain of axial and formula which has been inferred so far, and on the input we are putting the chain A0, A1, A2. When A2, when it is inferable, it is also transferable through the channel K as this output Y with the same result and so on. Carnot machine is also described as an automaton with the regular grammar and language L, which is the set of pieces of word delta AI which are produced during one run of any individual run cycle out, I, and for any cycle. These entropies are defined in the same way as it was before. Now we have created, let us say, congruence, equivalence, analogy among step of the Turing machines of the control unit, transfer act in channel K, and the cycle run in the medium L, the Carnot cycle. So the Carnot arithmetic inference is now modelable by message transfer, which is expressible in terms of heat transformation process. Turing machine states are equivalents of states of channel K, which are considerable as equivalents of the states of the medium L, and we have created now this, let us say, equivalence among the Turing machine, Shannon tensor chain, and Carnot machine. The processes of the Turing machine, Shannon tensor chain, and Carnot machine are now considered in isolated systems. As for the energies which are coding the values of variables x, y, and x under condition y. Yes. The state changes in the adiabatic system along the adiabatic trajectories are also describable by the relevant regular grammars. Well, these pieces of work are the words which are produced or consumpted during these changes. The thermodynamic model for the consistent plano arithmetic inference with axiom and formulas having been inferred is created by the Carnot machine's activity, which is modeling both the Turing machine and the Shannon transfer chain. The Turing machines and Shannon transfer chains configuration are then modeled by the states of the system, of this adiabatic system L, with this modeling Carnot machines inside, the configuration of which in fact are created these states. The initial imbalance of the system L starts the sequence along these adiabatic trajectories L to L, and is given by temperature difference on the Turing machine, existence of the input message of channel K, and the change existence on the Turing machine. These adiabatic trajectories now represent the norm of the consistency of the plano arithmetic inference, and they are expressible now in terms of information transfer and heat energy transformation processes. On the interacted channel K is valid that the input entropy is equal to this loss entropy, which is the entropy of the inner state of the channel. For this case, the transformation must be equal to 0, and the input hx is now without any relation to hy. This value of hy under condition x for the ideal case are considered at 0 value. Now, with insisting on the information transfer through this interrupted channel K, then contradictorily we won't build this channel transfer chain with a reversible Carnot machine, direct Carnot machine, where is to be valid that input heat is equal to the loss heat. Both are at the value delta Q, while we won't have this difference of temperatures of the heat time cooler, which means that we won't have this transformation entropy greater than 0. It is not possible. In fact, we are measuring delta Q against delta Q at the same temperature. Result must be 0. Nevertheless, our wish to have the information transfer this positive value on output through such interrupted channel K formulates the contradiction or violation of the second principle of thermodynamics. This type of our thinking requires have the change of entropy within the medium L at the negative value, and the same is valid for the change of the global entropy of the environment in which we are thinking this way when we are considering this environment be closed. Our measuring is now with the 0 distance between the measuring object, which is the channel K on medium L, and the measured object, which is the input x or heater A, and the equality, this equality hx is equal to hx under condition y, says that any channel can transfer its own state or observe, copy, or measure itself. Now, the last claim, its asterisk, within this input chain is presumably not inferable and as such interrupts the channel K. It is the situation when A0, A1, and so on to AI-1 are axiom A0 and formulas inferred from this axiom, and A with asterisk is not inferable. At this moment, it has no sense without within the Brno arithmetic theory. The occurrence of this A with asterisk here is a certain type of miracle which bears the infinite piece of information amount, and in language of entropies it must be at the 0 value. This means that this 0 value or nothing is transferred to the output. When the same situation will arise, when we are concatenating this A asterisk with anything else, which everything is the same as we are putting the input state of the channel on its the inner state of the channel as its input to infinity. Hx now expresses the structure Hx under condition y of the channel on toric machines. Hy and Hx are not in any relation. Repeating this autoreference attempt causes this infinite cycle, and we see that this equality is the halting problem core. Our better rating of a not zero and positive output now formulates the methodological error, but identifiable also by this type of consideration. We can say that this whole chain is a certain type of nonsense not possible within the Brno arithmetic theory. So the Hx is now equal to 0, while the entropy of the inner status is greater than 0. Then the resulting difference is less than 0, which means that the change of thermodynamic entropy of the system in which we are thinking this way must be at the negative value. In fact, we have 0, 0, that's all. Now, let x be the sequence of formula valid in the Brno arithmetic theory, and y is a claim with a general syntax only, not respecting the semantic limitation imposed on the arithmetic system and Brno arithmetic theory as well. Now, we define the valid relation Qx capital Y, saying that x from this circuit space x, which is the Brno arithmetic theory itself, is not in the Brno arithmetic inference relation to the values y of this capital Y, and the selective of this capital, selective space of this capital Y is given by this difference. This set is the set of all considered adiabatic trajectories, and this set is the thermonate model for our arithmetic theory. And this closure is the closure constructed on the set of the state spaces of the all members of hierarchy of our adiabatic system from the beginning of the lecture. Qx capital Y must be true, which is clear from this outside construction, and supposedly for it is true for any member small y of this capital Y, and also for the fact that for its construction are the symbols of the general syntax which is used for arithmetic construction, but now without limitations, needed limitation, we can consider, but mistakenly, that it is provable by the means of the system P, which means by the Peano arithmetic theory. For the Qx capital Y is in fact constructed outside of the Peano arithmetic theory, and above all it is constructed outside the whole system P, we can consider it as the member Y of the selective space of this capital Y. So we can produce the substitution Y, small y, by this Qx capital Y, which resulting in the claim Y of Y, which is the claim saying that it is not possible from the given x of the Peano arithmetic theory to achieve the claim which is saying that it is not possible to achieve the selective space of Y. In fact, existence of this capital Y or of the small y's from the selective space are stating the Peano arithmetic property. With this substitution, we are generating this sequence of autoreference claims. In fact, any member of this sequence has nothing else than Qxy or Qx capital Y. Nevertheless, these chains are representing, any of these chains is a certain representation of the same Y, and we can produce the infinite expansion of these Y's. Y, and so on, till Aleph 0 value. But any of these members of these expansions are also substitutable instead of one, just here for instance, and we see that we need have the selective space of this Y and this Aleph 1 cardinality. So we see that Qx small y is not constructible within the system P and not provable by the Peano arithmetic theory, but its validity follows from the second principle of thermodynamics in our consideration. Similarly, as the adiabacity of any adiabatic trajectory, its adiabaticity is not provable within the adiabatic system L, within its own adiabatic system L. The same is valid for the claim Qxy. It is not provable within the system P, and it is true. It is true. Similarly, the second principle of thermodynamics is true. By the quantification of this Qx capital Y1x, we are gaining the claim P about the capital Y, saying no x from the Peano arithmetic theory is in the Peano arithmetic inference relation to the variable y. With the substitution this P instead of y, we are gaining the P of P, similar as it was here y of y, and it produces this infinite expansion of the claim Qx, Qxy, and so on, with the same result as before. As before, the second principle of thermodynamics, by this principle of thermodynamics and in our analogy of equivalence, we can say that the set of the adiabatic trajectory cannot be proved as adiabatic within its own adiabatic space or system. The consistent Peano arithmetic theory is constructed by ourselves from its Prosím? Ještě chvíličku. And does not contain the axiom of its consistency and as its own object. They attempt to prove that the arithmetic consistency defies the autoreference or halting problem. Now, I will jump other. We can explain semantically the sets of Gödel theorems for every recursive and consistent class of formulae, and outside this set there exists the true claim R with a free variable V that neither its generation and the negation of its generation belongs to the set of consequences. And also, if kappa is an arbitrary recursive and consistent class of formulae, then any claim Y saying that kappa is consistent must be constructed outside this set. In fact, the true of this Widerspruchsfreiheit with kappa is equivalent to the fact of validity of second principle of thermodynamics. Our QXP is nothing else than this Gödel number 17 gen R, which is representing the undecidable Gödel formula. It is not provable within the system P. Similarly, as the adiabacity of this state space is not provable within its own system. Now, under the consistency of the system P, it is not possible to derive such a claim that is stating this consistency is a position. This claim is constructed pure formally syntactically outside the system P. In fact, the eye cannot look at and into itself. It is the same as for the adiabatic system. Any mixing of various observation levels leads to the paradoxes and is to be excluded. For instance, that's me, or the picture of me. Here is the mirror picture of me. And now I have ordered the mirror picture to step out from the mirror and step in front of me, having our right hand or left. The result is chaos, equilibrium, infinite cycle, paradox, resulting from mixing of various observation levels. That's all, thank you.
Professor Ashot Pagasaryan, who will talk on automatic theorem provers for minimal logic.
Okay, thank you very much. I will talk about a neural network-based automatic theorem prover for minimal logic. This is joint work with my supervisor, Hovannes Polybekian, and let's go on. First, let's talk about minimal logic, and let's consider the differences between classical logic and non-classical logic, especially intuitionistic and minimal logics. Here you can see that in classical logic, both of rules, the law of contradiction and principle of excluded middle, are provable, but in intuitionistic logic, the principle of excluded middle is not provable, and in minimal logic, nor the law of contradiction, neither the principle of excluded middle are provable. And because of that, you can see here that intuitionistic logic is a fragment of classical logic, and minimal logic in its turn is a part of intuitionistic logic, and because it is a constructive logic, it's in scope of our interests, and with the help of these systems we can apply these systems in such problems like program synthesis, system verification, and so on. Let's look at the problems of Kensen's style sequence system G1. There are three main problems. The first problem is that there may be proofs which are permutations of each other, and they can represent the same natural deduction. The second one is that there may be they may occur loops, and our proofs can be non-terminating. This means that during constructing a proof tree, we can come across a loops, and our proof will be non-terminating. And the third one is that we have a selection of rules. We have the same for the same point of proof tree. We can have different rules, and we can have to choose some rule to apply. And we try to construct systems with the help of which we will try to solve these three problems. So first, let's look at system GM. These are the rules of our system. And here you can see that this is our sequence, and the left part of this arrow we will call a context, and the right part we will call a goal of this formula. Here you can see that we have a specific kind of sequence. This one here, we have a formula in the arrow. This will we call stope, and we will use stopes for our system for constructing our proofs. Here we have different type of rules, right rules, which means that in the right part of our sequence we have an, in this case, implication. And we have also left rules, which means that in the stope we have left rules. And when we construct our proof tree, firstly we apply all right rules until the goal formula becomes propositional variable, falsum, or disjunction. And also pay attention to the fact that negation is not explicitly shown here. It represents in this system via, for example, node A is equivalent to I implies falsum. And the difference between this GM system is minimal logic system, and the difference between intuitionistic logic is this rule. Here in minimal logic we continue our proof when we come across this type of formula, we continue our proof this way, but in intuitionistic logic here the proof is ended like this, and this means that that branch of proof tree is successfully proved. So, and here pay attention that we partially solve the problem of rule selection. The only problems are this L1, L2, R1, and R2, because these are the specific property of that logical elements. And the problem of generation also is solved here, but the problem of loops still remains, and we have to develop some new systems for also solving these loop problems. And the choice of rules partially solved, and we have to add some new mechanism there. Let's consider this sequence, and let's try to prove this, to construct a proof tree for this sequence in our GM system. Firstly, as we have no, our goal formula is a propositional variable, we have to set this context, formula from context. It is only one here. We have to set it to the stope. After it, we have to apply left rules, left rules here, and we get formulas like this. After some steps, we get a formula as the beginning, and here you can see that we have a loop, and our proof will become non-terminating. And because of this problem, we developed a system GM-hist with different history mechanisms, and with the help of this history mechanism, we try to solve the loop, we try to detect loops and avoid it. We do have two different slightly modified versions of history saving mechanism. The first one we will call Swiss history, the second one Scottish history. And we can realize that only keeping all the, we can store in our history all the formulas during our proof, and at each step we can check whether the formula is in history or not. But this is very inefficient way because it requires much history, and we have to make checking every time. Because of it, we can show here that our proof rules are that context cannot decrease. Once a formula in each these rules, once a formula is in context, it will remain in the context. And so when the context is extended, we can empty our history. This epsilon stands for empty history. And also, we can store only a call formula in our history, because if the call formulas of two sequences are the same, the context is still the same, and we have the same formula. And with the help of these optimizations, we developed two systems. This is the Swiss history system. And here you can see that we have rules like in GM. We've extended this history notations. And pay attention here at the star restriction. Here for this C rule we have a star restriction, which means that our P formula must be a propositional variable, fulsome or disjunction. And the difference of minimal and deterministic logic is this rule and this rule. And this is the Scottish history, which is some slightly different approach of storing history. And the difference between Swiss and Scottish history are the following. We have to make some trade-off. We can store many formulas in our history and make some checkings very most often. But because of it, we extend our history, and it will become not efficient. So the differences are the following. The Swiss history requires less memory and requires less checkings, but it is slower and it detects loop slower, and it makes some unnecessary steps during proof. And we show equivalence between our developed GM-HIST systems and existing minimal logic system following way. We have a GM- system introduced in paper 1 in my references, and it is minimal logic system. And the equivalence between GM- and our introduced GM system is showed in paper 3 by also me and Polypekian. And it means that sequence S is provable in GM-, even though if that sequence is provable in GM. After it, we have a question about equivalence of GM and GM-HIST without star restriction we talk about. And we prove it with the help of theorem 2. We showed that sequence S is provable in GM, even though if sequence with empty history is provable in GM-HIST without star restriction. After it, we show the equivalence between GM-HIST and GM-HIST without star restriction. And with the help of it, we get the equivalence of GM- minimal logic system and our developed GM-HIST systems. So now let's look at three problems we have. The generation of proofs which are permutation of each other. This problem is solved. Loop detection is added to our systems, and non-terminating proof search is solved. And the problem of rule selections remains unsolved here. And we have to add some new ways and some new mechanisms for avoiding this problem. Let's consider this example. Suppose we want to prove this formula in our GM-HIST systems or in GM system. Here you can see that we have a sequence like this, and now we have to choose a formula from the context and to set it to the stop. Here we have two selections, A implies B or A implies not B, and our prover must continue with two branches. And it will be perfect for us if we can predict which one direction is good for us and which one will give us a small proof and will avoid unnecessary computations. Here you can see that in this step we also have two selections, and this green line shows us the good way. Here we successfully proved our sequence. And this green line shows the right direction for our proving, and it will be nice if we here can predict that this A implies not B is the right selection here, and here A implies B is the right direction. And in that case we will avoid these unnecessary computations here. And for that reason we have deployed neural networks to our systems, and with the help of neural networks we try to predict which formula from the context we have to choose and set to the stop. And for that reason, we developed an automated theorem prover, which we call SVProof, based on GMP system with Swiss history, as we talked about. And then more than 10,000 formulas we generate with the help of 50 predefined formulas of minimal logic, with the help of superpositions or other techniques. And we plan to use MISAR or TPTP dataset in future for generating these formulas. And after it, we build a proof tree for each formulas with the help of this SVProof automated theorem prover. And all the points which contains rule selection problem we store and save triples of these points. The triples are subtree representation, candidate formula, and yes, no, if a candidate formula is the right selection for us or not. And as a result, we get more than 50,000 training data points, and we divide them into training validation test parts with 18-10% proportions. And to be able to use this sequence in our neural network, we have to get them some numeric representation. And for that reason, we assign a specific number to each symbol, and based on that representation, similar formulas in our system get identical vectors. And as a final step, because we have a different length representation of our sequence, we train an autoencoder to get fixed length encoding for each sequence. And here you can see our encoder training progress. The orange line is training loss, and validation loss is shown by blue line. Here loss function is L2 distance between encoded and original vectors, and here you can see that our L2 distance between original and encoded vectors is very small. So the representation, the encoding is good. After it, we train our main model for predicting the next formula to select as top. Here we get the sequence of formulas in proof tree, our subtree in the point of candidate formula choosing part. And we pass the representation of this subtree, proof subtree, we pass to recurrent neural network. We tried different neural networks here, but the best one was recurrent neural network with LSTM layer, the best accuracy we get with the help of this type of neural network. And we get an output from this recurrent neural network, which we concatenate with each of candidate formulas from the context we think we want to select and set it to the store. After it, we pass this concatenated vector to two dense layers with non-linear and linear activations, and after it we get two length one-hot encoded vector. And during inference, this vector will show us will be a probability vector, and will show how much our chosen candidate formula is the correct one, and how is the probability that this selected candidate formula is the wrong one. And during inference, we will pass each of candidate formulas to our neural network and get and sort by higher probabilities for prediction, and with the candidate formula which has the higher probability will become our next stop. This is the RNN training progress. Here you can see that accuracy of our model is about 70%, and this is very good result. And now later you can see the results how neural network helps us to solve that problems. But because we deploy our neural networks to automated theorem provers, and our main goal was to reduce proving time in automated theorem provers, and neural networks are very computationally expensive. So that reason we have to make some optimizations for our neural networks, and to make inference of neural networks much faster. For that reason we do three different themes. The first one is inference reduction, the second one is TensorRT optimizations, and after it we deploy our neural network in different GPUs with different architectures. Here you can see that I've already said about it, that for each of candidate formula we have running this part of our neural network, which is the most computationally expensive part. And now we only run this part of neural network once, and for each candidate formula we only concatenate the candidate formula representation to this feature vector, which is generating only once. And we use an NVIDIA TensorRT, which gives us these 5 possibilities. But the two most interesting parts for us is precision calibration and layer and tensor fusion. With the help of TensorRT, we can run our model with different arithmetics with the help of float 32 and float 16. And here you can see a comparison of different benchmark of different comparison between our model runtime in different GPUs with different architecture. Here you can see that, for example, in NVIDIA V100 GPU with Volt architecture, we can make more than 3,000 inferences per second. So we can make 3,000 runs for our model, and this is a very optimized model for us, and we use this in this GPU for our automated theorem prover. And as a result, you can see here that we have here is shown different formulas, and it's proving time in SB proof system without neural networks, which is based on GM-HIST system with switch history, and the comparison it with proving time of SVNN proof, which is a prover with the help of neural network. And this is time in milliseconds for proving formula. Here you can see that in simple formulas, SV proof is faster than SVNN proof, but in complex formula, our neural network deployed system is much faster, and because it avoid unnecessary computations, it helps us to make our proofs much faster. Also, in our experiments, we have formulas which we cannot prove with the help of SV proof because of computational resources. But SVNN proof with its optimizations gives us a possibility in the same computer to prove hard and complex formulas. This is references, main references I've used, and thank you.
Thank you to our speaker. It's time for questions, comments. Please welcome.
Yes, I just wanted to ask two clarificatory questions. And so the first one is, I guess you didn't use like G3 systems, for example, because of the the G3 system for minimal logic that is described in this book in 2008, because of the permutation problem. Right?
Yeah,
this is the key. I see, because otherwise you will have kept some others, but it's a question.
In G1 system, we have a possibility. We have a straightforward solution for it, and it will become very simple for us to solve that problem in G1 system. But in G3, it gets some problems, and because of it, we use G1.
I see. And the other question is, I guess we have a simple answer for this. Why not intuitionistic logic? I mean, it's not too far away, right? Like either you put a bottom as an initial sequence, or maybe you do like an explosion. Like if there is bottom on the right, you can infer like.
Yeah, it comes from application. We have a program verification problem there, and we want to construct our system in minimal logic, which is a part of intuitionistic logic, and it's constructive logic, and because of it, we want to use our networks to build on, especially on minimal logic. But the same can be applied to intuitionistic logic, and it's also right for it.
I see.
Thank you.
Okay. Still a time for another question, comment? Okay.
It's a pretty naive question, maybe. It's the same. What's the motivation for minimal logic? What are the reasons we deal with minimal logic?
Minimal logic is part of intuitionistic logic, yes, and it's constructive logic, and because of it is the main interest of our main topic of our interest. And we have a problem of program verification come from my supervisor, and he recommends me to develop system in minimal logic firstly, and then if it is necessary we can switch it, we can move it to intuitionistic logic also. So because of that reason we try to do it in minimal logic, and it is also true for intuitionistic logic too.
Okay, the last call for questions and comments. And if not, let us thank to our speaker again. And it's a time for coffee break, 15 minutes altogether, so the next part of this sections will start at 35.
So I invite you. The subject of my speech will be question if there is something like alternative mathematics, and this is the main story, and the sub-story is Petr Vopenka wandering to alternativity and back. I will start with two case studies, two stories. The first one, it was only a short videotube joke. It depicts conflict between a teacher of mathematics and her pupil who insists on the alternative fact that 2 + 2 = 22. The teacher tries to explain him the mistake, but without success. Later on, the boy's parents and the school management recognize that everybody has the right to his or her own opinion, and therefore it is not possible to deny that right and to insist on obsolete textbook truths. And eventually the teacher loses her job as she was not capable of accepting another point of view. This is a short, it is not the whole joke, it has some continuation. You can find it on this YouTube. So from this point of view, it looks that anything like alternative arithmetic is but nonsense. The second speaks about the alternative higher mathematics. The central concept of higher mathematics, with some simplification, is the concept of infinity, infinity big or infinity small. The problem with infinity was, the infinity was known from the ancient times. In ancient Egypt, they have Hehe. It was even the god of infinity. In ancient India, it was Ananta. In ancient Greece, it was Apeiron. However, there was a problem how to incorporate infinity into mathematics. There were big problems, and therefore most mathematicians decided that it is not possible, that we must only use so-called potential infinity. It means not anything, no object, but process increasing over any certain limits. This was the idea, this was the opinion of Pythagoreans, of Aristotle, and most of other Asian mathematics. The change came with
not the change, but the important idea was formulated by St. Augustine. St. Augustine in the early 5th century of our epoch created so-called Theoplatonism. It means he came from the philosophy of Plato. However, he moved the realm of ideas, the realm of forms, to the mind of God. And this way of thinking I called Theoplatonism, and it has a great influence on the later philosophy of mathematics. And he also offers us a proof of infinity. God knows all numbers, so he must know infinity. Therefore, infinity exists. Of course, it is not proof, it is rather axiom. Also the omniscient God is rather axiom than anything else. However, God knows, but mathematicians failed to implement it into mathematics. The reason was that their subconscious or unconscious philosophy, their paradigm, did not allow them to forgo self-evident axiom valid for finite world. Yes, in the framework of finity, we cannot accept any infinity. Concerning axioms, it was initially supposed that axiom express natural, evident truth. At the beginning, the axioms were mostly on unconscious level. Yes, it was later Euclid and other mathematicians which formulate it consciously. However, concerning infinity, we or mathematicians had to introduce less natural, I wrote supernatural axioms. Yeah, and behind them there is still hidden image of omniscience being. It means God. Yeah, and the Asian mathematician really spoke about God, who is a guarantee for infinity. Another view on this axiom are that they are artificial human constructs. They are product of our fantasy, consciously formulated and accepted. So we can have two approaches, that it is given from up, they are divines, or they are our product of our fantasy. The progress came in the middle of the 19th century with Bernard Bolzano, who introduced the very concept of set, die Menge in German, and it consists of elements. There can be infinite number of these elements. And even Bolzano offers us proof of existence of infinity based on the God's omniscience. He spoke about the infinite realm of truths. There is a truth sentence which expresses truth. There must be another sentence which expresses that this, and so on and so on. It's a little different proof than St. Augustine, but it does not matter. And what is important, he taught that between all infinities can be found one-to-one correspondence. And this is one of the most weird, most fundamental paradox of infinity formulated by Bernard Bolzano. Of course, the most mathematicians accepted the beginning of theory of sets connected with Georg Cantor. Georg Cantor was birth father of set theory. Bolzano was also only grandfather. For Cantor, the criterion of equivalence of set is one-to-one correspondence. Of course, this is also definition or axiom, which contradicts opinion of Bolzano. So, from Cantor's view, Bolzano's view is not correct. It is not alternative theory, because Bolzano's view is not correct. And we can find it in many textbooks today that Bolzano was not correct. So as we know, Cantor introduced bigger infinities and even infinite number or infinite amount of infinite numbers, which are guaranteed by axioms, and the validity of axiom is guaranteed by our God. What is interesting at the beginning, when Cantor first met with a bigger so-called uncountable infinity, he paused and hesitated. It was the case when he studied the quantity of so-called fundamental sequences, now called also Cauchy-Bolzano sequences of rational numbers, which define so-called real numbers. Later he formulated his famous diagonal proof, and this was the idea of these two proofs were similar. However, when he met the question if there are more real numbers than rational numbers, he paused, he stopped, and he was hesitating. Because most of these real numbers, most of these sequences are not possible to calculate. It is not possible to count them. The French mathematician Émile Borel named them mathematical jokes. And the amount of constructible sequences is the same as the amount of rational numbers. So the similar situation was in 1891 with so-called diagonal proof. There he showed that there is more numbers, real numbers than rational numbers. However, most of them have quite undescribable decimal expansion. There is not possible to catch it by mathematics. So what are the strange numbers, so-called real numbers, which cannot be numerated, which cannot be known? So this initial hesitation was because his hidden voice of his unconscious pragmatism. Cantor, as most mathematicians, was of Theoplatonic religion, in quotation mark. However, he was also, as all of us are, a little pragmatic and eclectic. So he hesitated. No, after some hesitance, Cantor gave to the temptation of traditional mathematical religion Theoplatonism and accepted these jokes. And by this way, he got to the greater uncountable infinities. And he concluded that Bolzano conception is not correct, and this is not alternativity to Cantor's theory, it is not correct theory. Another step was building of so-called, Vopenka spoke about Babylonian Tower of Infinities. He realized that so-called power set must be greater than original set. Power set is the set of all subsets. And this is evident in the case of finite sets. But is it true also for infinite sets? Can we construct subset, the set of all upset in the case of infinite set? Of course we cannot. Yeah, this is also idea that some higher being, some God knows it and can construct it, but it is behind the possibility of human being. However, mathematicians accepted that this Cantor's theorem, which is in reality axiom, is correct, and then they accepted the existence of infinite high, tower of infinite set, which goes to the most infinite infinity, the absolute, which is given, which is divine, which is related only to God, as Cantor remarks. And later mathematicians find it even more effective method how to climb the Tower of Babel of infinities. They were speaking about finding or study of high infinities, but it was really in reality only construction. The main tool was acceptance of new and more supernatural axioms. The axiom that define the existence of something that can't be positively defined. For example, we suppose that there is a bigger, higher infinity of numbers which have quite irregular decimal expansion, but there is none that can be found. Yeah, the idea comes from this secular world to some higher world of some divine higher world. As is generally known, the Cantor story was at the beginning not very positively accepted among mathematicians. However, it was surprising that even the Catholic Church accepted Cantor's definitive earlier than mathematicians. However, at the beginning of the 19th century, situation changed, and mathematicians started to support that the Cantor's theory creates something like mathematical paradise from which no one banished mathematical anyway, as in the word of, according to the word of David Hilbert. And after, as mentioned, Cantor's theory was accepted by majority of mathematicians, and Cantor's infinities were believed to be facts, and no alternativity was acceptable. And there started a new idea that the whole mathematics could be based on the set theory. It was the grandiose project of so-called Bourbaki group, the group of French mathematicians. And I wrote that mathematicians found themselves in one-way street because they suppose that this is only the one possible way of thinking about infinities and about sets. This is a photograph from Halle and Saale, the city when Cantor worked and is buried. Cantor Paradise was a mysterious place and mysterious attract. I think that this was the main reason that this has some divine, something divine. There, concerning alternative approaches, the first alternative approach is connected with Lucian Brouwer, who formulated so-called intuitionism. The intuitionism was based on the axiom that everything which is real must be intuitive, that something which is very strange is not real. And infinity is too big to be evident, so it is not real, it doesn't exist. At the beginning, this anti-Platonic approach, why anti-Platonic? Because they did not believe in the existence of some independent realm of mathematical entities. Mathematics is but human invention, and these Bolzano's and Cantor's concepts are pseudo-concepts. However, later, Brouwer returned to Platonism, and his teaching was so idiosyncratic and systematic that it was rejected as Bolshevik menace, according to the word of young British mathematician Frank Ramsey. This is Petr Vopenka on Sázava seminars in the summer of 2012. Vopenka formulated many interesting ideas which are not even till today enough estimated, and his step to the alternativity was, I think, very important and founded on philosophical background. He realized that Cantorian infinities played no role in the world of phenomena and the world of physics. He was influenced by Husserlian phenomenology, and that the Kantorian view belongs among school prejudices. I called his visionary rule this axiom. It was originally formulated in a more complicated form, that the more elements some set contains, the lower is their value, their reality. So this is interesting. It cannot be proved, it is some kind of axiom. And another interesting idea, so-called general collapse. Vopenka said there is one-to-one correspondence between all infinite sets. So it can be suppose it is a particular application of Vopenka visionary rule, because the reality of higher infinities is even null, because the degree of existence of these elements tends to 0. Of course, there is a fundamental objection. Cantor demonstrated that there wasn't one-to-one correspondence between the set of integers and the set of real numbers. However, Vopenka argued, if we accept only numbers that have any meaning in mathematics, then the set of them is countable. The uncountable rest of the reals are numbers without any meaning. They cannot be expressed by any means. Cantor didn't find them, he didn't discover them, he even didn't construct them. He only defined that they exist, that they should exist. And it is possible to run mathematics without them, although some theorems should have been adjusted. And higher infinities, higher cardinals also play no role in practical mathematics and also in physics. How it was proved by Roger Penrose, for example. You can find it in this Penrose book. There are these mathematical jokes. The most important contribution of Petr Vopenka was, of course, his alternative set theory. He realized that we must go behind Theoplatonism, that God, whether he exists or not, does not play any role in mathematics. So do not supernatural axioms. And he built his theory without this Babylonian Tower of Infinities, without God hidden in supernatural axioms. And he introduced alternative or parallel concept of infinity. He believed that there would be two theories, Cantorian and his alternative. However, the development of the history of mathematics was a little different. So is there possible existence of more set theories, alternative mathematics all being right? Vopenka at that time said, yes, they are. He abandoned Theoplatonism on behalf of the realism of the world of phenomena. Mathematical entities represent our abstraction from the phenomenal world. However, abstractions are possible to accomplish in many ways. The relevance of aspects depends on our point of view. So there is space for alternativity in mathematics. However, I will skip this because there was also an idea that the mathematics is possible to found even without theories. This was formulated by Jiří Fiala. In recent years, there has been an increasing belief that we could easily do without set, that postulating such entities such as set and sets of sets and so on is at last suspicious and could be only language artifacts. In addition, there are some sociological indicators that purely mathematical exploration of set theory doesn't seem to be supported in the United States anymore. And perhaps once again, everything could return back to Prague, from which it came as a wonderful flower of Baroque. It's a metaphor of Vopenka. And possibly it could only turn out as a merely scholastic research in a pejorative sense. This is in Czech, in original Czech. 5 minutes, yes. But what this is not end of Vopienka's story. Vopienka gradually felt that the existence of more set theories was unacceptable. Only one could be the right. And at the end of his life, he came to decision that the only right theory was his own. He stopped using the name, the alternative, and he called it the new theory. Today, this initially alternative set theory is now a new set theory because there exists no alternative. And because traditional mathematics is built on a poor foundation, the whole building should be rebuilt. In a nutshell, mathematical research has to start again from the point where it ended, and that is at the beginning of the 20th century. Mathematicians did not accept this catastrophic conclusion because the old mathematics worked well, so why to talking about collapse? However, why Vopienka abandoned his most beloved child, the idea of alternativity? In my opinion, it was because people getting older are looking for something sure, they are feeling they are losing ground under their feet, and they sometimes return back to religion, and mathematicians return back to their mathematical religion. It means Platonism. Of course, not the original Kantorian Theoplatonism, but his own kind of Platonism. He explicitly said that all philosophy of mathematics should be Platonism. So he returned back to Platonism, and I say he lost the Kantorian paradise, and now he did not want to lose the rest of his mathematical religion. So I think the reason was mostly psychological. The solution of the problem of alternativity. I came from the division of described by Hans Reichenbach, a German physicist and philosopher, who spoke about phenomena. It means things which appears to us, which are apparent. And in the case of mathematics, this phenomena corresponds to numbers, to natural axioms, to simple arithmetic relations. However, there is the results of calculation that belong among phenomena must not contradict our experience. Yeah, this is the case, the first case with 2 plus 2. However, he introduced or he realized that there are also another kind of scientific object called interphenomena. So during the development of science, there were also introduced higher non-phenomenal objects. The infinity, first of all, infinity is not phenomenon, is not apparent. They do not correspond to anything directly observable. They are our entirely consciously created constructs. We created them intending to go between and behind phenomena, to connect them to causal links, to complete and arrange them into the consistent system, to explain them. In the process of the creation, we use conscious and sometimes very presumption and sometimes very sophisticated constructs. The world of phenomena can be arranged in numerous ways, so interphenomena can be also constructed in many alternative ways. So in the realm of higher interphenomenal mathematics, this is typical that higher mathematics is interphenomenal. There are such quantities, the qualities that did not correspond to anything apparent. So in the realm of higher interphenomenal mathematics, we can tolerate alternative theories, various concepts of infinity, alternative truths. And the conclusion, Vopienka's funeral of the alternativity of the set theory was premature. So thank you for your attention.
Thank you. It's a time for questions and comments.
Please, if anybody wants, I wrote this text and I have several copies. I can give it to him or to her. So Můžeš i česky.
Infinitary mathematics, and as far as return to Platonism, I don't think he ever abandoned Platonism. His Platonism only developed along the lines of Husserlian phenomenology.
I think that phenomenology is closer to Aristotelianism because in the basic elements are phenomena and not any Platonic higher word.
Phenomena in phenomenology, we are really not talking about any subjective perspective or about psychologism. Phenomena lead to some intersubjective phenomena, really. We are looking for something which is shared, and it's, as far as philosophy of mathematics goes, it, I think, led to something which is called constituted Platonism, and we get this Platonism back in a sense. So I would say I'm
So
sorry,
you
I
would
just
call
had to
everything
disagree with
Platonism. So
with that conclusion, because I don't think Wopenka abandoned his alternative set theory on the
but in his last works, he said that there is no alternativity. And therefore
well,
he
he
renamed this theory the new one.
He liked to tease, and I recognize the quote when you said that there is nothing, the new infinitary mathematics or the old alternative set theory could be an alternative to, because the classical set theory is dead, because there is no set of natural numbers and so on. But really, I think it has to be taken with a
Is that it is not correct?
Sorry?
No, is that it's not correct? The classical theory of Cantor.
He did write that, but he wrote.
He said that it is bad, and therefore we mathematicians should rebuild the whole mathematics from the beginning, from the start of the 20th century.
Yes, but it's sticking to his alternative set theory, really. In his last book, New Infinitary Mathematics, he really goes back to the very same ideas. As far as I understand it in the book.
So we can discuss it later.
Okay.
Thank you.
Okay.
Thank you. It's still time for questions.
I think that the similar situation was with intuitionism. That at the beginning there was a revolution that no Platonism, only the word of phenomena, and later it was step backwards to some strange kind of Platonism, which was not accepted by most of mathematicians. Yes. So.
If I understand, I can construct the potential of natural numbers, but only in a potential way. I cannot close it, because if I close it...
You speak about the power set, or?
Yes. No.
Yeah, you can do it, but in the case of finite number, there is no problem.
Yes,
but
yes.
does it? There is no proof that the power set exists also in the case of infinite numbers.
Yes.
Nobody can do it. Yeah, this is typical for mathematics. For example, Banach-Tarski paradox. The sphere can be divided into 5 parts and then shifted and made two similar or equivalent, but nobody can do it. Yes, so what does it mean?
The mistake is that I closed it. That the power set is closed set. Yes, because if power set exists, then there exists proof that cardinality of power set is greater than. Yeah.
But the proof presupposes that such amount exists. If it accepts its existence, then Cantor proves that there is no one-to-one correspondence, and so it must be bigger, of higher cardinality, of course.
Is correct.
Yeah.
And another question, the simple question, what about P in geometry?
You mean pi?
Pi.
P in it, it sounds a little unpolite in English.
Rudolph's number.
This is a strange number. It's so-called normal number, perhaps. It was not proved, but yeah, I spoke about it, I don't know if here in Brno or somewhere, because if it is so-called normal number according to Emil Borel, it means that all figures, all combination of figures are equally or present there. So if it is true, so in number pi you can find, for example, 1 million zeros behind one near one, but yeah, I cannot tell you without the relation with the number pi.
Thank you.
Sorry.
Okay, so the last question or comment.
You're
welcome. I can bring you the mic.
Thank you. I knew Vopenka very well. I don't believe that his position to alternative and new mathematics was so as presented here. More than 40 years ago, I followed at a Congress discussion about philosophy of mathematics. There was invited great American logician John Schoenfield. He refused to discuss with those philosophers, but said just one sentence: I don't accept philosophy which prohibited something.
Thank you.
Thank you for your comment. Yeah.
Okay, I have said that this is the last question. We still may discuss somewhere in some other place. I would like to end this conference day. We will meet tomorrow. The first talk starts at 9:30. It's Professor Baas, but we can meet even earlier at 9 o'clock. Coffee should be prepared at that time. So thanks. Let's thank our speaker again. Thank you.
Thank you.
During consequences of a short paper by Gödel, looking forward.
Okay, thank you. So how I switch that on? Up. Okay, good. So, as my revered predecessors, as invited speakers, devoted themselves to the most famous result of Kurt Gödel, I decided to speak about a much smaller paper, and the interest in Gödel's thinking you could see in a certain sense even better from the smaller papers, because in the most famous large paper about the incompleteness theorem, you have a revolutionary, groundbreaking result. So this is some sort of a unique thing in centuries. And so you cannot use it to derive general statements about the way how Gödel considered these things. So let me first thank for the invitation. So I am representing also the Kurt Gödel Society in Vienna. And I should mention here that Gödel does not belong to any nation. He is, of course, generally belonging to all countries, and I'm very happy that he is celebrated here, also in Brno, where he was born. So the paper I will speak about, so let's, what is it? No? Oop. How I switch here. Ah, that's important. Thank you, thank you. Okay, so that is Kurt Gödel in the time when he wrote these papers, and so in the Viennese time. In the Viennese time, Gödel wrote 2 long papers, the completeness and the incompleteness theorem, and several short papers. The short papers mostly coming from discussions in the Menger seminar. The Menger seminar was some sort like a deviant version of the Vienna cycle, namely one where the logic was not treated as a mere philosophical entity, but more as a practical mathematical entity. And in this Menger seminar, so Menger brought Gödel to write down the things. And there appeared some short papers. And the interesting point of these short papers is that every of these short papers contains logical ideas, so that you could build a logical career on any of them. Yeah, so this is a specific thing of Gödel. And here in this lecture, this is more or less a technical lecture, but I do not want to present it as technical lectures. I want mainly to show how Gödel's way to considering mathematical stuff was, in fact. Namely, you could ask, what is a specific ability which distinguished Gödel from other contemporary mathematicians? So why the enormous talented John von Neumann, for example, did not arrive at Gödel's results? I mean, in a certain sense, he came at the second incompleteness theorem, but later than Gödel. And Gödel was also himself absolutely convinced that nobody else can come up with his results. So whatever you hear, Gödel was very relaxed on working. So in the time he worked on the incompleteness theorem, he worked usually maximum 2 days a week. The rest he went partying after he married his wife. So his wife was for partying and Gödel went with her to the parties. So Gödel was not like that, like you might think. It is not some sort of an ascetic hero devoted purely to the pure art of logic. And you also will hear that that Gödel is the greatest logician since Aristoteles. But in a certain sense, this comparison is not the right one, as Georg Kreisler always pointed out. Namely, first of all, Gödel did not invent logic, not even in the modern sense. So in a certain sense, Frege would be more comparable to Aristoteles. But Gödel is very much comparable to Archimedes, because he changed the field completely. So the impact of Gödel on logic was that before Gödel, logic was some sort of a field of mathematics, however a confused one. And that you can see if you read the writings of the greatest mathematician of the time, in some would say the greatest mathematician of all times, namely David Hilbert, who was very precise and sharp in everything what he wrote about mathematics. But if you read his logical writings, you will see this confusion. Yeah? I could even point you a place in the infinite where on one page he states A and the other page he states non-A, Hilbert. Yeah, and this was completely changed by Gödel. So what was the important way of thinking of Gödel? I think, personally, the important way was that Gödel was willing to take abstract ideas serious. So many people think, what is truth, what is proof, what is that, what is this, but they will only do it to a certain degree, like a novelist who writes certain properties of his figures in the novel, but he would not make a 1,000-page exegesis on these figures. And so most people don't take these things serious, but Gödel took them serious. And he was very much interested in this way of thinking. He was not so much interested in the so to say, in the consequences of this thinking. So in that sense, he was also not the usual mathematician, that you can easily see that Gödel developed so many completely new technologies in mathematics and never used them a second time. Because his point was the development of these things. He did not want to solve problems, to solve the problems, but to see how such problems can be solved. So it was in all aspects. You maybe have heard of the famous proof of the existence of God by Gödel, which is a variant of the Anselm proof. And rather recently, in his left papers in Gabelsberger, it was deciphered that he wrote that he does not intend to publish this proof because the people might think he's religious. And this exactly describes it. So he is interested how you can prove the existence of God and what does this mean. And it is also an instantiation of another aspect, namely he analyzed the dogma that scientific fields have the biggest consequence in combination when they are the most apart, and he thought what is more apart than theology and logic, and so on. So this was the way he was thinking. And now we look at this paper in original. So this is the original of this paper, not easy to find, and it has exactly 2 pages. Of course, I do not translate this to you. This is in German. These were the maybe it's only 1 page. And so let me first say what is in fact in this paper. And these papers are 2 things. And 2 things are very, very important for logic. Namely, on the one hand side, he introduced the pigeonhole principle, and on the other hand side, he introduced that what is nowadays called Gödel logic or Gödel-Damit logic. So what was the content of this paper? In this time, this was a big time of movement in logic. There were the big 2 revolutions. On the one hand side, Hilbert's introduction of the axiomatic method, the most fundamental revolution mathematics ever has seen, because the axiomatic method relieved mathematics from ontology. This is the important point. So since then, a mathematician says, I define me this and that, and I prove this and that about that. And so in the Hilbertian sense, it doesn't matter what the things are. It is only the question what you assume about them and what you prove about them. And so from Hilbert is also the notion of proof, which everybody learns in the first course of university, if not earlier. A proof is a finite sequence of formulas such that every formula is either an axiom or follows by a direct rule application. By that, Hilbert guaranteed 2 things. So the first thing was a proof is now objectively checkable. Before that was not clear. If I make a rhetoric figure, how you can check that objectively? You can believe it or not believe it, but you cannot check it objectively. And the second thing is some sort of a atomism. That means a proof is now a sequence of single steps where every single steps can be understood without understanding the proof. And so you can convince yourself that the proof is correct without understanding it in the classical sense, so that you know what it means. This was such a profound revolution that nowadays the people cannot even remember how that was before. So before, for example, to show that the parallel axiom doesn't follow from the other axioms of Euclid, a very old problem, you had really to construct the whole world of geometry, realistic geometry, where the parallel axiom was objectively false. For example, you have done Polai and similar. And this, of course, poses a fundamental problem. I mean, the fundamental problem, what means real geometry? In the end, you could say, for me, a real geometry is only a geometry where the parallel axiom holds, and then it is teratological. And so that was all revealed by, so to say, proved by Hilbert. And the book, the place where this happened, is a famous Geometry of Hilbert, maybe the most famous mathematical book of all times up to now. And but in the same time, there, so to say, appeared an anti-movement, and this anti-movement went back to a Netherland mathematician, Brouwer. And Seth Brouwer was a very impressive figure, I could say. So he's maybe the only case known to me who wanted to overthrow mathematics from his early age. But he understood that if he, as a young PhD, would say mathematics is false, logic is false, they would consider him as a fool. He decided first to become a famous mathematician and then to overthrow mathematics. So he became the Brouwer of the fixed point, of the famous fixed point theorem. And then he changed mathematics. And so his idea was, so to say, to go away exactly the opposite direction, the coherent opposite direction of Hilbert's developments, namely he, in this opposite direction, he said that logic basically is free of language. It is in the mind. And but what is the explanation if we believe that the things are construction of our mind, that they are somewhere? Why it is not possible that we know everything when it is so? Then the answer is because all these things exist, or we see them only partially. And as this is so, all transformations have to be continuous because they have to follow the development of the objects in time. And as all transformations are continuous, the so-called tertium non dato, excluded middle, is false, because the excluded middle obviously allows you always to define non-continuous transformations. And from that arose Brouwer's mathematics. And the interesting aspect is, from Brouwer's mathematics arose intuitionistic logic. So intuitionistic logic is a secondary product. The student and assistants of Brouwer, Heiting, went through all the writings of Brouwer, compiled all logical sentences, he were around 1,000 he found, and compiled the system of logic for it. That was the intuitionistic logic. Now from that genesis it is clear that nobody knew what intuitionistic logic is. And so that was of course a debate. And in this paper, Gödel showed two things. First, he showed that intuitionistic logic is not a finite valued logic. Secondly, he showed that between classical and intuitionistic logic, there are infinitely many other logics. Now, how he showed that it is not a finite valued logic. This is where he used the pigeonhole principle, and a known principle of intuitionistic logic, one of the few things they knew about it, namely that if you can prove A or B, then you can prove A or you can prove B. And so the pigeonhole principle works. You simply write x1 implies x2, or x1 implies x3, etc., take xn, x1 implies xn plus 1. If you assume indirectly it's an indirect proof that it would be a n-valued logic. And then you continue. x2 implies x3, or and then the last step is then xn implies xn plus 1. And now, as you have only n values, but n plus 1 variables, it is clear that two variables have to get the same, under any evaluation, two variables have to get the same value. And that means under any evaluation, this large formula, there stands some C implies C. Now this C implies C should be 1, because we know in intuitionistic logic that A implies A holds. And therefore, the whole formula would be a tautology. And as the whole formula would be a tautology, and it is a disjunction, you can find one disjunct. So that would mean that xi implies xg for some different variables would be true, and this is not even true in classical logic, which is a superset of intuitionistic logic. So that was the first thing. And the second thing was now the logics which are, what I've done, the logics which are in between. So the important point of this thing is a definition of the implication. Nothing else is important, but the definition of the implication. And here you can see this very elegant way of Gödel to see the things. So you take conjunction, disjunction, and so on, all with classical logic, with the only difference that you have not one value, you have many values, n values. And the only thing is the implication. And in this implication, it is simply so that A implies B is true when A is less or equal B. This is to be expected. But A implies B is B otherwise. So that means classical implication falls under that, because in classical implication it is obviously so that if x is true and y is false, then x implies y is false and y, so there's a value of y, is exactly here. And now the interesting thing of this all is that by this you can very easily understand that all these logics, for example, are different, because you have always formulas who separate them, and so they are different logic. It is also clear that they are include classical logic, and they are between classical logic and this intuitionistic logic for the simple reason that if you so to say classical logic is a superset of them, and they extend intuitionistic logic. All principles of intuitionistic logic easily can verify it in that context. So, and now we will see how this simple definition of logics give a big plethora of logics, and so it shows in a certain sense this incredulous elegance which Gödel could find to fix such things. So let's continue. And so now sometimes this logic is called Gödel-Dammet logic. For the infinite valued variant of this logic is called Gödel-Dammet logic, for the simple reason that Dammet has shown in a certain sense a completeness. But I generally object to that for the simple reason that Dammet has shown it on a certain semantic which is not compact. So the entailment is not compact. If you would take the whole 0-1 interval, then the entailment is compact. But in the Dammet notation, so the Dammet used the finite linearly ordered Kripke semantics of constant domain, one would say nowadays. So they would be represented by the values 1, 1, 1, 1, 1, 0, 1, 1, 1, 1, 0, 0, 1, 1, 1, and so on and so forth. So Kripke semantics, by the way, is a semantics developed later by Paul Kripke for intuitionistic logic. So it was not from the Brauer time, one could say. And this semantics is of course a countable one. So if you would consider it in the order type over the 0-1 interval, then it is simply a descent to 0 with cumulation point at 0, a countable logic. And here it is so that and here we have some principles. So these Gödel logics have the property that they are linearly ordered. They have some sort of a extended tertium notator, non-A or non-A, and finally we have in the three-valued Kripke logic the last sentence A implies B, or B implies C, or C implies D. In classic logic, we would have only A implies B or B implies C, and so on. And exactly this type of sentences separates the finite-valued Gödel logic. This is written already in Gödel's paper. And now the point is that these Gödel logics have a very, very rich structure. So, for example, already the entailment separates uncountable many logics. Namely, first of all, the logic will be compact only if and only if the set of these truth values of this Gödel logic is uncountable, otherwise they are non-compact. Secondly, you can distinguish logics after all countable ordinals. So for every countable ordinals, there's a different logic. So to say the small logic for the smaller ordinal collapses in the logic for the big ordinal. Therefore, there are uncountable many entailments. Also, there is only one. There's in fact only one infinite valued logic from the set of tautologies in propositional logic. And this why this is the case, it's very easy, because what does it mean that such a sentence is not true? It depends, this is an evaluation which gives a value less than 1, and this evaluation depends obviously only on the number of variables. So plus true and false, one could say. So a sentence with n variables will be true in the infinite valued Gödel logic if and only if it's true in the n plus 2 valued Gödel logic, and therefore also infinite valued Gödel logic is decidable. That is the easy argument. And this is observation of Takeuchi, that in fact the Gödel conditional, also this definition of the implication, is the only conditional which fulfills modus ponens and deduction theorem, both over such linearly ordered truth values. Now, why the deduction theorem is so important? The deduction theorem or variants of it guarantee. So what says the deduction theorem? The deduction theorem says that when I can derive B from A, then I can derive A implies B. And variants, so the deduction theorem can of course occur in variants. So for example, in first order logic, we have to consider the universal closure to obtain this deduction theorem. Or in let's say in a modal logic like S4, we have to say A follows from B if and only if box A implies B, and so on. But some variant of the deduction theorem is extremely important to identify proving in theories with logical proving. That's what Hilbert used so much in his formulation of the axiomatic method. Because, of course, the usual thing is we do not want to derive logically, we want to prove things in theories, in number theories, in analysis, God knows where. And if the deduction theorem in no reasonable form holds, there is no connection between the proving in a theory and the proving in logic. So in a certain sense, you have locally always to find a new way to prove for every theory. So completeness is useless in a certain sense. And this is important for the deduction theorem. And a set property of the Gödel implication also shows that in a certain sense, this implication is a preferred one among these many-valued logics. So you have here something that behaves in a certain sense as it should, as classical or as intuitionistic logic. So this is an observation of Takeuchi. Here's a proof, but the proof should not bother you. So the typical thing is that all these things were not, which I show now, were not developed by Gödel, but he could have done if he would have wanted. So he said the very easy primal concept, which is the right one, and from this right primal concept you can derive anything. And this is generally true for many things Gödel did. So for example, if you communicate the idea of the incompleteness theorem, the idea is extremely short, so you could read in the Handbook of Mathematical Logic in Smarinsky's article that the core of the proof are exactly 5 lines. Yeah? And if you have this idea, all the other things mildly talented student could do over the summer if he sits down. Yeah? But to have this idea. And so this was Gödel's general opinion. Gödel was of the opinion, which is maybe not shared in mathematics, that the mathematical truths are all extremely simple. And all the mathematics is only used to communicate these mathematical truths. So you have to work hard to communicate this thing. And the proof is in fact a matter of communication. It is not something that verifies the own thought. And the own thought is extremely simple. When I organized a big conference on Gödel's 100th birthday, 2006 in Vienna, there was also Paul Cohen, who proved the independence of axiom of choice and continuums hypothesis. One result that Gödel always wanted to obtain but was not able to do so. And he told me the following story, which he, I think, never really understood to the end. From his point is also difficult. Namely, when he proved this result, he was very afraid that Gödel would behave like Gauss. So Gauss usually, under such circumstances, said, "Wonderful young man, exactly as I've thought 20 years ago." That Gauss would have done. But Gödel didn't do that. So Cohen brought his manuscript to Gödel's house. The door opened, the hand came out, took the manuscript, the door closed. Yeah. So on the next day, Gödel have read it, he received Cohen. And you should note that this was already a special honor, because Gödel usually received nobody. I mean, there were very few people he communicated with. So basically, among the younger ones, there were only 3, namely Takeuchi, Kreisel, and Wang he communicated with for various reasons. Kreisel and Takeuchi at the same time, Wang a little bit later. There were some other people, but he did not communicate much. He was even very evil in that. So, for example, many people wanted to meet Gödel. And so when they asked him to meet, he agreed with him to meet in the park. Yeah? But he never went there. So his wife once asked him why he's doing such, and he said, "Then I know at least that I will not meet them by chance." Yeah? Because he would know that they are in this park, and if he avoids that, he would not meet them. And so that was the way. Now Gödel received Cohen, a great honor, and asked him to explain the proof. So Cohen explains the proof. Then Gödel asked, what is the idea of the proof? Cohen, who was a usual mathematical formalist, thought that Gödel didn't get the proof, so he repeated the proof. Gödel asked again, what is the idea of the proof, etc. And I think still when I met him, Cohen was not sure about what Gödel wanted. But that can be interpreted in exactly the way that I said, that he thought that all this proof of Cohen underlies a very simple idea, and he wanted to know this idea. He could not see the idea from the proof, and he wanted to know this idea from Cohen. So this was the way how was Gödel thinking about proofs, like proofs being some sort of an enlightenment, and in that way he considered these things. And it is very true. Very often his methods was that the underlying idea, not the work, the underlying idea are from an extreme simplicity seen afterwards, but not before. So for example, if you think about the famous proof of the consistency of the axiom of choice and the continuum hypothesis, that was, by the way, the proof of Gödel that at this time fascinated the people the most, because they had serious problems with the axiom of choice. Not so much with the continuum hypothesis, but the axiom of choice. There was a Tarski paradox. The Tarski paradox is, of course, not a paradox, because it is something that uses unmeasurable sets, so it has a hidden wrong assumption that all sets are measurable. But still, it comes very clear to a convincing contradiction. Yeah, so if you are unaware of the circumstances in set theory, you could be easily convinced that set theory is contradictory by the Tarski paradox, and so on. And the axiom of choice was a typical thing that the mathematicians really needed, because it is a closure assumption that makes it is absolutely necessary for many mathematical constructions. So for example, I remind you that the vector space has only, the statement every vector space has a basis is equivalent to the axiom of choice. And of course, vector spaces of vector spaces are dearly needed in anything. What you do in how you can make function theory and so without that. Yeah. On the other hand side, of course, you have strange phenomena. I think everybody of you has knows linear algebra, and therefore you know the exchange theorem. So you can exchange the basis vectors in a vector space. Now, what you do now is you consider a vector space of the over the real numbers. So you consider the real numbers as vector space with rational coefficients. This is then the so-called Hamel basis, the basis of this vector space. Now, if you have this Hamel basis, you can do the following. You can easily, by this exchange theorem, understand that there are uncountable many non-continuous isomorphisms of the real numbers. They are non-continuous. And they do not exist if the axiom of choice is not there. And so you never can give them. So it is you can never describe this basis. So it is a very strange, thing. And so Gödel, so they were really worried about the axiom of choice. Still, Edmund Lafka, who came from that time, he was slightly older than, about the same age as Gödel. He told me that they were very worried about that. And now, what was the idea to show that the axiom of choice is and the continuum hypothesis both is consistent? The idea, extremely simple. So, first, if you want to show that the axiom of choice is consistent, you in the same way show that all the other axioms are consistent also. But do you want to know And this is difficult because of the incompleteness theorem. But do you want to know that the axiom or other axioms are consistent? No, you don't want to know. Because if the other axioms are not consistent, what bothers the axiom of choice? Yeah? There is the damage is done. There is no further thing that can happen. But we assume that the other axioms are consistent. But what is the benefit of assuming that is consistent? By the completeness theorem, the benefit there is a model. And so the idea is simply to tweak this model. Now comes the third part of the idea. The third part is under which circumstances the continuum hypothesis and the axiom of choice will be true. They will be true if there is the fewest sets possible. Yeah, and so the construction is they make from the model a model where a minimal, so to say, number of sets exists. This is the famous constructibility axiom. So he convinced himself that this assumption really implies axiom of choice in continuum hypothesis, and now you have only to show that you can really transform a model into a model of voice L, the constructibility. Again, that a talented student could do if he knows. Yeah, but Gödel found it. And that he was not really interested in mathematics, you can see exactly on that point. Because with this method, you can show hundreds and thousands of things in mathematics to be relatively consistent. Yeah? Which was done by many, many set theorists afterwards, topologists, mathematicians, but not by Gödel. He was not interested in it. Also, he could have done, because in the beginning, obviously, he was the only one who really understood his own method. But he was not interested. And this is a typical way how he was thinking. So let's go back to this Gödel logics and speak a little bit about the richness of this theory. So we have seen here the thing with the uncountability, that the compactness exactly means that the truth values are uncountable. And here we have the deduction system, which is very easy. It is simply intuitionistic logic plus A implies B, or B implies A for the infinite valued Gödel logic. And in that way, you can also show that it is axiomatized. And it has even some sort, if you know a little propositional logic, it has even some sort like a disjunctive normal form. But with a little bit other expressions in classical logic, you have such expression as x and not y, and z and so on. And here you have expression which expresses the order. So 0 less than a, less equivalent b, less than c, and so on. And the disjunction of all of this order assumption is a tautology. And by that you can easily prove also the propositional completeness simply by, if you have such an order assumption and the formula, it develops either to true or to false or to some variable in between. And in a tautology, it should always develop to true. So you could start with saying that this junction on this all order assumption is a tautology, then it is the same as all order disjunction and true. You develop it back to the formula, and then by distributivity, you factorize it out, and therefore you get exactly described here. You get the thing. Then you can also, there is in a strange way an asymmetry in this Gödel logic, namely you can describe the point 0. So non-A is true means A is 0. Yeah? But you cannot describe the point 1. And you can add an operator which describes the point 1. And this operator has a funny structure that if you look at it, it looks exactly as S4. The only difference is it distributes also over the OR. So that would describe that. And in the first order Gödel logic, you do the same. And of course, you have now to ask that the truth values are closed under infima and suprema. and you give to the universal quantifier the infimum and to the existential quantifier the supremum. And so this is all the usual. We have here now many different Gödel logics. But the really interesting aspect of the Gödel logics is, the first order Gödel logics, is that if we do not consider the strong completeness that we see entailment, then from the set of true sentences, there are only countable many first order Gödel logics. And this is an extremely strange result. Why this is so strange? Normally, in logic, you have the following dichotomy. You have either finite many or you have uncountable many. How that comes? For example, we have uncountable many logics between classical and intuitionistic logic. We have uncountable many logics between K and S4 and so on. So how that comes? That comes simply by the following observations. So we look at properties. And we say, this property holds, this property doesn't hold. So we make a binary tree. Next step, next property holds, next property doesn't hold, and so on. And so we have, if we have only finite many independent properties, then we have finite many examples. But if we have infinite many properties, then we get a binary tree which represents a real number, 0, 1, 0, 1, 0, 1, so it's uncountable. But in the case of the Gödel logics, very strangely, they are countable many. That is maybe the most strange property, a little bit about deduction systems. So the Gödel logics correspond also to something in the, for those who know, in the Kripke format, they correspond to constant domain logic. So they correspond to the linearly ordered constant domain logics of countable many worlds. There's a really interesting result by Beckmann and Breining, which shows that every Gödel logic, whether truth values are countable or uncountable, is associated with a countable Kripke frame. And the Kripke frame, so to say, associated with a standard Gödel logic over the 0-1 interval, so to say the natural one. This is simply the order type of the rationals. So let's continue. And it's also a little bit strange among all these infinite valued Gödel logics, exactly two are recursively enumerable or axiomatizable. Yes. So the two are, first, 0 is isolated and the truth values are uncountable. Second, 0 is not isolated, but every surrounding of 0 is uncountable. This, so to say, a little bit strange result is connected with the existence of perfect sets in the Cantor appendix and derivation. So it is something of descriptive set theory. Okay, so this shows the effect that how this is simply for aesthetics. This shows how the non-axiomatizable frames, the non-axiomatizable are. This result with Kripke semantics is also interesting, in a certain sense interesting, because it says that we have countable Kripke frames. And by the fact that we have countable Kripke frames, we always have the downward Skolem-Löwenheim theorem. If we start with uncountable many truth values, this is not clear. For the simple reason, as a downward Skolem-Löwenheim, so what does the Skolem-Löwenheim theorem, one of the famous theorems of classical logic, of classical model theory, not of classical logic, but of model theory says? It says that whenever a theory has a model, it has a countable model. So the Skolem-Löwenheim theorem downward can be explained simply by the fact that with a countable language you can only express countable many facts. But in a certain sense, if you have a true structure where you have uncountable many truth values, it is not clear how you prove this downwards Coulomb-Löwenheim theorem. By the way, the other direction of this Coulomb-Löwenheim theorem, the other direction makes, so to say, only the other direction makes only sense if you have identity, because otherwise it's trivial. You could always have isomorphic elements as much as you want. So the other direction says if you have a countable model, you have a model in all cardinalities. And this, if you have identity, otherwise it's trivial, this depends on compactness. Yeah, so that is easier to understand. Then we have that what I said already about the Kripke frames. So these are the things. And this was what I already said. And this is what relates them. So in a certain sense, it is a construction upsets for the specialists. So, and the interesting thing of Gödel logics is, besides that they have a quite nice semantics, they also have a nice proof theory. And in a strange way, again, you see the intuitionistic logic in them, because their proof theory is the same as a proof theory for intuitionistic logic, is the famous calculus LG, which is, by the way, a typo. So originally from the Gensen, the calculus LG should have been called calculus LI, Logikkalkül intuitionistisch in German, like LK, Logikkalkül klassisch. However, the current I is so similar to the current G, so that when printing this article, they identified the Gensen's I with G. And therefore, this calculus is called LG nowadays. So this calculus is very similar. So where you have in the intuitionistic calculus one sequent, you have now a finite sequence of sequent, a hypersequent, understood as a disjunction. And so all the rules are intuitionistic, but between the sequence you have two rules which allow you to communicate with them. So, and this is this rule which allows you to reshuffle the sequence. This is the only rule which is above intuitionistic logic. If you delete that, you would have intuitionistic logic. That again has cut elimination and everything. The only thing, and this is one of the famous problems of intuitionistic logic, it has no construction of interpolants. You cannot do that in that way. And so in the end, this would be, for example, a proof in this hypersequent calculus. So you see here in the first line, the reshuffling. That means the exchange of these heads, which go, however, from the conjunction to disjunction. So how that can be justified? By the order which underlies the Gödel logics, you see that one formula is bigger than the other, so they are always comparable. And that's a says. Yeah. So if either the P is bigger than the A or the A is bigger than the P, nothing else says this. Okay, so that's it. And this was the constant domain axiom, which is a more interesting thing, because there is the strange relation in first order calculi that normally the non-constant domain things are easier to handle, but in this linear setting it is the other way around. Okay. So that brings me to the end. And here in the end, I want again go back to Gödel. So you have seen the way how, in a certain sense, Gödel worked. So his way was really to consider ideas of thinking to the very end. I give you an example from that, which is usually suppressed in the Gödel biographies. The example is the following. When he was already in Princeton, Gödel suddenly started to took all known Euler portraits and to compare the face-nose ratio. Then he made a correlation between face and nose, and found 2 regression points. And these 2 regression points, he said, were the 2 Eulers. Yeah. So, of course, the Americans thought that he's a little bit over the edge. But this is only an example of the way he was thinking. He was not over the edge. The point is, if you take statistic reasoning seriously, then you have also to take this seriously. Either or. And so this is the way how I thought. Now you may think what was the background, what was the background of all that. What was also the background that Gödel was in principle a Platonist, as is always said, which is true. I mean, there was a very funny experience here in Brno. That was the 90 years Gödel's birthday, and this was on the university. And there were heavy bad weather coming, yeah. And Dr. Isaacson, a philosopher from Oxford, a well-known one, gave a lecture about Gödel. And when he said the words, Gödel was a structurally Platonist, the flash hit the electricity and the whole university was dark for 1 hour. So a Roman would have said that this was a sign. But so in principle, they consider Gödel as a Platonist. So what was the point underlying his Platonism? And again, something what the Americans suppress. Gödel was schizophrenic. Yeah? So he was already treated in Vienna by the most famous psychiatrist of these times, Wagner of Jaurek, Nobel Prize winner. Wagner of Jaurek got the Nobel Prize for medicine because maybe the only psychiatrist ever, but he got the Nobel Prize for medicine not for psychiatry, but he found the cure of syphilis, the first cure of syphilis. Also, this was a little bit a harsh cure. He infected the people with malaria, and then the high fever of malaria killed off the syphilis. Yeah? And then the malaria could be treated if you survived, of course. But this was in fact the only proven cure, and therefore I got the Nobel Prize. So that one, Wagner of Jaurek, Gödel's family was very, very rich. So Wagner of Jaurek treated Gödel against this schizophrenia. And now, what is the point, from my opinion, of this? And one should not speak negatively about these things. This is not a shame, it is not a guilt, but in America they don't want to hear such things. What is the point of the schizophrenia? It is not that what you usually hear, the paranoia, all these things. The paranoia, this is only a compensating symptom. The underlying problem of schizophrenia is some sort of an ontological disturbance. It is similar like you park your car in front of your house. In the night comes somebody, lifts your car and shifts it by 20 centimeters. So you come out of the house, you know something is not okay, but you do not know what. And we all have this feeling from time to time. But if it is overwhelming, that is schizophrenia. And all these paranoid theories or something, the voices and all these things, are in a certain sense a compensation of this underlying disturbance. Therefore, you could also not convince a very intelligent person that his opinions are wrong, because not the opinions are the illness, they are the compensation of the illness. And so by this, there follow two things. Anybody who suffers under this illness will have a definite interest in the ontological reality of the world. This is one thing. But the second thing is, he will develop a great logical ability in a certain sense, if he's intelligent enough, because he starts to analyze his own thoughts. Yeah? And in that sense, the illness gives strength. And you might also ask why it comes that this illness did not vanish, as it is a genetic illness, more or less. It did not vanish. So there should be, of course, an evolutionary benefit of it. And maybe it is that you are able to transgress the borders of usual thinking. Yeah, so one should not see that lightly. So that was, in some words, the way how Gödel thought, and maybe in the end, my own teacher Georg Kreisel told me once that Kreisel had the ability to become very close to the people he was interested in. That was both the Wittgenstein family, Gödel's family, and so on, Gödel's wife, for example. He said that once his brother, Gödel's brother, took him aside, and in the Gödel family they always thought that Gödel was the black sheep of the family. So the brother, Rudolf Gödel, a Medizinalrat, so a physician, asked Kreisel, seriously, did my brother do anything reasonable in his life? And so he didn't believe what the other said. And so Kreisel gave a quite philosophic answer, which could be even the epitaph of Gödel. He said he proved a small theorem similar to the prime number theorem of Euclid. And maybe that's it. Okay, thank you.
There's one up.
Well, so what you said about these ideas of this proof, I met this in several other occasions. For instance, I mentioned Grothendieck, and I think Vopenka also. And now my question is, of course, schizophrenia can help you to develop, like you said, maybe even evolutionary, something which helps you to make progress. Is this, now I would like to ask opposite implication. Whoever is such a genius and understands this simplicity of seeing this or sensing this truth, has to be schizophrenia, or maybe there are other evolutionary mechanisms which can help. For instance, I don't know, Grothendieck, if he was schizophrenic, or Vopenka almost for sure not. So
it is not necessary. It is not yeah. No. This I wanted not say. It is not necessary. Because of course you could transgress thinking in many different ways. Zen abbots do it in some way, and whatever. But what I think is really connected to schizophrenia is a certain sense of the ontological doubt, and what is really in Gödel's work, what I said during the lecture always again and again, that you have this thinking about the thinking, yeah, which is in a certain sense alien to most people, and which gives a different motivation. So, for example, the normal motivation of a mathematician is to live in the richness of the structure of in physics, to discover phenomena of the world or to prove them if you are experimental physics. But here you think about the thinking, and this I think is unusual to people, because it's very hard for normal people to constantly think about what you think yourself. So you simply think. You will not think what you think. But by this illness, you are driven to that you always not only think, but also you think what you think, because you want to analyze how you react on the phenomena. Yeah. So in that sense.
Thank you. Any other questions? If not, then we may enjoy coffee after this thought-provoking lecture. Thank you. So let me start another session. Another invited speaker is ahead of us. This lecture will be by a philosopher, Curtis Franks, from the Department of Philosophy, University of Notre Dame in Indiana, United States. And we'll hear about Gödel in 2020, hindsight, farsight, and logical blindness. Sorry, I couldn't read it.
Oh, perhaps this is not Yes, yeah, okay. Thank you all. It's such a privilege to be here and an honor. I was very, very excited to see the initial invitation, and then when I saw who else is involved, I thought it's really quite a wonderful experience. So I am very pleased to get to share with you some thoughts together with what we've heard. So I'm speaking about Gödel's discovery of the completeness theorem. I will speak mostly roundabout by describing ways of thinking that occupied his contemporaries and his predecessors in order to frame the fact that for Gödel to come to prove the completeness theorem or even begin to think in those terms was itself a huge accomplishment. I think much more so than the proof of the theorem itself is just to be able to ask the question in the way that he did. Although he may have not seen it this way, as this famous passage from the introduction to his thesis begins, after describing some of the technical framework in his dissertation, he says, when such a procedure is followed, the question at once arises whether the initially postulated system of axioms is complete, whether it suffices to derive every valid formula, or if there might be some underivable formulas that are nevertheless valid. So he says it at once arises. It's an obvious question to have once you have laid out the formal system that we're investigating. In the introductory note to Gödel's thesis in the collected works, Draben and von Heyenwert have written this: Frege never saw completeness as a problem, and it took almost 50 years from the publication of the Begressschrift to that of Hilbert and Ackermann, where the question of completeness of quantification theory was first explicitly raised for the first time. Why? And they answer, because neither in the tradition of logic that stemmed from Frege, nor through Russell and Whitehead, that is, the tradition of logicism, nor in the tradition that stemmed from Boole through Peirce and Schroeder, the algebra of logic tradition, could that question have even arisen. And here's Gödel, 1964, corresponding with von Heyenwert. Skolem, he says, could justifiably have claimed, but didn't, in his 1923 paper, a statement that looks very much like the completeness phenomenon that I proved. It seems to have remained completely unknown to him, as follows from the fact that Hilbert and Ackermann don't mention it in connection with their completeness problem. That is it, the fact that this is latent in the work of Skolem. The completeness theorem, he writes again around the same time to Wang, is mathematically an almost trivial consequence of what Skolem has done. However, the fact is, at that time, nobody, not even Skolem himself, drew the conclusion, neither from that paper nor, as I did, from similar considerations of Skolem's in other work. Jacques Herbron, working around the same time in his investigations in proof theory, went so far as to say that it's tempting to infer a certain result from what I have shown here that looks very much like a statement of the semantic completeness of first-order quantification theory. But He claimed this statement is too idealistic to make any real concrete sense, and so he kind of mentions the fact that what he had done brushes up against the completeness phenomenon by saying that he does not really think that that's a good inference to draw because it's not a sensible statement. And Gödel sums up his perspective in the same letter to Wang. The blindness of logicians is indeed surprising. We come so close to proving important things without even realizing. Gödel, looking at their work, sees how close they were. Describes this as a logical blindness. And indeed, this is Drebin and Van Heyenwoord again. If comment is a measure of interest, then the completeness of quantification theory, not only did Skolem not prove it, despite coming very close, but it had absolutely no interest for him. There's not one reference to the phenomenon of completeness in the 51 papers on logic collected in the collected works of Skolem, dating all the way through 1963. He never mentions it. And maybe it's not quite as statistically overwhelming, but if you read Ginsen's collected works, only once in the 10 papers collected does Ginsen mention completeness at all. And it's not exactly in the location you might expect. It's not in his investigations in proof theory. It's not in the following paper. So in his dissertation, the investigations in logic, Ginsen developed a system of natural deduction and sequent calculus for quantification theory. He proved their deductive equivalence with one another, as well as their equivalence with what he called a calculus modeled on the formalism of Hilbert. Now, in 1934, it was already known, this is post-Gödel, that Hilbert's system was sound and complete with respect to the standard quantificational semantics. Ginsen very easily could have inferred the same properties of soundness and completeness for his logical calculi, natural deduction and sequent calculus. But he doesn't. He doesn't reference the completeness theorem. He doesn't even pose the question. Not even in the 1938 paper that I will describe shortly does Ginsen mention the completeness of quantification theory, even though he has a section in that paper called The Exact Foundational Research in Mathematics, Axiomatics, Metalogic, Metamathematics, the Theorems of Gödel and Skolem. What would you expect to find listed in 1938 under such a heading? He says, my purpose in this section is to discuss some of the more recent findings and in particular some of the especially important earlier results obtained in foundational research in math. And he describes what's going on in metamathematics in general, decision procedures, questions of completeness of axiomatic systems of arithmetic and other branches of math, consistency proofs. And then he reviews a long list of results. Gödel's incompleteness theorem, the Levenheim-Skolem theorem, obviously, the completeness of quantification theory is a fundamental metalogical result quite difficult to omit from such a discussion, but Ginsen never mentions it. So, summing up, there are some features of the thought of Erbrand, Skolem, Ginsen, Gödel's contemporaries that either prevented them from recognizing the semantic completeness as a phenomenon or dissuaded them from acknowledging the relevance of the completeness theorem even after Gödel had proven it. You might suppose that those ways of thinking would be uninteresting to a modern logician if they could be recovered. You might even despair of the possibility of recovering those ways of thinking because, well, Gödel has introduced a new way of thinking, and so it will be hard for us to appreciate the ways that people thought before him. But I'm more optimistic. So what I want to try to do today is to describe a little bit of the history of how logicians were thinking about some fundamental concepts in logic that on the one hand prevented them from being able to pose the question of semantic completeness, even to be able to appreciate the significance of Gödel's completeness theorem when it had been proved. But on the other hand, gave them a purchase on other productive ways of thinking that are almost lost to us. Gödel attributed the blindness of his predecessors, in his words, to lacking an appropriate attitude towards metamathematics and to non-finitary reasoning. Others have suggested that the principal obstacle was that they couldn't restrict their attention to the first order case rather than higher order quantification. Van Heijenoort points this out about Frege in the Begreshrift. Moore emphasizes instead that the failure on the part of Gödel's contemporaries was that they didn't distinguish clearly between syntax and semantics. Now, each of these accounts has some validity to it, but I want to make a stronger suggestion that what Gödel calls logical blindness is somehow reciprocating. His contemporaries and predecessors couldn't see what they were so close to being able to prove because they were blind to those results. We, reciprocating that attitude, have a very hard time seeing what it is that they were focused on because we're working in the wake of the introduction of concepts from Gödel's own work. So quickly, to illustrate this phenomenon, I present a passage from Aristotle. This is from the Prior Analytics translation. I won't step through it. We're not going to analyze it. It's been analyzed. But the remarkable thing about the passage is that if you read it naively, just a gentle, straightforward reading of a translation, it sounds very much to someone from our perspective that Aristotle is announcing that he's going to demonstrate something like completeness for his system of syllogistic in the Prior Analytics. Indeed, what could he be showing in those words, if you focus on them, other than completeness? And yet, the scholarly reception of Aristotle for centuries, and even in the 20th century, when Lukasiewicz and other logicians began to take interest in reading Aristotle, they were systematically in denial that Aristotle could have possibly been proving anything like a completeness theorem there. So here's Smiley. When John Corcoran and I wrote about Aristotle's logic in the 1970s, and when Jonathan Lear did the same at the end of the same decade, we were all alert to the possibility of a completeness proof in that passage that I just recently displayed. Why did we all decide against it? The natural inference from that passage is that the intervening material represents a completeness proof. Corcoran made this very point, but he was deterred from following it up by two objections. One was that the text didn't fit his picture of a completeness proof. The other was that Aristotle wasn't clear enough about his own semantics to understand the problem of completeness. Corcoran therefore fell back on reading the chapter from the Prior Analytics in a very different way. My own preoccupations at the time, this is Smiley speaking again, led me to skip over that passage and in favor of a different one, a blunder. And Jonathan Lear made the point that it would be anachronistic to attribute to Aristotle the ability even to raise the question of completeness, because unlike a modern logician, Aristotle had a unified notion of logical consequence, not a bifurcated notion of semantic consequence on the one hand and syntactic consequence on the other hand. So how could have he even been asking that question? And Smiley gives, I think, a marvelous reconstruction of Aristotle's completeness proof from the Prior Analytics, which I won't discuss today. And in summing up, he says the following: as to one's picture of a completeness proof, it's quite true that Aristotle's proof is unlike anything one would expect. One aided with the knowledge that we have today post-Gödel. But in emphasizing the difference between Aristotle's project and the modern one, there's a danger of overlooking a similarity that seems to be more significant than the difference. So that's an illustration of this phenomenon of that I'm following Gödel and calling logical blindness. You can't imagine that you would find a completeness theorem in a work of ancient origin because the relevant concepts weren't around yet. And Gödel observed that even when the relevant concepts began to appear, people were working with them clumsily and not managing to establish the question of completeness, even sometimes to raise it, even sometimes to appreciate it after it had been proved. So what were these ways of thinking that Gödel's contemporaries had that would have prevented them from seeing what he thought was such a trivial consequence of their own work? In the 19th century, beginning with De Morgan, you find many mathematicians and logicians in their treatises on algebra and logic saying things like this. So De Morgan is describing what he calls his symbolic calculus. He lists 3 ways in which a formal system, even one whose given rules of operation be necessary consequences of the given meanings as applied to the given symbols, could nevertheless be imperfect. 3 sorts of imperfection. The last sort of imperfection he considered is that the system may be incomplete in its rules of operation. Here's his explanation. This incompleteness may amount either to an absolute privation of results or only to an imposition of more trouble than with completeness would be required. Every rule, the part of which would be a privation of results, the want of which would be a privation of results, may be called primary, and any rule that if you gave it up, it would just make things more difficult, that would be called a secondary incompleteness. So apparently he's worried both about efficiency and about actual, what we would think of as completeness, but nevertheless, he is saying here very clearly that there is a sense in which a symbolic formal system could be incomplete if it were not equipped with enough rules to get all of the results that you needed. So he has this independent notion of the desired results that your formal system is supposed to deliver. Just a few years later, also in the 19th century, Peirce asserted, I propose to develop an algebra adequate to the treatment of all problems of deductive logic. And then he said this, I'm not going to be able to perfect the algebra sufficiently to give easy methods to reach every conclusion. I can only give a method by which any legitimate conclusion can be reached and any fallacious one avoided. So he doesn't have this worry about efficiency, but he still is very clearly sensitive to a concept that we would call completeness, and even declares that his system is complete without any justification. It's unclear why he felt entitled to claim that his system was complete. Also in the 19th century, it seems that Frege made such claims about the Begreshrift, even without isolating its first-order fragment. He claims every valid inference will be recoverable in this system of concept writing. De Morgan doesn't make such a boast, but these 2 logicians and other 19th century mathematicians shared an ability to speak about the importance of logical completeness without being able to say anything about what it would be to justify the claim that a system is complete. In that same time period, we have in fact, a Czech-German logician, mathematician, philosopher, Bolzano, who seemed to have a far more robust systematic theory of logic that allowed him to pose the question of completeness in more precise, although not fully adequately precise terms, and enough that he was able to say, this would be a nice result to have, but I'm not able to find a proof for it. I think this is not a very well-known feature of Bolzano's work, so I'm happy to explain it to you and how it connects with the contemporary way of thinking due to Gödel about logical completeness, and some competing ways of thinking of his contemporaries. He was the first person, I think, to have two separate notions of consequence, a syntactic and semantic notion of consequence. Of course, the notions of syntax and semantics are not explicit in Bolzano, but we would think of them this way. He has one system of logical investigation which has to do with varying ideas and reinterpreting sentences, another system of logical investigation that has to do with strict derivation, more proof theoretic. He describes how one would establish the adequacy of the central notions in one of those realms by establishing a correspondence between the two sides of his logical system that I just described. So we'll describe the two parts of Bolzano's thinking individually and then describe his attempt to tether them together. The first side is what he developed in full in the Wissenschaftslehre of 1837, the so-called derivability relation of Bleibbarkeit. He defines a network of concepts, validity, compatibility, equivalence, derivability, all in terms of one another, very similar to how they would be done in contemporary presentations. And here's his definition of the last of these, what he calls derivability. Very complicated, but the idea is that you've got some sentences A, B, C, D, some others M, N, O, and you want to say that from the first group you can derive the sentences in the second group if you can take ideas from the sentences and systematically change the ideas that correspond with those words in a way such that anytime you make the first set of sentences true, you make the second sentence true. Obviously, his presentation of this is complicated by the fact that he has something like a multiple conclusion notion of derivability as his initial definition. But it's very, very similar, and the point has been made repeatedly that this is an anticipation of Tarskian or related notions of logical consequence from the 20th century. He says, if propositions M, N, and O would be derivable from propositions A, B, C, and D with respect to the variables, and these would just be any parts of the sentence that you could make substitutions in, I, J, etc. If every set of ideas which makes A, B, and C, and D all true when substituted for those variables also makes M, N, and O all true. That's his notion of derivability. Now, although this notion of derivability prefigures modern definitions of logical consequence in many ways, there are many, many important differences between what Bolzano's doing and what we do today. For one thing, Bolzano requires, if anything at all is going to follow from A, B, and C, that A, B, and C be mutually consistent with one another, simultaneously satisfiable. That's a foreign constraint for the notion of consequence from the modern point of view. It's also noteworthy that Bolzano is interested in propositions, not formulas, and he talks about their reinterpretations over some fixed domain of ideas, which is a more conservative notion of modality than the modern one, where we not only change the extensions of our predicate symbols and constant symbols, but we also change the underlying set of objects. And finally, the individuation of ideas with respect to which you can vary your interpretation is made very imprecise by Bolzano's focus on propositions rather than formulas, on concepts rather than symbols. Nevertheless, the modern notion of consequence is not conceptually distant from Bolzano's on any of these points, and it can be meaningfully seen as just an adjustment of his definition. We still want to draw a contrast, though, between what Bolzano is doing and the modern notion of logical consequence. Even if technically one can be seen as a refinement of the other, there's a major difference in the sort of relationship that Bolzano thought he was describing and the sort of relationship that the contemporary logician thinks of describing. The logical consequences of a formula, according to the contemporary understanding, are determined just by the existence and the details of certain structures, quite independently of our access to them or our ability to draw inferences. Bolzano, though, and I suppose he discloses this a little bit by using the word derivability to describe his notion of logical consequence, thinks of his relation as somehow procedural. There's nothing out there over and above particular deductions that we might perform that determines any special relationship between propositions. In his preferred terminology, the relationship of derivability doesn't correspond with an objective dependence of propositions on one another. It's just the case that we're able to obtain immediately from the known truths of some sentences the truths of some others as well. It's somehow anthropomorphic. It's a human procedural-centered notion of derivability. Now, of course, Bolzano isn't claiming that propositions only stand in this relationship with one another after someone's actually carried out a deduction. It's somehow still supposed to be a real eternal fact, whether or not that relationship exists. So what's the point of saying that the relationship is only subjective, that a truth obtained in this way is a mere conclusion, not a genuine consequence? Bolzano's point is that he's wanting to distinguish this concept of derivability from the other half of his logical theory, what he calls the theory of ground and consequence, the Grundlehre. That's where he thinks objective dependency lies. So in an earlier work of his, he describes that second half of his way of thinking in full detail. And here's a characteristic passage. He goes on repeatedly like this, but in the realm of truth, a certain objective connection prevails, which is independent of our recognition of it. As a consequence of this, some of these judgments are the grounds of others, and the latter are the consequences of the former. To represent this objective connection of judgments, that is, to choose a set of judgments and arrange them one after another so that a consequence is represented as such, and conversely, seems to me to be the proper purpose to pursue in a scientific exposition. Instead of this, sometimes people are usually only worried about coming to know things with certainty or to strengthen their conviction rather than to describe the actual dependency structure of thoughts. This consequence relation, which Bolzano calls Abfolge, is at the center of a robust philosophical account of mathematical truth, and it has many, many consequences. For example, according to Bolzano, a proof has to track the objective ground-consequence relation between propositions, and therefore individual mathematical truths can have at most one proof, the real proof. That's what he means by a proof. And people who have read Bolzano know that a big part of his mathematical career was just taking results that had already been proven and to come up with what he thought were better proofs. This is the concept that's driving his idea of what makes a proof better. Earlier proofs maybe assured us of the truth of a proposition, but they didn't uncover the objectual grounds of that proposition. And that's what my proofs will do. This was Bolzano's mission. And another consequence of his way of thinking is that the division of mathematical truths into those that have proofs and the basic truths for which no proof can be given is not a matter of conviction, but it's some objectively determined reality that we could discover. What are the real axioms? And The distinguishing features of an axiom, the thing that doesn't need proof, according to Bolzano, is not its self-evidence. It may be very hard to find out what the axioms are. Instead, it's the ontological role it plays as ground for other truths, and the absence of it having any grounds of its own. And, most importantly for Bolzano, the self-evidence of a fact is no reason not to seek a proof for it, because the proof will uncover its grounds, which are typically unrelated to the reasons we have for accepting it as true. So that's what's driving Bolzano, and you might reasonably wonder why this imagined network of objective relationships should be what he thinks of as the proper focus of a scientific exposition, rather than just the discovery of mathematical facts. And he tries to defend this. He says, look, there's just some value in coming to discover the hierarchy of facts. What rests on what depends on what are the ground and consequence relations. That's part of the world that you would just forever be in the dark about if you didn't pursue this line of inquiry. There's also, according to Bolzano, an aesthetic value to proving things the way that he wants to, because you get some kind of anticipation of what today we think of as a subformula property. In his terminology, if you track the objective grounds of a truth back to axioms, then you'll have a proof of that truth in which no foreign concepts ever enter. You'll only have concepts that are native to the result itself anywhere in your proof. And he also said that the conceptual purity of his proofs would somehow facilitate the discovery of new truths. It's a little bit unclear why he believed that. But those are the three merits that he thought that this perspective would give. So in developing this second half of his logical theory, the ground-consequence relation, Bolzano advanced logic in ways that are comparable to the advances he made with his derivability relation, but oriented in a completely different direction. So he makes this claim in an early work, 1804. I must point out that if I believed I could not be satisfied with a completely strict proof if it were not even derived from concepts which the thesis proved contained, but rather made use of some intermediate concept. Always some sort of, this Greek means passing from one species to another. That proofs should be free from such intermediate concepts, and the, what he calls atrocious detours in reasoning, was inspired by a desire to capture the objective ground and consequence relations in the world, to produce proofs that were topically pure and therefore free from circularity. But the significance of this notion of analyticity that Bolzano is developing isn't tied down to those, perhaps, peculiar ambitions. Bolzano distinguishes in his development of the ground consequence theory analytic and synthetic truths in ways that are similar to what are known from Kant's criteria of conceptual containment for analyticity and synthetic truth. And then later, he extends this to a distinction between analytic and synthetic proofs. And he calls a proof analytic if its derived formula contains in its compound concepts all the simple concepts that appear elsewhere in the proof. Remarkably, Bolzano suggested that the whole difference between these two types of proof, the analytic and synthetic, is based simply on the order and sequence of the propositions in the exposition. Thus, Bolzano rediscovered the ontological burden that he placed on proofs reflected in a rather mundane feature of the proof's written appearance. You just have to do some proof transformation in order to take an arbitrarily given proof and turn it into one that is analytic in this sense. And he develops a theory of proof transformation just along those lines. In doing so, of course, he has to specify, and it's perhaps underappreciated, but it took a very long time for the world of logic to develop propositional inference patterns and to distinguish them from syllogistic reasoning. Bolzano was very careful to make this distinction. So he, for example, gives a rule for conjunction and says, here's an example of an analytic type of rule. Notice that it's reversible. You get a valid inference reading it from bottom to top or from top to bottom, but the ground consequence relation only goes one way because the simpler sentences are the grounds of the compound conjunction sentence. And he illustrates a few of these and then observes, you notice that the syllogism rule, and here he means like propositional syllogism, it's not reversible in this way. Its premises are not in any way going to follow from the conclusion the way that the conclusion follows from the premises, but the analytical rules each are. And for this reason, the reverse of any analytical rule could seem like another kind of inference. But again, it won't have the ground consequence structure to it. So in the Beiträge, Bolzano argues for this claim. If you have several propositions appearing in a scientific system and they have the same subject, then the proposition with the more compound predicate has to follow the one with the simpler predicate and not conversely. Moreover, he says, it's obvious that we cannot extend our assertion further and instead of saying the proposition with the more compound predicate, put the more general expression, the proposition with the narrower predicate. So what's happening here? He's wanting to make some claim that you'll always be able to prove things beginning with simpler ideas and building your way to more compound ideas. But he notices that his rules for inference, they pick out syntactic data, conjunctions and sub-sentences and things like this. Whereas conceptually, things could be narrower or broader, but not linguistically represented by things that are narrower or broader, could be broken apart like that. This was a major obstacle in establishing the kind of general results that he wanted. In other words, Bolzano recognized that his proofs, because their propositions are ordered so as to track the objective ground consequence relation, would have a form of what we today call the subformula property, were it not for the ubiquity of the syllogism rule. But even with this rule, every proof has a related property. Given the normalization techniques that we discussed, that Bolzano himself developed, typical proofs may generally be written so that they begin with several syllogisms devoted to establishing the simple truths that you need to get started, followed by purely analytic rules to the compound consequence. And I'm going to skip a little bit about Laplace and Lagrange to describe this type of fixation on analyticity in the 19th century. Today, we just reflexively associate the proof systems with mechanical procedures, and we think of what Bolzano called derivability, the substitution of terms to see in a modal sense which things must be true in an interpretation in which some other things are true as a notion of consequence. And we ask the question, can our mechanical procedure of derivability correspond with all of the consequences that can be demonstrated in this way? We wonder whether our formulas are adequate to their intended interpretations, whether these mechanical procedures in fact trace the interrelationships among the objects of our researches, these latter being the original objective. Bolzano could only have things the other way around. His theory of ground consequence revealed that the analytic calculus traces facts back to their ultimate constitutive grounds. And he shared a suspicion with Laplace and other analysts of the time that these same dependencies might be inaccessible to geometrical or other traditional mathematical inferences. Should one side of the divide prove inadequate, it could only be the latter, the traditional mathematical methods. This rightly being designated as mere derivability because, in Bolzano's words, by abandoning oneself to the operations of analysis, one accesses the objective dependencies among truths. So whereas this ground consequence relation holds only between truths, false propositions may stand in the relationship of derivability with one another, according to Bolzano. And for this plain reason, you can't conclude from the derivability of some proposition that you've uncovered its grounds, very plainly. But more crucially, you also can't reach that conclusion even when all the propositions in a derivation are true. This is evident from the fact that derivability is obviously reflexive and symmetric, whereas according to Bolzano, no truth is its own ground, and no two truths could mutually ground one another. So in Bolzano's idiom, this derivability relation is not subordinate to the ground consequent relation. Just because you've established that some claim is derivable from another, you have not established that either is the ground of the other. But given the nature of these relations, the converse question seems more relevant. Is every ground consequence relation representable for Bolzano as a derivation? If not, then the very idea of placing this conception of logical consequence at the center of all scientific exposition, as Bolzano wants to do, is puzzling. Whatever the merits of knowing the objective grounds of a mathematical fact, no science can be devoted to this task unless you have a method for discovering the grounds. And on the other hand, if from the grounds of a truth, if from its grounds a truth can always be derived, then this process-centered derivability relation could be seen to be an adequate way to trace these objective dependencies. So Bolzano was naturally very interested in this question, and he devoted section 200 of the Wissenschaftslehre to answering it. Here's how he explained the point. If truths are supposed to be related to one another as ground and consequence, they must always, one might believe, be derivable from one another as well. The relation of ground and consequence would then be such as to be considered a particular species of the relation of derivability. The first concept would be subordinate to the second. But this seems unlikely. Why should the ultimate reasons for all the truths of mathematics always be related to them so that from consideration of the variation of ideas in each, one can reliably infer their way from them to their objective dependencies? Why should the formal features of propositions give us any access to this metaphysical reality beyond? Very few contemporary writers share Bolzano's confidence in our intuitions about this realm of objective dependencies. But even Bolzano recognized the unconvincingness of speculation on this issue. Probable as this seems to me, he concluded, I know no proof that would justify me in looking upon it as settled. So Bolzano asked something that we could very much appreciate today as a type of completeness question. I have the ground consequence relation on the one hand, I have the derivability relation on the other hand, and I would like to know that all these ground consequence relations are in fact derivable. Of course, his whole schematic seems backward to us because his ground consequence relation is the anticipation of our mechanical proof procedures, and his derivability relation is an anticipation of our abstract set theoretical notion of logical consequence. And so it seems that he's asking the opposite of the completeness question. But at least he is asking a question. He sees it as something that shouldn't be taken for granted, how to tether these together. And he asks it maybe not fully precisely, but precisely enough to be able to say clearly, that he doesn't know what the answer is. It's a clear question that could be answered, and he doesn't have an answer to it. Now, the whole focus that is driving all of this for Bolzano is very suspect. Logic's blind to considerations of truth, to say nothing of ultimate explanations for why some statements are true. Indeed, Bolzano's own development of this derivability relation was a turn away from factual truth, towards distinguishing statements that could be true from those that couldn't, towards thinking about which statements rise and fall together, rather than what the world is actually like. Mathematics, he wrote, concerns itself with the question, how must things be in order that they should be possible? Unlike metaphysics, which asks how things really are. But in the end, Bolzano was very driven by this notion of objective grounding, and his theory of derivability, if it can't be shown to trace the world's ground consequence relations, it loses much of its scientific interest. Modern logicians, by contrast, have no expectation that their craft is going to uncover ultimate grounds. Many don't even believe in such things. So what remains of Bolzano's scheme for writers who don't share his metaphysical aspirations? There are two distinct ways forward from the impasse that Bolzano found himself in. The first one is the one we're familiar with. It involves reversing the entire dialectic, uproot the relations of derivability and ground consequence from their metaphysical setting, and ask not about the adequacy of the first to capture the second, but ask instead whether the proof calculus, which no longer is subject to constraints of analyticity, can always be used to deduce from a set of formulas the formulas that are true in every interpretation in which the first are true. That's Gödel's way forward. And of course, it requires considerable modification of Bolzano's fundamental notions. But there's a second way forward from Bolzano's impasse, and it's much more natural. You think again about the relation Bolzano called derivability. Think of it now as an abstract consequence relation. First, project this relation into a proof system directly, so that a single logical system has analytical logical rules living side by side with rules encoding the abstract consequence relation. Then just continue pursuing Bolzano's project of proof transformation to see if the steps in a given proof of this system can be systematically rearranged so that the entire proof is transformed into an object with no occurrences of the second type of rule, the rule that encodes the notion of logical consequence. Whereas on the first path, Gödel's, completeness is proved by bridging the divide between Bolzano's two realms, now reconceived as the syntactic and the semantic. On the second path, the chasm that Bolzano dug between his two branches of logical theory is filled in before the completeness problem is made precise, by formalizing the consequence relation within the same deductive system that houses the logical rules. And this second path is the one that Ginson chose. His first two fundamental theorems together constitute a completeness result according to the scheme of projection and elimination just described. So people are familiar with Ginson's work on cut elimination, I think less familiar with his earlier work on sentence systems. My belief is that when you look at his work on cut elimination together with this earlier work that I'll describe, you can appreciate cut elimination as a way of proving completeness according to the second path forward from Bolzano that I was just indicating. So in Ginson's first paper, he describes what he calls a sentence system, sentences of the form M arrow V, where V is an element and M is a complex. Complexes are just non-empty sets of finitely many elements. And Ginson defines satisfaction for these sentences. If you, a complex, the same kinds of complexes that appear as parts of sentences are also the kinds of objects that satisfy or fail to satisfy sentences. A complex satisfies a sentence if it contains its succedent element, or if it fails to contain one of its antecedent elements. And then we have only two rules of inference that he calls thinning and cut. And he defines a proof as just a tree, a finite tree of thinnings and cuts, where the top nodes are what he calls tautologies. These are sentences whose sole antecedent element is the succedent element. And Ginson proves three theorems. The first two I'll describe now. He says that my proof system is correct. If a sentence is provable from some other sentences, then it's a consequence of them. Now, what's this notion of consequence? It's the notion of consequence that very much is an anticipation of Tarski. Ginson borrows it from Paul Hertz. Just to say that a bunch of sentences have another sentence as a consequence of them if every complex that satisfies those sentences also satisfies that other. So again, it's an anticipation of Tarski, but it's also a continuation of the notion of derivability due to Bolzano. So I can prove, if I can prove something, then in fact the proved thing is a consequence in that Bolzanian, Tarskian sense of the premises. And as you would expect, Ginson's statement of what he calls informal completeness is a converse of this result. He says if a sentence is a consequence of some other sentences, then it's provable from them. Ginson established informal completeness in Theorem 2, where he also, in fact, shows that proofs of a certain normal form suffice to exhibit all consequences among sentences. Normal proofs are just cut followed by one possible ultimate use of thinning in the final inference. So Theorem 2 says if a sentence is a consequence of some other sentences, then there's a normal proof of it from those other sentences. And his point was that the pure notion of logical consequence is at once simple, uncontroversial, easily enough specified to be captured formally by a logical calculus, and the soundness and completeness results of this 1932 paper are the proof that his formal definition of provability does just that. That proof system embodies or captures the notion of logical consequence directly. He calls it informal completeness and informal soundness because he doesn't describe it as a coordination between a semantic notion of consequence and a syntactic notion of derivability, but as the formalization of an informal notion. So he takes this notion from Bolzano of derivability, and he says that's informal, it's imprecise, but I will tether it down to a formal proof system. And that's what he does. And I'm running out of time, so I'll quickly just indicate that the idea of a sequent calculus for Ginson, which we're all familiar with, was to map the expressions of pure predicate logic onto the elements of this proof system. So instead of them being elemental now, they will be propositional formulas. The rules of cut and thinning stay as they were before, and then Ginson adds new rules for analysis of the logical symbols as they appear within the individual elements. And these are familiar rules for us. But the point is that cut here has been proved by Ginson in 1932 to be the embodiment of the concept of logical consequence. It's now domesticated. It lives side by side together with these other inference rules that have a logical character to them. According to Ginson, the cut rule is a complete formalization of the pure notion of logical consequence. It's by far the most widely emulated pattern of reasoning used in math, so the mathematical thought is predominantly synthetic in nature. But the cut elimination theorem shows that all mathematical thought that doesn't rely on the principles of any specific mathematical theory can be simulated with purely analytical reasoning. And just to conclude, I'll mention this. In the same 1932 paper, Ginson proves the following. If a non-trivial sentence Q is provable from the sentences P1 through PV, then there exists a normal proof of Q from them. It's illuminating to contrast Ginson's comments about this normalization result with the approach that he takes in the interesting where he proves cut elimination. After all, if you think about the cut elimination theorem, there's a very simple proof of cut elimination that Ginson doesn't give. You could just say everything that is provable is, of course, valid because of soundness, and everything that is valid has a cut-free proof because of the completeness of the cut-free system, and therefore everything that's provable with cut is provable without cut, because I go from it being provable to it being provable without cut. Very slick and simple cut elimination result. Ginson doesn't do this for well-known reasons, but maybe for also an unwell-known reason. Because here's what he says about this theorem 3. This theorem 3 follows at once from theorems 1 and 2 together, because I proved soundness and then I proved informal completeness for normal form proofs. The theorem can also be obtained directly without reference to the notion of consequence by taking an arbitrary proof and transforming it step by step into a normal proof. The reason the approach chosen in this paper is that it's much easier. Why do all that work of proof transformation? It's a tedious exercise. By following that same line of thought, Ginson could have established the correctness and completeness of the forms of inference of the calculus LK simultaneously with the elimination of its cut rule. And of course, the relevant observations were technically and methodologically within Ginson's reach in 1935. But the fact that LK and its cut-free fragment are sound and complete is guaranteed by the proofs in section 5 of their deductive equivalence with Hilbert's calculus, and the template for inferring such normalization results in that way, it was right there in Ginson's own 1932 paper. But we wouldn't want to say that Ginson was blind to the fact that he could have proceeded that way, or that he was blind to semantic completeness. Because on Ginson's conception of logic, the parallel between the sequence theorem 1, theorem 2, theorem 3 of 1932 and the sequence soundness of LK, cut-free completeness of LK, and cut elimination, it breaks down. Because theorems 1 and 2 of his earlier work, those were his verification that the notion of logical consequence is fully analyzed by the cut rule. Because the notion of logical consequence appears again in this exact form in the immanent features of the sequent calculus, the question of the completeness of that logical system wasn't for Ginson a question about how that system corresponds to something beyond itself. Instead, it was a question about the ability for the analytic fragment of that system to keep up with its internal consequence relation. If you think of cut elimination as the completeness of analytic methods with respect to the synthetic notion of consequence, then the idea of inferring the cut elimination theorem from semantic completeness just doesn't arise. And in conclusion, I'll leave you with this quote from Goldblatt. As mathematics progresses, notions that were obscure and perplexing become clear and straightforward, sometimes even achieving the status of obvious. Then hindsight can make us all wise after the event. But we're separated from the past by our knowledge of the present, which may draw us into seeing more than was really there at the time. And I'm only adding that when we look back at work of Gödel's contemporaries or his predecessors, and we, like Gödel, see maybe more than was there at the time because of the benefit of hindsight, we also might be missing that they were seeing something that we no longer are able to recover. They may have had very robust and viable ways of thinking that made it impossible to ask the questions that we now ask so reflexively. If there's one achievement that we can isolate in Gödel that has been underemphasized because so many of his achievements have been so widely celebrated, it's that he introduced ways of thinking to us that today we struggle to even imagine one could live without. But when you see that Gödel's own predecessors lived without those ways of thinking, and very productively in ways that prevented them even from asking the questions that he answered, you realize what tremendous gift Gödel gave us by giving us those questions that we can answer. Thank you.
Thank you. Two questions. Sorry, I didn't notice which one was first.
So, there is, of course, something of a blindness that you did not mention, because Gödel, in a certain sense, underplays what he did. So one important aspect of the blindness is the following. There is a completeness proof for propositional logic of Berne's 1918. And this was the ground for this appearance of the completeness problem in the Hilbert Ackermann. Now, what was the point here? Berne simply transformed any tautology in a conjunction of disjunction and recognized that there should be a dual atom there. Yes, otherwise it's not valid. And from that you can make a proof. And this was also the problem. So they could not find such a thing for first order logic as it would imply decidability. And so Gödel separated the thing from the decidability by his inversion, by saying that a consistent set has a model. And in a certain sense, technically seen against the Hilbert group. This is the argument.
This is exactly correct. Another detail, in 1917, 1918, in Hilbert's own lectures, he already was posing the completeness question for quantification theory. Most of the Hilbert Ackermann is just a redaction of notes from his lectures in those years. But another important difference between the propositional case and the case of first-order quantification theory is that you no longer have the maximality criterion of post-completeness being equivalent to completeness. This seems to have been maybe not an obstacle for Bernays, but for Hilbert at least. If you read Hilbert's own presentation of Bernays' completeness proof for propositional logic, he says, but now we need to prove it in a precise form. The same result, and he gives the maximality criterion of post-completeness formulation, and it seems that Hilbert was somehow allergic to the free-flowing semantic notions that he wanted to be pinned down to this concept of post-completeness, which of course is not available, as Ackermann showed, once you're in quantification theory. So that was another aspect of the blindness, but it very much fits with what you're saying.
Yeah, you have been saying that it's hard to recover how people were thinking then, but I think there's still a tribe of logicians that think that way, namely the Martin Luthians.
No, for sure.
So
that is true.
So there are two, and I think there's really probably two aspects. So the first thing is that certainly Frege most clearly was thinking of validity as a relation between contentful judgments. So for him, the idea of the schematic thing was simply blocked. And if you look at Frege-Hilbert correspondence, Frege is saying to Hilbert, you're not thinking about the propositions you seem to be thinking about, but about second-order propositions in which you could recognize the quantification over models that we have in second order, that we have in the our current understanding of what's going on. And so there's this one thing, so the relation between judgment, and there's the other thing, Bolzano, that reasoning should be grounding, right? That's not, I don't think, so much present in Frege, but if you look at Martin Luff, they have both things, right? So
I think that's right, yeah.
So they have very empathically, they always emphasize that it's a relation between judgments that they're looking at, and well, they're conditional judgment, that's a kind of refinement coming from Gensen. And the second thing is that they're producing this realizing object, which is, I think, could be viewed as the Bolzanian ground. So, in some sense, yeah, I know all this because I've talked. My neighbor is Göran Sundholm, and I've been talking to him a lot. And so I think he is a kind of, you could view him as flashed from with a time machine to our time and interview him to at least understand a number of the things. And he definitely thinks, of course, that something was lost.
Oh, without a doubt,
Yeah.
right.
Yeah.
I'm wanting to emphasize here just an achievement of Gödel as its tribute to Gödel, but the duality of that is that there is a lost world, as you say, not completely lost. In general, I think that many people working in structural proof theory are sensitive to thinking of grounding between judgments as the primitive basis of logical inference, and even of thinking of cut elimination as a type of consistency, of completeness result. I think even Girard says subformula property is the real completeness. This is a way to think, right? So this is not completely lost, but predominantly neglected.
Yes. Okay. So I have a comment exactly on this point. So viewing like cut elimination as a completeness. So we know about some strange phenomena nowadays it's called ST phenomena. It's called strict tolerant logic. So it's a trivalued logic in which you take the antecedent of a sequence to be true and the consequent to be not false. Okay. And we know that this logic is representable in a sequence style system, LK, without cut. So cut is not a valid rule, but we have all the classical validities.
Mm-hmm.
So I mean, like this makes me think about this kind of reversal project that you had in mind in the Gensen terms. I mean, in this way, like so. There are people debating about whether this is really classical logic or not, because it's classical logic at the level of the inferences maybe, but not at the level of meta-inferences. So if you have, because transitivity at the level of meta-inferences, which is cut, right, is not valid. But it's not, it's just that you, like from a semantical point of view, you block this. Because if you look at the cut elimination, like the possible cut, I mean, nothing changes, it's just LK. Maybe with some labels saying, okay, this is strict, this is tolerant, but then you don't have like this cut. So I was wondering about this. So maybe in this case you see like a kind of like semantic first approach in a way that seems not to fit with I don't know, with the picture.
Yeah, I will just say quickly that I find it very interesting. I will talk to you about it some more. I don't have a ready answer to the question of it though. Yeah, thank you for this.
Pardon?
Short remark from
Professor
Baz.
That's possible.
Because in the end, there's also some blindness which hit Gödel himself, because you should remark that in the thesis, the compactness is not stated. Right. That most trivial but most important consequence of the completeness theorem,
Very
only
good.
in the publication.
Very nice remark. Yeah.
Thank you very much, and apologies for cutting the discussion. Let's make a short break of less than 15 minutes and come back for the contributed talks. And before that, let's thank the speaker again. And our first speaker is Eriola Rossa from Munich, from the... it should be. You have to push it further.
Further?
Wait until it's clean.
Ah, okay, okay. It's not any...
It's the Center for Mathematical Logic.
Yes, yes, yes. Maybe shall we try it again? Okay. Maybe I'll just use the other mic.
So anyway, it's from the Center for Mathematical Logic in Munich. And he's going to talk to us about informal probability and its logic. Hopefully we can hear him. And if not, you can...
And use this one?
You can use this one?
Okay, yes. Okay, okay, I hope you can all hear me. So first of all, thank you for having me here. Yes, today I'm going to talk about also the consequence of a little paper by Gödel. It's almost just one page. And it's about interpretation of propositional intuitionistic logic in S4, what is now S4. And we will follow some basic intuitions and see where they lead us. So we will make an assumption, basically the assumption of the fact that concepts related to informal probability are captured by S4 modalities. We will employ this concept from a formal side, so as embeddings in S4, but also from an informal side as BHK kind of interpretation for this logic that we will characterize then. But this is just a preparation work for something, I guess, more interesting, which is a kind of BHK interpretation for classical logic validities and an embedding in S4, and that we will use to construct a particular kind of natural deduction calculus that has some properties that we will see. So, first of all, from where like this absolute probability or informal probability kind of, thank you, okay, so I guess I can switch. Yeah, okay, it's working. Thank you. Sorry for this. So, as we said, this paper by Gödel, and there is some other two papers that I wanted to cite. Meal about conception of proof in general, and Lightgibb on informal and formal probability. So we are going to make this. So first of all, informal probability. So we are talking about probability in some kind of theory, which is not better specified, or absolute probability. So probability in a general sense, of what we would like to have in terms of desiderata from a theory that maybe extends arithmetic, but of course it cannot be, since we have in S4 the T axioms, which is clearly causes problem with incompleteness theorems. So the intuitive reading of box A will be that there is a proof of A in some sense of being a proof, since the system, as we said, is like informal. It's not defined the kind of deductive relation that we have. But I mean, since it fits very well with our intuitions, the axioms for S4, we can ask about the other operators. So diamond, not box, not diamond. So what kind of concept, if any, they characterize? So first of all, like there has been some work on this. So for example, Fitting in his translation for classical theorems in S4, we are going to see a lot of proof of embeddings and embeddings. So this is more or less the kind of embeddings we are going to see. So we place operators in front of each subformula of the formula that we want to translate. For example, in this case, we obtain a weakly faithful result in terms of classical logic. So S4 under this translation proves all the theorems of S4, not all the validities. For example, a counterexample is transitivity. Transitivity is not provable if it's not taken as theorem, if it's taken as validity. So basically there is no deduction theorem in this. And in this case, fitting treats diamond as an informal consistency operator. So you have something like each subformula that is provable and consistent gives a formula that is, if it's a theorem, is provable in S4 and in the classical logic, if only if. So what kind of thing we can have with this kind of operator? So it's convenient to put them in a kind of square of opposition, just for a matter of representation. Clearly, it's a modality, so we can do this. So we will have like probability. So if box A, then there is a proof of A. Consistency. So if we have diamond A, then there is no proof of not A. Refutability in the sense of there is a proof of not A. And unprobability, so just there is no proof of A. And this clearly like fit in the square of opposition. So we have all the subaltern, contrary, and contradictory relations that we would expect. And we are going to try to characterize for each point a different logic, in the sense that if we take probability logic, the logic of probability in a sense is intuitionistic logic, because if we take box A as an embedding for S4, we obtain intuitionistic logic, and we will see if it's possible to do the same with the other logics. We also like think about BHK interpretations for the other logics, and we are going to trick around these elements of BHK interpretation. So construction in the case of the usual BHK interpretation with intuitionistic logic, probability, logical constant clauses, and the concept of species, which kind of more or less is the same of having variable domain semantics. So if we characterize the logic of probability from BHK interpretation, so we have this idea of constructions that prove, for example, A and B is proved by the construction C, if and only if it has this form, and C proves C prime proves A and C double prime proves B. And then we have like the most important one, I guess, is the construction C. There might be, we could say something about what Gödel thought of this particular kind of clause. But for now, it's just like the construction C proves A implies B. If C is a general method of construction, such that applied to an hypothetical construct C prime that proves A, C the function C with the argument C prime proves B. So it's a kind of functional interpretation, and so on and so forth. The other maybe interesting one is that the one for all x A, in which we have this general kind of method of construction, such that given any individual A from the species under consideration, which will, like, if we translate this into Kripke semantics, will be the domain we are considering, CA proves AA. And so this is the embedding we was talking about. So we can put a box in front of each subformula, and we will obtain from S4 intuitionistic logic. And this is a system for intuitionistic logic. We have seen this before in the previous lectures. It's just LJ, and this is a system with just at most one conclusion. This is what characterizes LJ or LE, LI, sorry, as it should be said. And so how are we going to prove these embeddings, this one and the next one? So one direction is the trivial one. So we show that every rule of LJ is derivable in LKS4, which I will show is a system for S4 modulo the box this translation. On the other side is a little bit more complicated, but still it's still kind of easy. So we show that every LKS4 derivation of a box translated sequence is equivalent to a single conclusion derivation, given cut elimination as a formula property that apply for this system. And therefore, the only box translated provable sequence are single conclusion ones. And because of this, we have also this corollary. So if you enrich intuitionistic logic with S4, and we are still under the same kind of translation, we still prove intuitionistic logic and nothing more. So LKS4. This is just LK enriched with these rules, and you can have an idea of the proof by looking at this. So for the box on the left side, there is no problem. You can put it whenever you want. But from the box on the right side, you can only put on one formula. The other formula would be diamond, but we don't have diamond formulas given the box translation and given the subformula property, so we can just forget about it. And there is a way of getting from each derivation a kind of normalized derivation in which there is only one conclusion, and this proves this side of the theorem. So what about the other logics? So for example, refutability. So the propositional part for this has been showed by Schramko in a recent paper, and it's actually kind of easy. So the refutability was on this side. There was the negated diamond part, and it's kind of straightforward if you look at the interaction between negation of the diamond and the negation on the formula that we want to prove. That we get something like this. So we have more or less what we would expect, except for the implication. If we have to treat as we have to use in this case a co-implication, which is basically the negation of an implication. And this basically works using the same strategy as before, and just having this co-implication that basically works in this way. So we take A implies B, and we give it this this premise, and we take A co-implies B, and we have this premise. So we just switch the things, and this is how we get the rule for this one, for this operator here in S4, in LKS4. So how does the LDJ system look like? It's a system with a single premise. So it's basically almost perfectly it's actually perfectly the symmetric of LJ. And you have like this co-implication here that does exactly what I showed you. So what about the other logics? Exactly as you would expect, the diamond one kind of just distributes, and you have like the implication that is respected, and the negated box one again like switches to this kind of co-implication. What the kind of logics are this one? These are the LJ without implication would be co-implication, which is actually a defined operator. So you just define it as A and not B and A. And in the case of LDJ implication, you take out the co-implication from DI, from the dual intuitionistic logic, and you define it as not A or B. And you have these rules, which are the non-Ketonen version of the so-called non-Ketonen version of the intuitionistic logic rules, for example. And these are the consistency one and unprovability logics, if you want to call it in this way. I'm open to suggestions from what regards the terminology, because I'm still not sure if it's the good one. So here are the translation schemes represented. So as we saw, like there's a natural correspondence here for box and diamond, and for not diamond and not box is a little bit different, just with this kind of operators. But everything else stays the same, especially for what regards atoms. It's really interesting, I think. And yes, so we can try to put this in a kind of square opposition again. I mean, this is not really informative, just to present it, because really we have here only propositional theorems. Actually, if you want to have just theorems that intuitionistic logic, the fact that intuitionistic logic theorems are derived by dual intuitionistic logic with implication theorems, we would have to add something as the dual of KF, which is this axiom that says that, I mean, from the perspective of dual intuitionistic logic, which will be something as the dual in a Kripke frame, that an endpoint sees the root of the model. And the same thing goes for this logic here. We would have to have KF so that the root sees an endpoint. So yes, and we have this kind of translation here that they can bring us to from intuitionistic logic to dual intuitionistic logic, and from dual intuitionistic logic with implication to intuitionistic logic with co-implication. That works really easily. So we have just to swap antecedent and consequent, and then we have to swap and with or with and, implication with co-implication, and universal with existential, and so on and so forth. As we saw that there is this dual Grivenko theorem for DI implication. So DI implication proves A if and only if C proves A, as we saw basically for the case of fitting for A propositional. And we have still these corollaries. So we have that, as we saw before, if we enrich with S4 intuitionistic logic, we still can prove that under this translation it doesn't prove nothing more than intuitionistic logic. We have the same thing modulo the different translations or for the other logics. Okay, so all this result lead us to something that I guess is a little bit more interesting maybe. So first of all, like semantic intuition about this. So if we take the semantic clauses in a Kripke semantics for the implication of this kind of for these logics, so we have the intuitionistic logic is the usual one. So we have like for all the words that the maybe the root point or whatever point sees, and then we have to put to evaluate the implication at this point of evaluation, at all the points of the evaluation. Whereas for example the logic of consistency, so this DI implication, we go the other way around. We are in an endpoint because it's actually the antitone. We have to go from the endpoint, and we kind of have to find a way out in order to reach the root of the model. So in a way it's kind of dual. And of course we have increasing domain for the logic based on intuitionistic logic and decreasing domain for logic based on dual intuitionistic logic. So from this respect, I tried to give a kind of BHK interpretation for this logic of consistency, for this dual intuitionistic logic plus implication in terms of abstraction. I mean, I'm not super happy with the terminology, but still. So abstraction would be this kind of dual of construction, in the sense that we abstract from the kind of information that we have up to a stage in which we didn't have them, and we have exactly the dual of the logical process that we had before. So the abstraction A does not refute, because what we really want is like not provable, not A. So it does not refute A and B if A, sorry, it's not S. A is of the form I A prime with I either 0 or 1, such that for I equals 0, then A prime does not refute A, and for I equals 1, then A prime does not refute B. And this is basically the same the logical clause for the disjunction, but in this case it applies to the conjunction. The one for implication kind of remains the same, but it's actually derivable from the one for disjunction, and the one for negation that stays like the strong one. And yes, we have, like, for example, for negation, the abstraction A does not refute not A if and only if A is a general method of abstraction, such that for an hypothetical abstraction A prime that does not refute A, the abstract A of A prime does not refute bottom. So as you would expect in this case. So what does this lead us? Why this might be interesting is because if you take this kind of translation, you have a nice embedding of classical logic into S4. Classical logic, I mean classical validities. And how does this work? So basically you put a box in front of each subformula, except for the implication, in which you put a diamond here. You switch to this diamond translation, which is this one. So every time you have a box and you have an implication, the antecedent of the implication switches to the other one, and the other way around. And we have here that gamma under this implies A under this translation. And these are all classical validities, but this is actually not classical logic because of a simple fact, which is this one. So we cannot cut A under the translation of diamond, which would have a diamond here, and A under the translation of box, which will have a box here. And this is basically the same phenomena I was talking before when I did my question to the previous speaker. This is the case of a classical logic that has classical validities but doesn't have a cut definable or a cut that is valid. And this is some studied phenomena. Girard thought about it. The first was Schutte to come up with this kind of system in a tree-valued system. So what we can do now is to kind of mix up these two BHK interpretation in order to give an account in terms of probability and consistency of the thing that we saw before. So we have like the construction C proves A implies B. If C is a general method of construction such that applied to an hypothetical abstraction now. So we kind of like look now at the other way around, so at an abstraction that does not refute A, then CA proves B. So you have this kind of interplay between these two things. And I mean, this I think is already interesting, but I wanted to see more. I wanted to see if this kind of intuition actually makes some sense. And I guess the benchmark for this kind of stuff would be natural deduction, in which, for example, BHK interpretation represents more or less the introduction rules. And so I went to natural deduction, and especially for what concerns BHK of DI implication, there is a nice proof system by Luca Tranchini, which is dual to NJ in the same way as LJ is dual to LDJ implication, and I kind of mixed that. And in LDJ you have this kind of assumption that go from bottom, and still you have the one from intuitionistic logic that go from up to the bottom. And if you combine this, you have a nice proof system for classical logic that actually has only only subformulas appear in the derivation, and usually it provides a tremendous speed up. So, for example, this is a proof for the consequentia mirabilis in this form. So it doesn't suffer from the fact that it's a theorem and it could have been proved already in, for example, in dual intuitionistic logic plus implication. And the same goes, for example, for this theorem, which is the theorem that intuitionistic logic cannot prove even in the first order, given that this is a limitation of the dual negation implication in the first order, the double negation translation in the first order level. And this kind of seems to correspond to one conclusion system for LK. One conclusion because it's basically minimal logic, but enriched with this explosion rule. And with this kind of rule, actually, this kind of rule tells us that we can always contract in this kind of, we can do this kind of meta contraction into this. If you have here P implies P and we have here P implies P, then we have Gödel logic, actually. But this is for classical logic. And this seems that this system here as it's a multiple conclusion systems. Of course, we take like multiple conclusions that are equal as only one, so we kind of implicit contract, but we always do this with natural deduction. And in the same way, we will have like some kind of multiple conclusion that are the same here, and we will contract. And yeah, that's it.
Questions, comments?
What happens if you replace S4 by Loeb's logic or S4 Grigorgic?
S4, sorry?
S4 Grigorgic.
I haven't thought about that. I only saw that maybe S4 plus this KF axiom, that the one that gives you not for all x, AX or not AX, gives you this kind of more interesting kind of square of opposition. But I haven't thought about that. I'm talking with Matthias Batz before. Apparently there is this S4 translation with box only for Gödel logic only on the level of atoms, and I'm wondering what happens with the diamond at the level of atoms, like if there is this kind of correspondence as well. And yeah, there are some steps still to be seen, but yeah, not on the the diamond translation. The only thing that I've seen was Schramko, but then like not much interest about that. And also I think like very intuitionistic logic can be interesting in its own way. I mean, like thinking about maybe, I don't know, dual heighting arithmetic or whatever. Maybe it could be interesting. I don't know.
Thank you. If there are no more questions or comments, perhaps there'll be some over the lunch. So let's thank the speaker again, and let me invite the next one. Thank you.
Works, okay.
Okay, so our next speaker is Piotr Blaszczyk from the Pedagogical University of Krakow, in Poland. And he's going to tell us something about the modern alternatives to Cantor's theory of infinity. And the floor is yours.
Thank you. First, I'd like to thank the organizers for this chance to present my talk at this charming observatory. I have never imagined have a chance to project my slides on a horizon-like screen, so it's great. Now, as for the very word alternatives, it doesn't refer to any non-classical logic or alternative set theory. In fact, I will present you 3 alternatives to Cantor's theory develop within the framework of standard Zermelo-Fraenkel theory. So to develop alternatives, we do not need alternative frameworks. As you know, Cantor introduced 2 kinds of infinities, cardinal and ordinal numbers. Each case has its own arithmetic and its own relation greater than. In both cases, the set of natural numbers makes the yardstick of infinity, be it the cardinal number Aleph 0 or ordinal number omega. As regards the structure of finite numbers, it is the structure of natural numbers as regards Cantor. And as for the rules for the arithmetics of finite numbers, these are the rules or just axioms for an ordered field. And as you know, Cantor seeks to transcend this structure and transcend its arithmetic. However, the arithmetic of his infinite numbers hardly mimics the arithmetic of finite numbers. The addition and the product of ordinal number is not commutative. The addition and the product of cardinal numbers is not compatible with the order. Cantor believed, he realized this defect, and he believed it is because of the special nature of infinite numbers. In the famous paper, in 1947 paper of Gödel, What is the Cantor Continuum Problem, Gödel explicitly presents Cantor's cardinal numbers as extending the system of natural numbers, and seeks to show that this extension can be effected in a uniquely determined manner. And to this end, he discusses definition of cardinal numbers, the equality, order, and operations of sum and products. Sometimes it happens in mathematics that a definition is founded on some theorem. It's not the case as regards the arithmetic of infinite numbers, so Gödel's arguments are in a way heuristic arguments. However, let's have a look at his arguments. Gödel claims that Cantor's definition of infinite numbers really has this character of uniqueness, since whatever number is applied to infinite sets may mean it has to be based on a one-to-one correspondence. As regards equality and order, he claims that there is hardly any choice left but to accept Cantor's definition of equality between numbers, which can easily be extended to a definition of greater and less for infinite numbers. And as for the arithmetic, as for the sum and product of ordinal, just should be cardinal numbers. Gödel writes, it becomes possible to extend the arithmetical operations to infinite numbers and to prove practically all rules of the computation. No, man, you cannot prove this rule. There's no way. And in what follows, I will address two issues. The first one regards the arithmetic of ordinal numbers. As we know, in modern developments, cardinal numbers are reduced to the specific ordinals. And secondly, I will show you how to measure infinite set with means of different kind of infinite numbers, different than the Cantor's cardinal or ordinal numbers. In fact, it will be non-standard natural numbers. The point is how to assign non-standard natural numbers to infinite set. So the plan of my talk is as this. First, I will remind you, I guess, the Heisenberg normal sum and products of ordinal numbers. The ORD here stands for the class of ordinal numbers. Then we'll sketch you an idea of the field of surreal numbers. The acronym ONAC here stands for On Numbers and Games. It's the title of the book in which John Conway developed the idea of his surreal numbers. And then the very recent development of Benchi-Dinasi of numerosities. That's the idea how to assign non-standard natural numbers to countable sets. Here you can see that the framework of ONAC, or those surreal numbers, provides the most general framework for the theory, because the class of ordinal number with the operation defined by Heisenberg can be inserted into the field of surreal numbers. Benchi-Dinasi numerosities are also included in this structure. And this idea, Euclidean numbers, with this idea, Benchi-Dinasi tried to transcend the idea of the numerosities and try to show how to assign a specific numbers to the subset of real numbers. I will discuss this specific point here in this talk. So, let me start with the first alternative, which concerns the alternative definition of sum and products for ordinal numbers. In fact, it's as old as 100 years, and it's based on the theorem proved by Cantor. The theorem reads that any ordinal number can be represented, and that's the point, in a finite form, as presented here. These coefficients are natural numbers. And based on this representation, we can define, Heisenberg defined so-called normal sum and normal products. That's the index n stands for the word normal. So when alpha and beta are represented in a finite and, let's say, a polynomial-like form, we can add this coefficient just like dealing with polynomials, and we define products in a way similar to the product of polynomials. And now, these operations are commutative and compatible with the order of ordinal numbers. And in fact, this structure here, to remind you that ORD stands for the class of ordinal number, mimics the structure of natural numbers as regards the arithmetic operations. And now, in 1967, John Conway developed an idea of now called Conway numbers or surreal numbers. In fact, it is an ordered field, and it is the biggest ordered field, which means that any ordered field can be immersed in this structure. The field of fractions is there, the field of real numbers is there, and so on and so on. And what's the most interesting is that also this structure, let's call it Heisenberg, can be also immersed in this structure. And in fact, it's my own result in this whole presentation. I won't present you the details. Let's have a look at this. ONAC contains all ordinal numbers. However, now these numbers are in the structure of ordered field. So when we have an omega, and it is an element of an ordered field, so there is also in the field of surreal numbers minus omega numbers such as this, half of omega, the inverse of omega. It is not the case that any ordered field is closed under the square root operation. However, the field of surreal numbers is. So we also have the infinite number, the square root of omega. To repeat, it is because the omega is an element of a ordered field of surreal numbers. John Conway developed his idea beyond the limits of standard mathematics, beyond the limits of Zermelo-Fraenkel theory. Happily, I found a set theoretical representation of Conway numbers. The idea was developed by Henry Gonscher in 1867. And Gonscher provides a very easy representation for surreal numbers. So let's take any ordinal, classical ordinal number, and any function that goes from omega to the set of two elements, let it be plus and minus, it could be 0, 1, doesn't matter. And any such a function function is a surreal number, and now ordinal numbers are represented by the alpha length sequences of pluses here. And here you've got, here you can see representations of these strange numbers. Here is the omega, minus omega, omega minus 1, half of omega, and the inverse of omega. Let me go back to this slide. Here you can see the inverse of omega. And in fact, the idea that the infinite numbers are inverses of infinitesimals, because it is infinitesimal in the field of non-standard number, and vice versa, that inverses of infinitesimals are infinite numbers. So the very idea was explicitly stated in the middle of 18th century by Leonhard Euler. And you might find it interesting that the idea was developed in the book called Analysis of Infinity, Introduction to the Analysis of Infinity. This is the most famous book of the 19th century. And you may find it interesting that all throughout Cantor's papers and his letters, there are merely few references to this book. 5, maybe 4 references to the most important book of 19th century, in which the idea of infinite numbers are inverses of infinitesimals is developed. Let's go. And now, so here is the field of Conway numbers. As I mentioned, is the biggest ordered field, so it includes hyperreals, real numbers, all the class of ordinal numbers, and also non-standard natural numbers. And in the next part, I will deal with this structure, because in fact, these are the so-called numerosity as developed by Benzi Ignacio. This idea was developed in the very recent book of theirs, and in this paper they developed the idea how to assign, let's say, Euclidean numbers to subsets of real numbers. I will present you the idea of numerosity. Numerosities are in fact non-standard natural numbers. And here's my presentation. Benzi Ignacio developed the theory in a different way. Okay, so here you can see symbols of ultra-power construction, octa-power extension of a structure. I guess all you are familiar with this technique. With the same technique, we can extend the structure of natural numbers and real numbers. Here, as a result, we get the model, non-standard model of piano arithmetic. In fact, it is uncountable model. When the starting structure is the structure of real numbers, as a result, we reach the hyperreal numbers. In both cases, the construction is the same. We define relation, equivalence relation on sequences of natural numbers or sequences of real numbers. U here stands for non-principal ultrafilter. Operations are defined pointwise, and the total order in this way. I assume that you know all this stuff. One interesting point is that when we try to represent standard real number or standard natural number, it could be represented by the constant sequences. However, when the sequence is constant starting from some index on, it also represents the same number. It's presented here formally. And now, Benchi and Venatio call this theory alphanumerosity, and alpha is this number represented by the identity sequence. And due to the previous definition, alpha square is just this number. The half of alpha is this number. The square root of is this number. However, this number or this number belong to the field of hyperreals. They are not non-standard natural numbers. And here is the operation of the floor. It's also defined pointwise. And now this number is non-standard natural numbers, and the floor taken from the square root of alpha is also non-standard natural numbers. And here is the basic definition. I will write it down for those who are skillful and would like to check the examples I will present in the next slide. It's the cardinality. In fact, this set is always finite, and this function says how many elements of the set A are smaller than n. Now, the measure alphanumerosity of this set, and to be clear, I'm dealing only here. Here, I'm dealing only with a subset of natural numbers, just to get you the idea of numerosity. So, the numerosity of the set alpha is the non-standard natural number defined, represented by this sequence. How many elements in A are less than 1? How many elements in A are less or equal than 2, and so on, and so on. And now a few examples. What's the numerosity of the finite set? It's like in the standard theory. Here is an example. The A has 2 elements. These are number k and l, k. So the function this will work like this. For any n that is smaller than k, we've got zeros. When we meet k, the value of fe is 1. And for sometimes there will be the same ones. And when we go to the number L, the value is 2. And from that index on, there will be all 2s, 2, 2, 2, 2, and 2. Which means that from this index on, this number is represented by a sequence like this. It doesn't matter how it looks like on a finite set. From this point on, they are all 2s, which means that this sequence represents number 2. With the analogous reasoning, we've got that when the A has k elements, his numerosity is k. So we does not violate our standard intuitions. How about the bigger infinite sets? So the numerosity of the set n is just the number alpha. We can how many elements in the set n are that are less or equal to 1 element? how many elements are there that are equal to two elements, and so on and so on. So that's the alpha. And now the most interesting, the numerosity of the set of even numbers is this sequence, and in fact is this number. The numerosity of this set, I mean the set of squares and so on, is this sequence, and in fact it is this number. And here are some general rules. When A is a subset of B, its numerosity is smaller than. So this rule agrees with our, let's say, everyday intuition. When a set is smaller, set A is smaller than B, smaller in terms of inclusion, its numerosity is also smaller. It does not happen in Cantor's theory, as we know. And here we've got this also obvious rules. So it looks like that these numerosities behave like finite numbers. Okay. And now some conclusions. In Cantor's theory, any subset of n can be either finite or of cardinality of other zero. There are no alternatives. There are no ordinal numbers also in between finite numbers and omega. The numerosity of any infinite subset of n is less than alpha and greater than any finite number. It can be shown that the numerosity of infinite subset of n is represented by infinite non-standard natural numbers. So that as regards subsets of natural numbers, it's clear, and that's all.
Questions, comments?
Please, can be the concept of numerosity also apply for uncountable sets?
This idea is supposed to be developed in this paper. As far it's not clear for me, so that's the project. That's the work in project, as regards me.
I'll bring it.
Uh-huh. Here the universe of this field is not a set, it's a class, proper class, and in fact there is a theorem with a proof. Okay.
So what happens if we vary the ultra filter? So for example, are there examples of two sets of natural numbers where for the one ultra filter the one is smaller than the other and the other way around?
Mm-hmm.
So if you go through non-standard models, then the numerosities will differ, right?
Okay. In what way it affects the numerosity? For example, the number alpha, depending on the ultra filter. Where is this? The number alpha could be, let's say, even number or odd number. Right. It depends on the ultra filter. Yes. Okay, we can, in a way, control it. In a way, we can control it.
I can see no hands rising up, and that's not so good for the speaker, but maybe the questions will come up during the lunch, which is ready outside. But before that, let's thank the speaker again.
Can you hear me? Yeah. Okay.
Jo?
Nahrávání.
No, zvuk audacity.
Okay, so one small technical announcement concerning tomorrow's trip. In order to speak in the time, we will have to start a little bit earlier than it's written in the papers which you obtained. So we start at 8:45 with the first talk, and everything is shifted by those 15 minutes. Therefore, we will leave right after the third lecture and go down to the church. There will be bus, and which leaves at 10:30, and then we will go to the trip. Those who are accommodated at the hotel, bring your luggage with you. So the bus will take it with you to the hotel where is the end of the walk and the trip, and then there is the conference dinner, and then you will take the luggage from the bus so that you don't have to go here or to the hotel where you stay. So that's about tomorrow. And
when will we finish?
Finish what?
Tomorrow.
The trip will finish at noon, and then is the lunch. Any other questions? Okay, so.
Thank you, Jan van Leek. Can you hear me? I think yeah. Hey. So, dear participants, esteemed guests, ladies and gentlemen, as all of you certainly know, the title of this conference is Tribute to Kurt Gödel. This afternoon, however, we are going to honor and pay tribute to Petr Vopienka. This is no way a contradiction. Petr Vopienka was a great Czech and Czechoslovak mathematician, logician and philosopher, a charismatic teacher, a founding and leading personality of the Prague School in mathematical logic and set theory, who made a remarkable contribution to several topics Kurt Gödel had been interested in and working on, most notably to the problems of independence, of the axioms of choice, and of the continuum hypothesis within the standard axiomatic systems of set theory. More specifically, this afternoon the Kurt Gödel Prize will be awarded by the Kurt Gödel Society in Brno upon Petr Vopienka in a memoriam. And there hardly could be a better choice for the first recipient of this award. Petr Vopienka influenced at least 3 generations of Czech and Slovak scholars, and his students are spread in many universities not only in the Czech Republic and Slovakia, but also abroad on both sides of the Atlantic Ocean. His work counts more than 2 dozens of volumes, but even more impressive than its extent is the depth and originality of the ideas he introduced and elaborated on. No less admiration deserves the right artistic beauty of his books and essays, manifested both in his brilliant literal style as well as in his masterly wielding Czech language. He was firmly convinced that a genuine, profound and authentic philosophy worth its name can be carried on just in the mother tongue of the philosophizing person, and he expressed this his opinion on several occasions. That's why I am viewing the fact that the celebration is held in English and not in Czech and Slovak, that is in the intimately akin native languages both of the speakers as well as of the majority of the listeners, with some bewilderment, as however little and innocent but still an embezzlement upon his heritage. I hope that he, when watching and listening us now from heaven, will understand this gesture of politeness towards our guests from abroad and forgive us generously. I hope he does. Some few years ago, I gave a lecture in Brno. Maybe some of you were there present. The lecture in Brno about Petr Hopenka and my personal relation to him and his work, based on my article which appeared in the Czech Philosophical Journal in an issue dedicated to his memory in 2016. I tried to assess his work and ideas by referring to the 3-degree classification of genii introduced by the Polish writer Stanislaw Lem in one of his fictitious reviews of non-existing books, which appeared in Czech translation in 1983. The book, maybe some of you have read it, was titled The Perfect Emptiness in Czech, Dokonalá prázdnota. So according to Lem's classification, genii of the third class are those who succeed to be recognized and receive appreciation already during their lifespan. Genii of the second class during their lives are ignored or viewed with suspicion in the better case, but more frequently they are persecuted, arrested, expelled, interned in mental houses or even sentenced to death. Nonetheless, their contributions recognized and honored by the next or by some of the following generations. Finally, according to Lem's hero of the fictitious book under review, there should and even must exist genii of the first class, creators of such original and profound ideas and coming up with such groundbreaking discoveries that will never be understood and recognized by the rest of the mankind. Obviously, Hopenka fits partly into the third of Lem's classes. However, I am sure that later generations will appreciate a pretty large piece of his work which escaped recognition of his contemporaries, placing him partly into the second Lem's class as well. And due to Hopenka's intimate relation to the Czech descent, if there did not come the Czechoslovak Velvet Revolution in 1989, much less of his work would move from the second class to the third one. During my lecture, I repeated some arguments from that article, too lengthy and delicate to recall them at this occasion, that some of the most ingenious and profound of Hopenka's ideas and contributions may never become sufficiently understood and recognized and will remain lost for the mankind forever. In other words, Hopenka at least partly belongs to Lem's first class of genii too, at least in my opinion. I think that this my short introductory note is sufficient for a preliminary general acquaintance with the personality of Petr Hopenka to this distinguished audience. 3 highly competent speakers are ready to follow me and present 3 different aspects of his life and work. All of them are former students and collaborators of Petr Hopenka, and they have known him very well. Lev Bukovský from the Masaryk University in Košice, Alena Vencovská from the University of Manchester, and Kateřina Trlifajová from the Center for Theoretical Studies of the Czech Academy of Sciences and the Charles University in Prague. Our first speaker, Professor Lev Bukovský from the Masaryk University in Košice, is going to deliver a talk titled From Topology to Set Theory. Please welcome.
Ladies and gentlemen, I should like to thank the organizer for the invitation to present this lecture.
It is a great honor for me to speak about the work of Petr Hopienka. He was one of the persons who strongly influenced my life and my professional career. Petr Hopienka studied mathematics at Faculty of Mathematics and Physics, Charles University in years 1953-58. The supervisor of his master thesis was Eduard Čech. The main result of his master thesis was the theorem stated below. Actually, Petr Hopienka was the last student of Eduard Čech. So, topology knows more than 3 definitions of dimension of a topological space. Small inductive dimension, large inductive dimension, and combinatorial dimension. There are definitions of those 3 dimensions. I will not read it. The classical result says that for separable metrizable space, all those definitions give the same result. The small inductive dimension is equal large, inductive dimension equals to dimension, combinatorial. The famous problem formulated by several topologists included Petr Sergeyevich Alexandrov in 1935 was the question whether the equality holds true also for compact topological spaces. Petr Hopienka in his master thesis proved that it is not true. Negative answer that for any integers m less than n there exist compact topological spaces with different inductive and combinatorial dimensions. Petr Sergeyevich Alexandrov was the very famous Russian topologist. He was student of Luzin, and in 1966, during Prague Topological Symposium, I heard in a discussion that Petr Sergeyevich Alexandrov said that Hopienka is topologist. He so appreciated his result. In March 1960, Professor Eduard Čech died. Petr Hopienka began to take part in the seminary of Ladislav Svante Rieger, devoted to mathematical logic and set theory. In working in the seminary, Petr Hopienka obtained very soon non-trivial results about models of set theory. People say that he was decided to solve continuum hypothesis, and there was main problem that Gödel showed constructing model in which continuum hypothesis holds true by taking the necessary set, the small possible universe. And to show consistency of negative of continuum hypothesis, you needed to find some new sets which are not in this minimal model. So there were 2 solutions, either to start with countable model and then you have enough set outside, and another was actually this attempt made by Petr Hopienka. Petr Hopienka preferred to work with the Gödel-Bernays axiomatic of set theory. He was mainly influenced by Gödel's work and the fact that this axiomatic is finite. He constructed a model of the Gödel-Bernoulli set theory by ultra-power and showed that this model is often non-well-founded. That was very important. That was the first non-well-founded model of set theory. Moreover, constructing this model, there was enough subset of natural numbers outside this model possible to add and to obtain negation of continuum hypothesis. Then, using a well-founded model constructed by a measurable cardinal, Petr Vopinka presented a very nice proof of a recent result by Dana Scott that the existence of measurable cardinal is incompatible with the Gödel's axiom of constructibility. Again, in February 1963, Ladislav Svante Rieger died. So, Petr Vopinka became the leader of his seminary. Actually, Petr Vopinka established an essentially new seminary. In October 1963, with the exception of Petr Vopinka, the seminary has just 2 members with finished university, Petr Hayek and me. The other members, at least 8, were the students of mathematics at Charles University. The members of the seminary were strongly influenced by the enthusiasm of Petr Vopinka for the set theory. The work of the seminary was very, very intensive. In the academic year 1963-64, the seminary started with special domains of set theory and of the theory of models of set theory. The recent result of Petr Vopinka about ultra-product models were deeply studied in the seminary. Then, let me remind you that during the session of the seminary, Petr Vopinka usually sit down by the last table, of course with ashtray and cigarettes, and let the session go without his interruption. When he say something, that was actually at the end of the seminary, preparing the new program. In 1963, Petr Vopinka obtained the manuscript of Paul Cohen paper on the independence of the continuum hypothesis. Paul Cohen used countable model for to have enough set aside for adding a new subset of the set of integers. Petr Vopinka immediately began to study the Cohen's paper, trying to find some new ideas. He was successful. He led with his new version in the seminary. New versions, not one. Some 2 or 3 versions were read without finishings. Before finishing the reading of the version, Vopinka brought new version of the paper. Finally, in April 1964, Vopinka in his seminary led presented paper in which the independence of continuum hypothesis of the Gödel-Bernoulli set theory was proved. The topologist Petr Vopinka considered some Kloppen subset of the generalized Cantor space as forcing condition. Actually, he has defined the Boolean value of a formula in this forcing as an open subset of this Cantor space. The universe of the model was an ultra-product of generalized Gödel's structure of the constructible universe by Levy and András Hajnal. Ultrafilter had to contain all open-dense subset of this contour space. Full paper was published Russian in Commentatio Mathematicae Universitas Caroline in 1964, English translation in American Mathematical Society translation in 1966. In the next years, Petr Hopienka obtained a fully new topological version of constructions of models of the set theory by sheaves of function over a topological space. The main parameters of the model was the topological space and an ultrafilter containing all open dense sets. Then he presented his result at Warsaw University, and a Polish mathematician Czesław Ryonarczewski remarked that Hopienka de facto works with a complete Boolean algebra. Those who know something about topological spaces and regular open subset can understand that open subsets modulo ultrafilter, which contains all open dense sets, are actually regular open sets, and they form a complete Boolean algebra. Though the theory of Boolean valued models of the set theory has arisen, the obtained results were published in the paper General Theory of Nabla Models in Commentatio Mathematicae in 1967. Independently, in same time, American mathematicians Robert Martin Soloway and Dana Stewart Scott have built similar theories of Boolean valued models. Boolean valued models are still the main tools of showing relative consistency of some sentences of the set theory. In years 1930, 63, 68, Petr Hopienka obtained also another non-trivial result in set theory. Let me mention some of them. This Karol Hrbáček showed that the existence of a strongly measurable cardinal is incompatible with a generalization of the axiom of constructibility V equal L of A for a set. That was a very strong generalization of Dana-Scott result. Then Petr Hopienka constructed a new proof of the Gödel's second incompleteness theorem. With Petr Hájek, he has built the theory of permutation submodels of the delta models for showing independence of the axiom of choice. With Bohuslav Balcar and Petr Hájek proved the consistency of the axiom of choice by so-called hereditary ordinal definable sets. Independently, some 4 years later, that was Myhill, American mathematicians, Myhill who obtained same result. Moreover, Hopienka shows that some result about about extension of the universe and hereditary ordinal definable says that they are generic, that means by forcing. That was very important result. As a joke, Petr Hopienka formulated today called Hopienka's principle. This principle plays today an important role in the theory of large cardinals. Important role played a result with Baltzar. You have two inner models of set theory, one with the axiom of choice, then which have same sets of ordinals, then they are equals. That means that the inner model with the axiom of choice is uniquely determined by its sets of ordinals, or more comfortable, by its subset. That was the basic idea of the theory of semisets. The simplest model of semiset is as follows. Let M be an inner model, elements of R are called sets, subset of R are semiset, and subclasses of R of M are classes. By Baltzar-Poppenka theorem, the whole universe is uniquely determined by sets and semisets. Sorry. In 1972, Peter Poppenka and Peter Haig published the monograph, The Theory of Semisets. The monograph contains several important results of the set theory formulated in the language of semiset theory. The translation from language of semiset theory to the language of set theory is very easy. I present two important results of the monograph. There was more results, but I present just two. The first very important is as follows. Let M be an inner model. A subset of this inner model M is said to be a support over N if for any two binary relation R1, R2 from M there exists a binary relation R such that the image by this relation of this sigma is equals to the set theoretical difference of R images by R1 and R1 and R2, where the image is defined below. Then he showed very important theorem. If sigma is a support, then the extension by sigma is a generic extension. That means there is a forcing such that M sigma is equal to the extension of M by this forcing. Later, both of Baltzar find a very nice proof of a strengthening of this result. Baltzar showed if sigma subset of P from M is a support, then there exists a preorder in M of the set P such that sigma is directly a generic filter on this preordered set P. If M is an inner model, Peter Poppenka, the other result is, if M is an inner model, Peter Poppenka defined the boundedness axiom. Boundedness means that any subset of M can be written as union of a subset sigma, where subset rho, where rho is subset of a set in M of small cardinality. There is very important condition. And then he proved proved very nice theorem that V is a generic extension of M if and only if there is such a kappa that bounded with kappa holds true. Also formulated similar condition about approximation, and I succeeded later to show that similar theorem holds true, that with generic extension if and only if for some kappa this approximation condition holds true. This result became to be very important the last years, since in the study of so-called mathematical genealogy alebo geography, in study of different or structure of inverse model. Unfortunately, people were afraid of the language of semi-set theory, and those results remained unknown. I will not comment the very detailed style of presentation of the monograph. Just I recommend you to try to find and to understand the above-mentioned result in the monograph. It is quite difficult. In 2014, at a conference in Novi Sad, I presented a simpler alternative proof of my old result. In the proof, I have used the notion of support. Several participants were surprised. What is it? After my lecture, a prominent topologist and set theorist came to me and asked me what I did speak about. He never heard about such a result. So this time I decided to publish this paper, and with explaining the notion of support in the Baltzar-Bopienka theorem. The report of the reviewer was very positive, that he considered it as a very interesting paper, since the West did now those results. Now I present a part of the report of the reviewer of the part. You can guess who is it. The Czech schools work in the theory in the 60s and 70s is not readily accessible in the West. Personally, I found the paper both useful and interesting, mainly because presenting the Bopienka result. Finally, I should like to present the most important consequence of the Bopienka's work in set theory. Bopienka built a strong school of set theory in Prague. Košice School of Set Theory is a product of Bopienka's seminary as well. Petr Bopienka was a teacher, but he didn't behave as a teacher. He was a friend with great influence on the members of his seminary. The members of the seminary have obtained already at the end of 60s several strong results in set theory. The Prague seminary was well known over the mathematical work with its result. I will finish with presenting alphabetic order of the most important members of the seminary and therefore Bopienka's students. Bohuslav Baltzar, me, Petr Hájek, Tomáš Jech, Karel Hrbáček, Karel Príkry. He studied in Warsaw, but took part in Prague seminary, Antonín Sochor and Petr Štepánek. Thank you for your attention.
somebody wants to remark something or add? If this is not the case, so let's have our speaker, Professor Bukovsky, again. Really interesting contribution, and perhaps could somehow assess the extent and depth of Opěnka's influence. So let me invite the second speaker, who is Professor Alena Vencovská from Manchester, also a student of Petr Opěnka, belonging to a little bit younger generation, but certainly not the last one. And she will speak about the alternative set theory and new infinitary mathematics. So that another chapter of scientific work of Petr Opěnka and his collaborators.
Okay, so first of all, thank you very much for inviting me. I'm very pleased to be here. I will speak about the next stage in Opěnka's mathematical career, and that means about 1970s. I studied at Charles University in 1974 to 79. So I met Peter Opěnka while the later part of the time. By mid-1970s, Peter Opěnka became rather concerned about the work in set theory which he was doing, because he stood quite firmly on the position of Platonism or mathematical realism, and he really needed his mathematics to be about something which at the time meant about some true set theoretical universe. But because of the number of independent principles which had been identified, and in spite of enormous effort put into it, lack of intuition which would help people to decide between them, it was felt that he felt that the foundations of mathematics needed rethinking, and that we should go back to the basic principles for what we are doing. It was also a time when he was exposed to strong influence, philosophical influence of the phenomenological school in Prague. In the peculiar atmosphere of the communist Czechoslovakia, it happened that there was a philosophical seminar going on in his group. He actually sheltered a philosopher, Jiří Polívka, as was mentioned yesterday. So every week the seminar met and read Husserl's writing. And Opěnka found in phenomenology strong inspiration. Phenomenology, as you know, has been mentioned several times here already. And it's a program initiated by Husserl at the beginning of the 20th century. He calls to abandoning our assumptions about how we arrive our concepts and going back to experience and scrutinizing phenomena of the natural, real world, as Opěnka came to call it, that the world of our experience, where we experience phenomena. And it is important to keep in mind that this is not meant to be about some subjective experience. It is about what we can find is in common in how we perceive the world. So it's about some intersubjective experience And Bopenka took this quite seriously. In fact, I should mention, because it is this forum, that he has this in common with Gödel, who I believe had 3 philosophers which he considered as the most important ones for him, and it was Leibniz, Kant, and Husserl too. So going back to Bopenka, in this context, he found the most important phenomena to consider for thinking about new foundation of mathematics, those of horizon and indistinctness. He believed that our intuition about infinity comes from considering large collections which are indistinctly defined, namely sub-collections of possibly distinctly defined finite collections, but sub-collections which are defined indistinctly. So this is perhaps best illustrated by pictures, because Bopenka's favorite examples were something like milestones around a long straight road, where we can distinguish few individual milestones to start with, and after that, if we make an effort, we can, with each milestone, distinguish the next one, but yet we can't distinguish them all. In this picture, I put a picture of sleepers on a railway line, where the same phenomenon can be observed. Or Bopenka quoted the sand heap example, where we might consider the numbers of grains of sand which we can consecutively remove from a heap of sand one by one, as long as we still have a heap of sand remaining. So it is the case again that with each grain of sand we remove. We can, whilst we have a heap of sand remaining, we can remove another one, and it's still the case that it remains, but when we remove them all, there's no heap of sand, it disappears somewhere in the process. So this was the sort of intuition Bopenka quoted when he emphasized that that theory went sort of wrong with being a theory of infinity. It went wrong in the sense that it placed the infinity beyond all the natural numbers, how the infinity should be somehow placed before some big finite numbers. So, based on this consideration, the most important points about intuition for the new theory were these. So, in our new theory, we should have those collections considered countably infinite that can represent paths towards the horizon. Horizon here, according to Bopenka, should be understood as a general limit of perception. As we talk about it, we usually sort of have in mind some sort of visual limit of perception, but this was meant to be quite general. Another important point about this is that these paths to the horizon, which we can see, experience, have the property that they always continue a little bit beyond the horizon. It's not the case on those pictures I had there before. The horizon is some strict boundary where the path disappears. Although it cannot be seen by the observer, the path to the horizon continue in the same way a little bit beyond. Finiteness should be associated with collections, only those collections that can be distinctly and individually surveyed, so those collections on which we cannot see this phenomenon of infinity in this sense that there would be some sub-collection which blur at the horizon. And finally, infinite collections, more generally, should be those that cannot be distinctly individually surveyed. So it would mean that if we attempted, we would identify some paths to the horizon, so they contain some countably infinite sub-collections. Surely, when Bopenka considered this intuition, he would be thinking about a way in which this could be modeled in the standard set theory. Undoubtedly, he was well aware that this in a way corresponds to models which like non-standard omega saturated non-standard models of arithmetic, of cardinality, alpha 1. So the mathematical possibility how such a theory could be formulated and be shown relatively consistent with respect to ZF, that's really clear to Bopenka, even in very sophisticated contracts. So he not only did elementary analysis in it, but also some results in functional analysis and so on. So Robinson's theory was welcomed by mathematicians with great enthusiasm. In particular, Kurt Gödel wrote at one point that non-standard analysis is the analysis of the future. So there are great expectations that infinitesimals will make a comeback and be rehabilitated and be used in mainstream mathematics. However, this wasn't happening. So going back to Bopenka after some detour, this closeness of the theory which we imagine can be proposed to formulate the intuition which he had in mind, and Robinson's non-standard analysis, which clearly worked very well for introducing infinitesimals, gave Bopenka encouragement to hope that his alternative set theory will enable a comeback of infinitesimals. So now, with all this inspiration, Bopenka came in 1979 with alternative set theory, which formally could be described as follows. So it is a theory with sets and classes, where all sets are also classes, but not vice versa. Sets satisfy axioms which are equivalent to axioms in Cerno-Frankel set theory without the axiom of infinity. Saying this, of course, doesn't do justice to Bopenka's theory, because the axioms for sets are very elegant in the alternative set theory, but it can be expressed like that, and probably just to get across what properties they have, this can do. So all sets in set theory behave just like finite sets in classical set theory. Now, there are not only sets of classes which are not sets, so a proper semi-set is defined as a class, such that it is not a set, but it is a subclass of some set. And obviously, to distinguish the theory from set theory, classical set theory, Bopenka has an axiom that there is a proper semi-set, and finite sets are defined after it. That should be finite class. A finite class is a class which has no proper sub-semi-set, it necessarily has to be a set. Okay, so to continue describing roughly the alternative set theory as proposed in 1979 in Vopenka's book. Vopenka, as is usual, defines natural numbers in it, namely by a set by von Neumann definition. So the natural numbers in alternative set theory form a class which he denotes N, and the finite natural numbers form class which he denotes as N. So as a consequence of the existence of proper semiset, it is easily seen that the finite natural numbers don't exhaust all the natural numbers in alternative set theories. Fn is a strict subset of N. So we have this class of natural numbers which with each natural number contain the next one but don't exhaust all the natural numbers. So then there is first axiom which concerns classes and not set, is the axiom of prolongation, which says that for each function on Fn there is a set function extended it. So functions of Fn, going back to the intuition, corresponds to pass to the horizon, and a set function extending each such function means that pass towards the horizon continue in the same way beyond the horizon. Vopenka was keen to demonstrate that we don't need all the various infinite cardinalities, so he has an axiom of two cardinalities, which says that every class which is not finite is class equivalent either to the class of all natural numbers or to the class of all finite natural numbers. So to complete a set of axioms, there's the axiom of extensionality, axiom of comprehension for classes, axiom of extension of coding, which is the same as axiom of choice basically. So this is the formal framework, formal setup for alternative set theory as formulated in 1979. What Vopenka does in his book, Mathematics in Alternative Set Theory, which appeared at the year, is that he uses it to develop some mathematics, namely traditional mathematical structures like natural numbers, as I mentioned in the classical way, real numbers, in a rather interesting way, which is really generally special way to do it in this theory. Then rational and irrational numbers. Then he also develops some topological shapes, as he call it. It's again something which is not classically done on. He studies motion, point-wise motion, offsets, and so on. But all the mathematics in this small book, which Vopenka developed here, is done within what he calls limit universe. So it's a universe where there is no concrete natural number which is not in Fn. So all the infinite natural numbers are beyond the concrete natural numbers which we can point to. Vopenka also in the books calls for the study of what he calls witnessed universe. So it would be a universe in which there is some concrete natural number which is not in Fn, which is infinite. And actually such a theory would be classically inconsistent. And Vopenka says that it should be studied in a different way, namely only those proofs which have lengths from Fn, whose length is finite in the sense of alternative set theory should be considered valid. As far as I know, he didn't pursue this, and as far as I know, nobody else. But I believe there is more results around, and perhaps it would be interesting to revisit this. So what happened after 1979? Alternative set theory had been continued to develop for a while, but it did remain relatively unknown. Bopienka himself left mathematics more or less a few years after that, and devoted himself to the study of history and philosophy of mathematics. He was also distracted by politics, but I think there was one thing which he felt remained unsolved and needed more attention, and that was exactly the development of infinitesimal calculus within alternative set theory. As I tried to say before, when he formulated alternative set theory, he knew that it is possible to develop infinitesimal calculus within alternative set theory, but he didn't want to do it in a way which would be somehow parallel or very analogous to non-standard analysis. He believed that infinitesimal calculus would somehow grow out of alternative set theory in some natural way. But it hasn't happened, and I think it was one of the things which drew him very strongly back to mathematics. So he did return to mathematics after his spell in history and philosophy and politics, and I believe that most or all of his mathematical thoughts, late thoughts after that gap, are contained, collected in the book on New Infinitesimal Mathematics, which is really a set of 4 books, which I will briefly describe now. So the first part of this book is called The Grand Illusion, where Bopienka surveys the historical roots of Cantor's set theory, and that means he surveys classical approaches to infinity, and in particular Bolzano's proof of infinite set. I mean, Bolzano's proof was mentioned here yesterday by Peter Damarovsky. I am returning to it because it will be relevant when I say something about the next book. So it is the proof where Bolzano points out that there exists a true sentence, and that there exist infinitely many of true sentences which we can produce, but saying that previous sentence is true. But Bopienka always emphasized there is this crucial step, namely that God must hold all the true sentences, that within God there must be all the true sentences at the same time present as an actually infinite set. So Bopienka used to say that this is the only true proof, consequential proof of existence of infinite set, because it spells out the assumptions and it follows from the assumption. So the last step is that it is important that it's true sentences which the God must hold together in him. So Bopienka goes on to argue that within this line of thought, we have to conclude that no set of natural numbers exists. And he uses a very old argument. He even used to say that Scholem should have seen it and so on. That set of natural numbers cannot exist if we continue this line of thought, because if it existed, then we could construct ultra product working, say, in constructible universe, and form an ultra-extension operator which makes sets out of the functions in the ultra product. In all this, again, Hopenka talks about natural numbers and means for Neumann representation, so he means the sets. And if we do this, use an ultra product, use an ultra-extension operator, we form more natural numbers, and we form another set of natural numbers which exists as well. So to continue the line of thoughts, teleological line of thought, Hopenka would say that it means that all we can do is to allow God the ability of create any of the many possible sets of natural numbers, because whenever there is one, there could be another one, and God has no reason to choose one or the other. So Hopenka's conclusion here, form sets of natural numbers, is similar to the conclusion he made many years before about set universes, namely that we have to conclude that what there is, say in God's mind or wherever classical set theory was supposed to take place. All we can conclude is that there is something which he calls sensorium Dei, which is the space where possible set universes could be actualized, but one at a time, not simultaneously, because of this independent principle. And the same thing applies to sets of natural numbers on the basis of this argument. So this is the first book. The second book is called New Theory of Sets and Semisets, where Hopenka goes back to the intuition he developed for alternative set theory, and the mathematics in it is similar. Hopenka remains very informal. In the introduction, he motivates doing it basically again by saying that being consistent about insisting on non-actualizability of the set of natural numbers and insisting on working with the set of natural numbers that is Fn as indistinctly defined actually makes many of the concepts in the form alternative set theory simple, and therefore he calls the new theory new infinitary mathematics, not alternative set theory, and develops similar intuition. He is much more informal here, and at one point he even says that we can use predicate calculus when studying elements of Fn, their properties and relation. However, we must be very careful with the quantifiers, because the semi-set Fn is not sharply defined in the direction of the horizon, limiting the size of finite natural number. So we again sort of recalls the fact that alternative set theory is not meant, or the new infinitary mathematics is not meant to study a limit universe, but it was meant to study witnessed universe, because is the universe to which all this motivation about natural infinity apply. So, the last two books in New Infinitary, the third and fourth book in the New Infinitary Mathematics collection, are about real numbers and differential calculus. And here Hopenka goes, sort of leaves the framework of mathematics, phenomenologically defined mathematics, and uses a framework which he describes as follows. He works with two mathematical works, and one of them is what he calls Greek mathematical world, which is the world inspired by phenomenology, the mathematical world of ancient Greek mathematics, where the horizon is geometrical horizon demonstrated in lines or points. So there's one world, and the other world is the world which has been arrived at in connection with arrival of Bolzano and Cantor's absolute infinity. And that's his motivation. He works with it in a similar way in which non-standard analysis uses the two mathematical worlds constructed within the set theoretical universe. So the result of all this is infinitesimal calculus developed from axiomatic principles which are very carefully philosophically motivated, but which are very related to other axiomatic approaches based on non-standard analysis like those of Kaiser or Hrabáček or other people. Having said that, it is the case that Opěnka's approach is particularly elegant, and it works very well. It was actually also noted by the reviewers of this book. So, in conclusion, I would like to emphasize how privileged I felt to be Peter Opěnka's student, and I try to indicate how much I believe there is still in his legacy for other people to take up and follow. And I do hope that it will be just as big an adventure to pursue this as it was for him. And to illustrate it, I would like to read a paragraph to say this in his own words. It is a paragraph from a fictional book which Opěnka wrote about Gauss, actually, because unlike Matthias Park this morning, he didn't think that Gauss actually always dismissed the young boys coming up with a great idea by saying, I had it before, whilst he didn't have it. The book is about Gauss's alleged discovery of the consistency of non-Euclidean geometry, which had been actually discovered by Bollier. Lobachevsky Bollier was the young guy who did come to it, visit to Gauss, but Gauss actually is supposed to have known it before. Opěnka speculates, just makes a story, a very readable story, about why Gauss would have never published anything about it. And this paragraph, which I'm going to read out to finish, is from the point when Gauss actually realizes what he has discovered, that when he realizes that the negation of the fifth postulate is consistent. So here it is, about Gauss at the point when he realizes his big mathematical breakthrough. He was living this rarest moment of enlightenment that only a few chosen scholars encounter, possible just once in their life. It is a moment of indescribable excitement, marrying a religious thanksgiving with a solemn apprehension to take the fruit that has ripened. This fruit lies in front of us, attracts our eyes, and at the same time repels the hand from reaching out to it. We know that we have it now, it is ours, but its glow dazzles us and holds us in a sweet intoxication so that we don't find enough strength to take it completely. And yet at the same time we long to become sober because we know that we must still make the last step. Never are we so frightened of death at this very moment. Only that can catch us our heart with the crown of our life, turn our moment of seeing into nothing. Yes, this moment truly appears to us at the peak of what a skull can achieve. Whoever has lived through it once will not stop longing for it. And whoever, even though seeking, has never lived through it, is, without being aware of it, seeking that, and not what they imagine to be their goal. Okay, thank you.
Thank you all now for perhaps you can add some small short remark or comment. Yeah.
I have a question. It regards the relation between alternative set theory of non-standard analysis. Because non-standard analysis builds on specific definition of formal language, and the basic tool is the so-called transfer principle that allows to transfer non-standard results into the classical language. So the question is there any counterpart of transfer principle in alternative set theory?
It is in the new infinitary mathematics. In the infinitesimal calculus, Bopienka actually developed and presented as a possible textbook for study. There we of course have the same transfer principle called by a different name. But there is nothing like that in alternative set theory. In the preface to alternative set theory from 1979, Bopienka says that infinitesimal calculus could be developed from within alternative set theory, and I tried, not very successful, but I tried to argue why that was the case. It is because of the shared formal structure of the two things. But it is not there, no, it hasn't been developed within alternative set theory.
So let's thank the speaker again. So the next, now we have a 15-minute coffee break. We'll resume at 16:30, so in fact it will be just 12 minutes. And we will continue with the chamber music and performed by the trio of chamber girls. At least 4:30. So ladies and gentlemen, it's my special pleasure to introduce the trio Wind Harmony Orchestra Brno. Trio were orchestras, sorry. They will amuse us with some sweet short pieces experimenting with the flow of time.
Many thanks for invitation, but now some music in the introduction.
gentlemen, let me introduce our ensemble. It's a very small ensemble, which is the trio of chamber wind harmonic Brno. It's an amateur company, and we play as usual in a much larger larger number. So our trio is the smallest ensemble. It consisting from 2 clarinets and bassoon. And we have just heard the beginning of the third movement entitled Lovers from a Slovak suite which was written by Czech composer Vítězslav Novák. The composition has had its premiere in '94. So it's 2 years before the birth of Kurt Gödel. So it's not excluded, or it's very probable that he knew it, because it was the famous, the most famous Novak's orchestral work. But we transform it in our trio for only 3 voices. So now we are in mathematical conference, which is dealing also with the flow of time, and it's a very good opportunity to do some musical experiments. I hope that Master Novak will allow it. And now we need to remark that music is the art which is flowing in the time. And the time or players need to have the same time, the same beginning, and the same tempo. And also the same direction of time. Now we shall to do some experiments. The first we will remind you with the first theme of this piece, Zamilovaní, or Lovers, from Slovak suite, as it was written in original. It's the first 10 measures. Sense of time from the back to the beginning. So only 10 measures, not more. So. Because the harmony remain, but the sense or logic, music logic is out.
there is no good musical logic. But we have the same tempo, but we have the opposite direction of time. So now we will do some musical massacre because I will go through from the beginning to the end, and my colleague will go in another direction, but the tempo will be the same. So it will be something. Why it's such problems? This is no music now, and why? Simply because the music is not symmetrical. From the beginning to the end, we have asymmetrical way, but we have some special pieces where we hear something another which are so against this rule that the music needs to be symmetrical. I want to introduce one piece of Johann Sebastian Bach, so-called correct canon. All of you have the possibility to see it in notes, and you can see which sense or which music are in this correct canon. Let me know you that this canon is not written by Johann Sebastian Bach completely. The first part, in the first voice, is the theme, so-called King theme, which was given to Johann Sebastian Bach by the Frederick the Great, Prussian king, which was also a very good musician and composer. And this theme is the common part of many other compositions. The name of each is musical offering. And was written by Johann Sebastian Bach. And this part is the simplest and the shortest from that compositions. So, as the first, I will play the King's Hymn. So, it's Johann Sebastian Bach, but not itself, but is the theme which was given by him. You hear that it's very severe, constructive. You see here a descendant descendant of the music in chromatic, and it's not very good for hearing. It's not melodic. It's construction, which was very good for Johann Sebastian Bach for experimenting in different musical forms. And now, if you can see in the correct, you see that there are some edits, and this melody is written by Johann Sebastian Bach. I will perform it. It's from the axis to the right. It's a melody. So, the piece is very interesting that if it's played backward from the end to the beginning, it gives some musical sense, and I will ask my colleague who is playing with the second voice to perform it, and you can check that these notes are my part, but from the end to the beginning, please. Bachian piece, yes. But what's interesting is that we can play it together. So. It was Kurt Gödel, and it could be only by a composer which was more or less mathematically oriented. And it was Bach. And what's very interesting that very good mathematician was also Wolfgang Amadeus Mozart, who was very good in mathematician, but now we will play the composition which was not ruled by some mathematical laws. So now we will play the rondo from the second divertimento B flat of allegro, via trio chamber with harmony, please.
Dear colleagues, we start with last session of our conference. I apologize that I must insist on strict respect to timetable because after session is trip and we have bus and sightseeing. So every speaker has only half hour, including eventual discussion. So we can start with Kurt Gödel from Mathematical Institute in Prague and in the same time from Stekov Institute in Russia. He will speak about Presburger arithmetic.
Oh, yeah. Thank you. Yeah. So of course, yeah, clearly better people than I am, because I definitely I would skip my own talk if it wasn't be mine. So, this time is, yeah. Okay, so now so about myself. So when deciding what to talk about, I asked to give some talk related to Gödel and preferably the Tarski. So I thought, so what kind of talk would I give that is related both to Gödel and Tarski, and I come up with this topic. So now I'll talk about this speed up results for this classical decidable theories. Gödel is the first person to notice this speed up phenomenon, and Tarski spent quite a lot of time in his career studying this decidable theories. Okay, so let's now to remind you of what is Gödel's speed up theory. So there's this extremely short paper by Kurt Gödel. So where actually he haven't gave any proof, but he stated his speed up result. This result, so he the theorem that he formulated was about this high order arithmetic. So if you consider this nth order arithmetic, so basically you start using this lowest sort, you have natural numbers with the usual addition multiplication, and then you build up sorts of sets. So if you say the second order arithmetic has this sort of sets of natural numbers, the third order arithmetic has a sort of set of sets of natural numbers, and so on. And so of course the series becomes stronger and stronger because you're not only adding the sorts of new sorts, but actually you're adding new axioms, namely your comprehension scheme for each next sort. So you have this comprehension for second order comprehension for set of natural numbers. So that given any formula, any property of natural numbers that are given by a formula should correspond to a set, and so on. So some property of set of natural numbers that enforce order arithmetic, you will have this set for objects that satisfy this property. Okay, yeah, and so what happens here is that actually given say this n+1 order arithmetic and n order arithmetic, it's possible to find the sequence of formulas that have relatively short proofs in n+1 order arithmetic, but arbitrarily long proofs in nth order arithmetic, despite okay. So what I mentioned here is that both the formulas are provable. So actually nth order arithmetic still should prove these formulas phi I. So I forgot to mention it. But despite the prove them, it proves them only by very long proofs. So namely the proof with the length f of ki. So this f is arbitrary recursive function that is fixed. So before the construction, so when computable function f, there is a sequence of formulas that corresponds to this extreme growth of to at least f's growth of lengths of proofs. And so by lengths of proofs, so here I mean the following. So we consider some proof system. So in the example that will be interesting to me here, it will be just standard Hilbert style proofs for first order logic, but one could consider some other kind of proofs. And then we just measure the amount of the length of this proof as binary string. So of course we have this encoding of proofs by binary strings, and then we could just measure this encoding length of. So actually it's a natural method for length of proofs. Okay, so this was the result of Gödel. So actually there are a number of other speed up theorems. So let me briefly mention them. So actually this essentially this it seems that the simplest way to prove Gödel result, perhaps I don't know what exactly was the proof that Gödel had in mind, but so there is this elected theorem by Voigt and Masaryk, so that actually this in this realm of undecidable theories, this speed up phenomenon is extremely typical. So So I actually can't mention what speed up is. So basically speed up is the same situation as in Gödel sequence. So when we have the sequence of formulas that is provable in both theories, I forgot to mention this in the definition, but yes, we presume that all the formulas in the sequence are provable in both T1 and T2. But T2 proofs are following the T1 proofs, and naming F long, and then we say that there is F speed up. So in the second plan we have this indecidable series, and one is stronger than other. We have this moment speed up of the speed of arbitrary recursive function. So then there is this situation of conservative extension. So you have one theory and a theory in larger language, but where we have this conservation also this theory in large language proof of the same theorem as initial one in the initial language. We have most known example for this phenomenon is a pair of NGP, so for Neumann Gödel Bernoulli set theory and Sarmel-Frank set theory. So this important distinction is that so despite this first order theorems of this for Neumann Gödel Bernoulli set theory are precisely the theorem of ZFC, so NGP is finite some type, whereas ZFC is not. And actually it's reflected in speed up, so this actually implies there are no arbitrary recursive speed up, of course, between these two theories. But there's rather high speed up, so namely we have this hyper-expansion speed up, so we have this hyper-expansion function, this hyper-expansion of x is exponentiation iterated x times. So it's non-elementary, so this is actually it's precisely corresponds to what kind of speed up we have in this situation. So the second example is an example of the pair series of arithmetical comprehension pianarics. Okay, so if you go from this to different, so when we not looking just on maximization, but actually trying to fix something in proof systems. So if, for example, we consider this cut-free proofs and proofs with cuts, then again, so we have exactly the same kind of speed up. So if you consider just first order logic, then so we have this the same kind of speed up. So of course, proofs with cuts are more efficient than proofs without cuts. And so actually, since now, so far I've mentioned essentially only undecidable series. Of course, the strong first order series are decidable, and of course first order logic is undecidable. But actually, the same the speed up occurs in the level of proposition, even on the level of propositional logic. So here's this result. Happens so that if you consider this, resolution in the standard proof system for propositional logic, precisely for DNFs, that is used in this automatic provers, CH procedure, and so there is this fraction principle, which is essentially the same as Hilbert-style proofs for propositional logic. And actually, the fraction proof system is more powerful than resolutions, and there is this precise expansion speed. But actually, it's best optimal because because actually any propositional tautology have exponential size proof, so you can large speed up. So here in this setting of this, decidable language, propositional logic, so there is this natural bound speed up. Actually, it corresponds to situations that I will talk about. Okay, so now so the theories that I will talk about are so the decidable elementary theories. So so actually I will focus on two. I think most well-known examples. So we have this stability of Pressburger arithmetic, so this elementary theory of natural numbers, and we have process stability of field of real numbers and of Euclidean geometry, which of course is more or less so Euclidean geometry, in fact, and field of real numbers are more or less interchangeable from this perspective because we have translation from one to other and vice versa. Really, so you could reduce question about real numbers to Euclidean geometry. It's a bit more tricky part, and so this part of the discussion about killing geometry to real numbers, but actually could go in another direction as well, so it's more standard stuff. So, and because we are interested in the slides proof, so it happens from our perspective, this kind of theories are more or less the same. Okay, so now let me speak a bit in a bit more details about this. How because now compare the various proof systems for the theories, because so far this was a semantic definition, but of course we could give axiomatization for the theories, complete and decided, but of course we have this nice axiomatization. So first of all there was okay, so we'll start with Pittsburgh arithmetic. So, okay, so for me, it will be convenient to start with some basic theories. So important feature of Pittsburgh arithmetic is not finite axiomatized. So, and in reality, for understanding the strength of proof, what's important is this infinite series spectrums, not finite, finite part of axiomatization. So basically, we need to fix some base finite axiomatization theory. Okay, so here it's a theory of PRI minus. That is a theory so where that says that so plus and zero form and cancellation for being semigroup. So yeah, okay, so I think it's say here. Okay. Okay, yeah. Okay, actually, I think we just need to say. Yeah. Okay. So we have this. We have these axioms. Yeah. And then over them we are we have two natural axiomatization of Pittsburgh arithmetic. First one is which perhaps is more natural one, and is by adding this induction scheme. So very natural. So and actually then this final dimension Pittsburgh arithmetic even a bit more excessive, because we could just add this Pittsburgh fragment of the standard axiomatization plan arithmetic and get the same result. And the second option is to get this series fragment that says that we could divide by the remainder by any fixed natural number. So we have this notion multiplication, but any by any fixed natural number, and we would have this modular comparisons, and yeah, so we should formulate this axiom. Say that any basically any natural number is comparable with one of number from 0 to n minus 1 modular n for each n. So I mean quantify elimination. It shouldn't be that elimination. So because actually using the standard quantify elimination, we actually could prove that both the theories coincide with each other, and with true theory of natural numbers with addition. But in fact, there is this double exponential speed up of this axiomatization with induction over the axiomatization without induction. So with this modular comparisons. In fact, this second this induction axiomatization happened to be much more efficient in the sense of proofs. So let me briefly mention why it happens. Actually, the reason for this results are rather simple ones. So basically, the point is so that we could express this, despite we couldn't express the full multiplication with Pittsburgh arithmetic, we could have this short formula that express some restrictive form multiplication by some relatively small form numbers. So namely, we have this could have this polynomial in an formula that expresses multiplication of arbitrary number by a number that less than 2 to the n. So here we have restriction on y's, but not x's. So we could multiply any number by this number that is smaller than 2 to the n. Okay, and these are short formulas, and in parallel, even this base theory PRI minus to prove a lot of natural properties of this formula, so it actually, to some extent, knows the express multiplication, and this allows actually them using given induction for arbitrary formulas. It's easy to then prove that any number is divisible modulo y of all y's less than to the 2 to the 2 to the n. So basically, we can easily express this using this multiplication formula for restricted kind of numbers, and then we could easily prove it by induction. So because on x, so if you know that x is divisible with remainder by all numbers from this range, then of course x plus 1 is divisible with remainder by all numbers from this range, and that's by induction, practically by induction, and proves that all numbers divisible modulo all numbers from this range. So in fact, so this with some using some standard techniques in estimation of the length of proofs, it's possible to show that this family of proofs, so the sentences that for x we have this divisibility by a lot of numbers. So the length of the proofs are polynomial in n. But the point is, but it's of course in this exemplification with induction. In exemplification without induction, of course, these formulas are extremely hard to prove. And it's very easy to see because essentially this formula incorporates a lot of our basic axioms of this alternative maximization. So it's essentially incorporates this kind of axioms for all k for all k's less than or equal to 2 to the n. And in fact, so I haven't given here the precise, we actually know what precise dependency between these axioms are, or principal, but so short corollary from the fact we know about this dependency is that so we will need at least one axiom of this to prove this formula for x and x. We will need at least one axiom of this form for some large enough case. So this is, at least it's 2 to the 2, then by half. So it's so it's of course an extremely large axiom, and by necessity it implies that we have this double expansion speed up. So because just the length of this axiom itself is of this double expansion length, so it's you couldn't get anything better from this. So this was the situation with Pressburg arithmetic. Actually, with elementary geometry, the situation is more or less the same. But let me keep a bit more details. So what are the corresponding exemplifications? The efficient ones that say corresponds to something more stronger schematic principle, and the ones that say more corresponds to what happened in the concatenation. So actually, that will measure. So basically, of course, there is this, as I said, so there's a theory of real closed fields and theory of elementary geometry. Both of them could exist, but it's more or less interchangeable things. So the standard way, actually, but actually, what difference is how they are usually axiomatized. So usually, when people axiomatize elementary geometry, for example, the standard task axiom, the key part of the axiom is this. Continuity schema. So it says, so it basically says that so if you have some subset of arrays and that is bounded, there you have this. It should be list. Of course, it should be list per bound, not gets per bound. So basically, so they express continuity of real numbers in this schematic way. So this one way how you do it. But in the theory of real closed field, the standard way is that one. So namely, so they still have this infinite sequence of axioms, but they say that all polynomial of odd degree have roots. And so what actually happens? So this is actually interchangeable. But what really happens here is that so this, in fact, continuity axiom. So it's far more efficient than axioms about this polynomials of axioms about the roots of polynomials of odd degrees. So namely, in fact, we could for example, we could express by a short formula that says this all So we could say, yeah, so we could express this exponentiation operation for so finite range of natural numbers. So in fact, so in this in this language, we could express what does it mean to be so in the language of real closed field. We could explain what is. We could have this short formula that expresses that something is a natural number less than double exponentiation of n, 2 to the n, and then we even more could express this exponentiation by the natural numbers from this range, and then using this exponentiation, restricted exponentiation operation, we could express that this kind of equation has a solution. Yeah, this kind of equation. So here y is not really arbitrary numbers, but rather a range of naturals that are less than this. And so of course, so is just so we have this. This says that we have this roots of 2 of this large range of degrees. Yeah, but then it's easy to again. So it's easy. It's a sense that it's very easy to prove using continuity because of course we have this. So basically we do it in a completely straightforward manner. So we have basically we use intermediate value theorem for exponentiation function, and yeah, and of course it could be done. So we could find this roots of 2 using continuity, and so this piece of code will be very small. However, okay, so it's yeah, I wrote something wrong about this. That implies axioms. Okay, it's of course not the case because it's not an arbitrary equation. So we don't we don't a solution to arbitrary equation, but the specific one. So it's okay. Don't print this. So I don't know why I wrote this. Yeah, but the point is that still we couldn't prove existence of the roots of 2 of high prime degrees without using this existence of solution of this equation of odd degrees for some rather large odd degrees. So it's inevitably we need this axioms about solutions of polynomial odd degrees for very high degrees. So it's okay. It's not supposed to be for this. Business test. It doesn't work like this. Yeah, but so we still need this so high. It's easy to prove. So it's a rather easy exercise that could be proved using the law theory. Yeah. So next, then. Okay. Yeah. So actually, this was a specific case. So this was start of this very classical optimization. Actually, so all the optimization mentioned are well known. So it's not that I invented something here. But in fact, so other option is to actually use even just undecidable theories as this proof system for this weak decidable theory, because we could embed the language of decidable theories in the language of undecidable theories. And in this setting, we actually could exploit the Gödelian phenomenon. So actually, that if one theory could consist of other, that is essentially strong, and in this setting, we actually could get the speed up. So namely, so if you have this first order arithmetic that proves consistency of some theory that contains language of Pressburger arithmetic, then there is exponential speed up already in the language of Pressburger arithmetic of this stronger theory E over weaker theory U. Okay, and more or less the same holds for real closed field, so one should be a bit more careful for mesh because there is a standard embedding of Pressburger, language of Pressburger arithmetic is language of Peano arithmetic, but for real closed fields we need so fix itself, so we need to fix the interpretation of theory of real closed field in our arithmetical theory, or maybe some theory in the even Daytician arithmetical, for example, in set theory. Okay, so then we have this speed up. So actually, this result actually even doesn't. So here we don't use the standard secondary completeness part, rather this finite version secondary completeness theory that public have talked about on the first day of the conference. So yeah, that's all.
Thank you very much for the interesting lecture. We have 2 minutes for you consider the quantify elimination for real closed fields as additional property, that only polynomials down the degree of the problems are used as zeros for uneven polynomials less than the degree of the problem. So if you have, for example, a cubic problem, you use only zeros for 3. And now the question is there a speed up, you think, if you use, so to say, higher polynomials?
Oh, okay. Actually, I think I can understand. So what is that doing? Because of course, so when we do this quantifier elimination, so of course you could get, so we have this formula with quantifiers, we could get a...
Yeah, we have a proof. So in the end, the quantifier elimination shows there's a proof where you only use zeros which are less or equal to the degree of the problem.
Yeah, but you need first to quantify eliminate it.
Yeah, but this gives a proof, so you can reduce it to a proof. So, and now the question is, would there be a speed up if I allow higher polynomials than the degree of the problem?
No, I think I still don't really understand.
No, you see, if I have a problem, for example, with a three-dimensional problem,
okay, sure.
Then I need only polynomials of degree 3. Also the roots of degree 3. Because the quantifier elimination is based on that. But I could, so this is a subsystem. So I could imagine there is a sequence of problems with higher and higher degree, so that there is a speed up if I use problems which are much higher. This is a question of Kreisel effect. He asked me that once, but I couldn't answer.
Oh, yeah. Yeah, I don't know if I but again, I think we could talk afterwards.
So, is it true that there's a divide between the Pressburger and the geometry case and the cases where you use consistency? So in the consistency case, you use things like the finite consistency statements, and in the other cases you use quantifier elimination, right?
Oh, okay. So it's not necessarily. It's not like I necessarily use quantifier elimination, but I like. Okay, so basically I formulate something that is very difficult to prove from. That is easy to prove using some schematic synthetization, but very hard to prove using this simplified synthetization that is arising from quantifier elimination.
Yeah, but so the question is, so what do you use in the proof?
Okay, so in this first cases, I say it's quite elementary consideration. So we need to estimate the lengths of proofs, but we don't really need anything about Gödel incompleteness theorem. But in the second proof, so that from consistency you could derive speed up, the probability of consistency you could derive speed up. Of course, I don't need this Gödel. And actually, so I actually had the different degrees of speed up there. So one case it was double exponential, other one was single exponential. But I don't think that I think in the second case actually one could prove even double exponential speed up, but it would require more refined techniques that I used.
Right. But so the methods in both cases are still quite different.
No, okay, in a sense they share quite a lot. So we need to essentially encode natural numbers in these fragments of natural numbers inside our systems of Pressburger arrays. Pressburger arrays, which we call elementary geometry. Using this, we could form. But in one case, this is next used to formulate finite consistency sentences inside the language of the decidable series. And the other case, it basically used to kind of compress a lot of axioms from our series. So basically, because this axioms is derived from this quantifier eliminations that correspond to this long sequence of axioms of low quantifier complexity, and then we could using this embedding of natural numbers could compress into a lot of axioms from the series to a single sentence.
So, discussion is finished. Thank you very much.
colleagues, my theme is probably somewhat from above. Gödel's religious worldview and the strange way in its immanent personal interpretation. First, something in general. Could Gödel no exactly constructed discipline can prove its system as indisputable? For a broader public, his profession was somewhat, and still is, maverick. We can say that Gödel, throughout all his life, felt himself being also importantly appealed by religious motivations. Gödel's ontological proof of God came to be more broadly known in 1995, even if spoken about sooner than that. Gödel possibly relevance for theology was from that time not neglected anymore. In Czech we have several authors who might be quoted now. Professor Vopienka, for instance, or Professor Hayek. As far as other items are concerned, I would like to quote now Hao Wang. Preliminarily, it should be stated that the Gödels lived for many years here in Brno, and at that time it was a town in a Catholic empire. Kurt's father was but only formally Old Catholic. Mother, sincerely Lutheran. And if we take into consideration that children from the earlier youth, when they come into contact with religion, they start with it in a very sincere manner. And religion serves them as a miraculous safeguard for the early life and for many people till the end of the life. During all his life, Gödel was, we can say, in a somewhat remarkable and regular contact with his own mother. He exchanged letters with her for all his life, and we can also say that we have at least 200 such letters between son and mother. What also may be interesting from this or similar point of view is also a rather strange fact that when he was young schooler, he made an acquaintance with a woman which was older than himself, some 10 years. And then he married a wife, or he married as a wife. After several years, it was not immediately a wife. As his wife, she was nearly 7 years older than he himself. We can probably say that even that shows some anxiety of Gödel as far as his life concerns, and his striving after safety can be shown even later in various other items too. My second remark, I have some 10 parts of this contribution. So now some short notes. If we want to reflect on God, then no verbal expression can be a possible tool for such a thinking. No verbal expression can serve as a possible tool for, we have not got any satisfying and unifying and immediately concept when we say or hear the word God. It is only a preliminary label, nothing more. And by means of some words exclusively, we have not got any concrete object which could be automatically verified. When we believe that some such essence exists outside of our immanent world, then we cannot say anything at all concerning his possible transcendental reality. Transcendental reality is outside of any plausible description. Something quite different is a possibly physiological impulse which forces us sometimes to believe in God and being sure about it. My third remark. The ontological proof of God finds its first model, as probably all of us know, in Anselm of Canterbury, to whom it is traditionally attributed. To prove the existence of an object, I repeat once more, to prove the existence of an object, we need to dispose of it or show it. Words are not enough for such a purpose. We have no viable proof of God, and we can't bridge it over to our immanency. We have no immanent proof of God. And the first person persuasion as against third persons views in mutual communication, that is something quite different. And as personal idea, God is a very strange singularity. I repeat, he is a rather strange singularity, dressed up for our conscience as duality, dressed up for our conscience as duality. There must be something in between. And it must be somehow, and it can't be stable personal experience in its followers' psyche. I repeat once more, it can't be constant and stable personal experience in the follower's psyche. I'm going on. Number 4. Gödel's conception of the human mind is the basis of our problem. The human mind was defined by Gödel as an, now I'm quoting, individual mind of unlimited lifespan. I repeat once more. Human mind as individual mind is something of unlimited lifespan. Gödel claimed also that, I'm quoting again, matter and mind are two different things. Matter and mind are two different things. You may find it also in Wang. I was quoting him at the start of my contribution. Another such quotation: mind is separate from matter, it is a separate object. And another quotation: even if the finite brain cannot store an infinite amount of information, the spirit may be able to. The spirit may be able to quote anything till the eternity. That are my words. And I would like to add something more, only as a note. There are many experiences described by Benjamin Libet. He was inspired by two Germans, by Kornhuber and Derke, some years before that, exactly in 1965, and in 1984, there are two contributions by those authors. By once more again, something which may be interesting here, that there is a certain readiness potential in our brain. There is a certain readiness potential in our brain, in German, Bereitschaftspotenzial, some 350 microseconds. So if I or anybody else wants to think about something or do something, the brain as such prepares itself before that, and before anybody knows that he is already preparing some operation or some activity. It means that our body is physiologically ready to start some reflection or some activity. And our psyche still seems to be singular. Singular in a similar way as God probably is, if God exists. I'm going on. Another note, contrapunct to note number 3 in my notes. There is no describable boundary of our cosmos. During the last autumn, that means in 2019, scientists in the USA announced the first possible results in quantum technologies. On the other hand, we can't find on one side imaginable limits of human knowledge, on the other hand some end of this continent or of this cosmos, of our universe. There might be some question here, where is Gödel's outside of this boundary? Now, my lament number 1. There are 3 laments here quoted in my text. I can say that a logical notation with its apparatus is completely located outside theology. The same thing holds concerning God in his possibly logical proof. There can't be any logical proofs of God. They are either words or symbols, but not anything for the experience, personal experience of God. That means something having to do with his singularity, if God exists. That is, of course, a problem. Metaphors cannot substitute assurances of a spiritual reality. If we want to give some place or existence to God, let's say somewhere before the Big Bang, we can do so, but it must be outside of our human imagination, so it is not very helpful for such a purpose. Messages, if they should come from God, have to be verbally presented by their creator. Thus they wouldn't be in any singular form anymore. And here should start some duality situation, and such a presentation was not yet presented by anyone. So at the beginning of an information process among us, if there is some spiritual interpreter at the other side, then we as persons, we should find before us singularity and not duality. This, of course, does not hold, and we as bodies seem to be in a situation of somebody who wants to give some message to his audience. So it is a situation of third persons, let's say onlookers or third person's audience. And something like that has not been found. I am going on. Another lament. I have here the Latin form lamentatio third. Something like an incompleteness principle also exists for theological problems. And there is also something to be added to it for such an observational formulation. Incompleteness, it's something to be commented within us mentally and of course on the material basis. And it should be at the same time a spiritual observation. What is or what may be, what might be spiritual, it is also a problem. And God thus cannot be given any human name, and he cannot be portrayed in any adequate way. And here several other difficulties arise. Bible reading cannot serve as a testimony of Jesus' life for Christians. And any verbal formulation within this or that religion cannot and does not specify anything in the heavens. Expressions like God is supreme, we can read something like that in various documents. God is supreme, or again quoting, God exists. Such formulations are not observational products. I am repeating, such formulations are not observational products, so they cannot serve as expressions with reliable meaning, being only preliminarily substituted by logical signs. Moreover, such expressions are a priori, which is another difficulty to consider such formulations invulnerable. We know it already from Hume. So, we have not got any viable criteria for, now I am quoting, nothing greater can be conceived. It is not only the formulation by Anselm of Canterbury or Bath and others. Also, in the same way, we should conceive eternal and infinite essentiality. And if we formulate some verbal axioms describing properties of something which we cannot find in our reality, in our immanent reality. God might exist in all possible worlds, and also now well. When the cornerstone of his existence and properties is only verbal, and that's the case, either verbal or symbolic, which must be somehow defined, and it's problem to make a good definition. Then he must be a singularity, and if he can't be connected with us, then such a singularity cannot be duality, sticking with somebody or to somebody else. And as an object of human knowledge, it is impossible to speak of him. And Gödel, we can say now, Gödel had some assurance that he can not only speak to his God personally, but he also and daily used his Bible to read in it. And thank you for your presence. I think it may be interesting, for logic cannot help us in theological questions. I think it should be here said and formulated, for Gödel believed in God and believed in the scriptures, or else he wouldn't read it daily. Thank you for
you can discuss with him after the session, because we have time, not many time. And now we will lecture Professor Joachim Hertel from the United States of America about hypercomplex mind.
Good morning, everyone. And I'd first like to thank the organizers for giving me the opportunity to present our research here on new numerical evidence for hypercomputing minds. So actually we heard just in the previous talk that Gödel had some opinion about minds, and also we heard already some references in the talk on Monday. So what we are doing here as an outline in part one, we briefly recall some other references of what Gödel had to say on minds and machines. And then in part two, we are presenting a new Gödelian argument, which is more quantitative in nature and was presented by Bringsjord in 2006. And then in part three, we are actually presenting our numerical computations. So let's get started on what Gödel had to say on minds and machines. And actually in his 1951 Gibbs lecture, he delivered an opinion on minds and machines, and here is what he did say. The human mind is incapable of mechanizing all its mathematical intuitions, which basically means if it has succeeded in formulating some of them, this very fact yields new knowledge. And he also had an opinion on Turing's proof that every mechanical procedure is equivalent to every mental procedure is equivalent to a mechanical one. And here he says, Turing gives an argument which is supposed to show that mental procedures cannot carry any farther than mechanical procedures. However, this argument is inconclusive because it depends on the supposition that a finite mind is capable of only a finite number of distinguishable states. Although at each stage of the mind's development, the number of possible states is finite, there is no reason why this number should not converge to infinity in the course of its development. So, of course, there is a large body on this philosophical discussion, and we are not going to comment on this. What we are saying here is that statements like the number of minds, states converging to infinity are a little bit complicated and not really quantitative. So we are asking ourselves, is there any chance to make this more precise? And yes, there is, and that's the new Gödelian argument that was proved and forwarded by researcher Bringsjord in 2006. And in order to state his new Gödelian argument, we have to recall some more or less elementary facts. Number one, this is all textbook knowledge. We all know that there are too many functions on the integers for them all to be Turing computable. And in fact, almost 60 years ago, mathematician Rado presented an explicit example of an uncomputable function called the sigma function, also somehow known as the busy beaver function. And sigma of n is defined as the largest number of ones left on a Turing tape by a halting binary n-state Turing machine when this Turing machine is started on an all zero or all blank tape. And it is easy to see that this function is indeed uncomputable, because otherwise it would solve the halting problem, which you all know is undecided. And on the other hand, you can compute the sigma function for individual arguments, and indeed, if you look up the history, the values are known for sigma 1, 2, 3, and 4, and for sigma 5, for about 30 years we know a lower bound, which is 4098. Now, computing the sigma function for any specific value basically means to solve the halting problem for n-state Turing machines, for one particular n. We come back to this later. Now, after we have introduced the sigma function, we can now formulate this new Gödelian argument, which was brought forward by researcher Bringsjord in 2006. And to set the stage here, we follow his definitions and his kind of proof. And for that matter, let's first formulate the thesis of computationalism, which basically means, in practical terms, that each mind can be represented by a Turing machine of finite complexity. So, taking his notation that P be persons, or minds for that matter, M a Turing machine, we have a complexity measure to measure the complexity of a Turing machine in terms of states and transitions, and let K be an integer, and the thesis of computationalism can be stated that each person, meaning mind here, can be represented or is equivalent to some Turing machine of a finite complexity. And now Bringsjord makes a very interesting assumption which mirrors, so to speak, the more fuzzy statement of Gödel when Gödel said that yes, the finite mind can only work with a finite number of states, but there is no reason why this number cannot eventually converge to infinity. And this is now replaced by a new assumption of Bringsjord, and he says, let's assume that if the human mind is able to compute sigma n, it is able to eventually compute also sigma n plus 1. Now this is a very quantitative measurement, and keep in mind, this is not saying that the sigma function is a computable function. All it says is, if we assume that the human mind can compute sigma n, then eventually the human mind becomes so creative that it can also compute sigma of n plus 1. Now, and then he basically shows in a very interesting proof which I really suggest to look up. We don't have the time to present it here. That if this assumption holds true, then one can logically prove that computationalism cannot hold. So, and that is basically where we start. And keep in mind that I said the sigma function is already known for the values of n equals 1, 2, 3, and 4, but only a lower boundary, a lower bound for sigma 5 is known for the last 30 years. So what we are trying to do here is to present new evidence that this assumption of Bringsfjord is true, that eventually we are now, given modern software tools, are able to compute sigma 5 and hopefully then over time sigma 6 and so on. So in order to keep notation very simple, we represent 5-state binary Turing machines as a 5x2 matrix. The matrix elements are the transitional instructions that control the operation of the Turing head on any given tape. And so basically you see here we have 5 states. That the Turing machine is binary means basically that it can read and write only a 0 or a 1 on the tape, and the head can move to the left or the right. The tape is infinite, and whenever a transition is operated, it moves to a new state, which can be one of the operational states, 1, 2, 3, 4, 5, or the state 0, which is a halting state. And basically, that leaves us with 24 to the power of 10 possible binary 5-state Turing machines. So it is a very large search space, and to compute sigma 5 basically means we have to decide on each and every of these Turing machines whether it holds and therefore contributes to sigma 5, so we can eventually compute sigma 5, or it is a non-halting Turing machine. Basically it goes on and on. So essentially it means we have to solve the halting problem for 5-state binary Turing machines. Now here's one example of a Turing machine, and it is a very, of a 5-state Turing machine, and it's a very famous example. It was published by Marxen and Buntrock about 30 years ago, and it is the current record holder in the sense that if you start this Turing machine on an all-zero tape, it actually stops at about 47 million steps, and it leaves exactly 4,091 ones on the tape. So this machine is actually giving us this lower bound, which, as I said, is now known for about 30 years. When you look up the literature, you of course find a lot of publications where people tried to calculate sigma 5 and made some progress. Virtually all of them started out to classify the Turing tapes in terms of geometrical patterns, and so you find in the literature a lot of classification of Turing machines like Christmas tree Turing machines or glider Turing machines and so on and so forth. So from our point of view, this was more an art than a computational effort. So we took a new and fresh approach, and basically our approach is based on Turing tape numbers, which I will shortly introduce. First of all, however, we are fortunate there are some well-known off-the-shelf methods to reduce this gigantic search space very easily, and these are the methods of tree normal form, which basically is a way to organize the Turing machines when you create them. We have backtracking, and we have simple loop detection. And so these methods are known for quite a long time. And if you apply them, you can reduce the search space to, down to, roughly speaking, 1.6 million undecided Turing machines. Everything else is then, after applying these three mathematical methods, already decided either as a looping, never halting Turing machine, or a Turing machine that stops, and if it stops, it contributes to the sigma function. So basically, what we are embarking here is to finally compute and decide these 1.6 million Turing machines. And as I said, we are doing a different approach because we really want to apply modern software, meaning artificial intelligence programs, to classify these Turing machines. And there's a very well-known method, and that's the method of tape numbers. Tape numbers is a very elegant way to encode an infinite binary Turing tape into two integers, the left tape number and the right tape number. Left and right here depends on where the Turing head currently scans the cell. And let's take an example here of a Turing tape. So first of all, the notation here, the 0 on the left side and on the right side in brackets means that an infinite number of zeros follow, because at any point in time of the execution of a Turing machine, you only have a finite number of ones on the tape. And the one which is here in the middle, which is printed in bold, serves here as our example where the Turing head currently scans the cell. So the left Turing number is basically in binary. We start reading from the outermost one. So in our case, and we are not including the cell where the head is. So the left tape number in binary is 11010, which is decimal 26. And the right tape number we read backwards from the outermost one. So it gives us binary 1110101, and then we include the cell which is currently scanned by the head, which translates to decimal 235. So this particular sample tape can be completely characterized by two integers, namely 26 and 235. And that's a very elegant way, because now you can imagine what we are trying to do here. We record these sequences of left tape number and right tape number plus the state, which would give us the complete configuration. And we do this for millions of times. And then we apply basically software to see if we find recurrence relations based on integers. And there is good software support for that. Let's continue on that. So basically, what we have done first, and we come to some examples, we are almost done. We have already classified roughly 90% of these 1.6 million Turing machines. And of course, if we find a recurring pattern of integers, it doesn't mean itself that we already have a proof. So that is the second step, and I come to that. So let's first give you some example of how this looks. So take a look at one of these 1.6 million Turing machines, and if you execute this machine for a number of steps, and when I say number of steps, you really need to run it for several 100,000, if not millions, to get rid of the initial noise and so on. And then what emerges is the following recurrent sequence here. If the machine is in state number 3, the left tape number is basically following a recurrent pattern of 4 to the power of n minus 1, while at that moment the right tape number is 0. So this now what do we learn from this? This is in itself, of course, not a proof that this particular Turing machine is never halting, but it gives us a nice induction hypothesis. And that's exactly what we are doing here. We take these first steps where we, with the help of artificial intelligence, we find these patterns, we formulate these patterns as an induction hypothesis, and then the second, much more complicated step is to actually do an automated induction proof that the Turing machine runs when you start it on a symbolic configuration. It actually starts and runs from n to n plus 1. And we come to this, how this looks. So the first thing is we have to verify the induction hypothesis for n equals 0. This is very easy because after a couple of steps we already see that the configuration for n equals 0 emerges. So the induction hypothesis is valid for n equals 0. And now comes the complex step, which basically means we have to do the induction proof itself, meaning we start the machine on now a symbolic configuration, which first of all means we have to find a way to execute the machines not on integers but on symbolic numbers like 4 to the power of n. And this again is based on a software project that we are developing. This, I have to say, is not fully under control because of the many branches these proofs can take. And basically, it is very similar to what we have heard, I think it was on Monday, in a talk which was called Automated Induction Prover and Neural Networks for Minimal Logic. And we are doing here the same in spirit, and our automated prover basically detects the possible induction proofs and tries to verify that the Turing machine actually fulfills the induction hypothesis and goes from n to n plus 1. So here's one concrete example for this Turing machine I just mentioned. So we start the Turing machine, let me say where the, here is, oops. Yeah, okay, so we start the Turing machine in a symbolic configuration. We prepare it in state 3. We prepare the left tape number as a symbolic number, 4 to the power of n minus 1, and the right tape number remains an integer. And then our automatic induction prover starts executing the Turing machine now on these symbolic numbers, and after 20 steps we see a new pattern emerging where we introduce here a k, and we see that k moves from k to k plus 1 and so on. So this in itself is a subproof which the induction prover has to do, and we see that after a finite number of steps we have a new configuration emerging where the Turing machine is now in state 2. Left Turing number is now integer 0. Right Turing number is now a symbolic number 2 to the power of 2n plus 1 minus 5 and so on. And then we see how, so basically from here to here we see that n bits has been shifted from the left tape number to the right tape number, and that of course resembles what people previously tried to do when they organized Turing machines by bit patterns. The big benefit here is that we are now dealing with integer sequences at a symbolic and recurrence relations, and we have a large number of software tools available to do this. So anyways, the proof continues, and after another number of steps we see how the bits are shifting back from the right tape number to the left tape number, and eventually we see that indeed we are reaching a configuration in state 3, and now we have 4n+1, so we actually have a full induction proof where the machine translates the initial configuration for n, for any arbitrary n, to n+1. So this is now a fully qualified induction proof. The length of the proof, meaning the number of steps the machine has taken to go from n to n+1, in this particular case is linear growing, 14n plus 40 steps. So this basically is now a mathematical proof that this machine will indeed never halt, and therefore is not contributing to the sigma function. And basically what we are doing here is, after we have almost classified these 1.6 million machines in terms of integer sequences, we have to refine our automatic induction prover more and more to capture all the individual branches. So for example, if you deal with symbolic numbers, at some points you have to decide, is it an even number, is it an odd number, and these kind of things. So there are a lot of problems, and then also these subproofs where we have a small induction proof in between. So there's a lot to do, but basically we are very confident that within a limited amount of time we fix all these problems and get the induction prover working, so that we can actually do all the 1.6 million induction proofs in an automated way. So you might wonder, what kind of behavior are we finding when we classify all these 5-state Turing machines? So we already have seen that we find exponential increase of tape numbers. This particular Turing machine here is an example of a double exponential growth. Oops. A double exponential growth in the tape number, so that's another kind of complicated behavior that we are finding for a lot of Turing machines. And this one here is exhibiting an even more complex behavior, and it is essentially the most complex behavior we are finding within the 5-state Turing machines, and we call it a Collatz type of behavior, because it reminds us on the Collatz problem, the 3x+1 problem. So here the exponent of in this case of the right tape number follows a kind of Collatz-like sequence, as I have noted here, and the initial value here in this particular case is 2. So basically, if we sum up, what we see is, for many Turing machines, which are very easy to prove, we see a linear behavior in the tape numbers. Then we see exponential growth in the tape numbers. We see double exponential growth in the tape numbers. And we see this very complicated Collatz type of behavior. And that's basically where the 5-state Turing machines stop. They simply can't be more complex because they only have 5 states and they are only binary. And that's of course why we might have eventually the chance to fully compute sigma 5. And in order to sum up, although we don't have really a solid result as of today, I can say what remains to be done is essentially software updates on the automated induction prover, and we are very confident that we finally will succeed in handling all the different cases. And if that is the case, what we can say is that this famous lower boundary for sigma 5, which is 4098 and which was published by Marx and Buntrock like 30 years ago, is actually the value of sigma 5. And if we assume that for the moment we would have given a tiny bit of evidence of the new Gödelian argument, which basically says if the human mind is able to compute sigma n, it will eventually be able to compute sigma n plus 1. So historically, so far, sigma function was known for the values of 1, 2, 3, 4. And if we are successful, and we have no doubt that we will be, we make the next step and present the result for sigma 5. And if you would ask me if I'm confident that eventually the human mind will be able to compute sigma 6, I would say with great caution, yes, given the enormous advances in neural networks. I think it will be possible, although sigma 6 is extremely more complicated already. The search space is even more gigantic, and 6-state Turing machines, binary Turing machines, create much, much more complicated patterns than 5-state Turing machines. But on the other hand, computing power is there. We run, by the way, all on Amazon S3, and because keep in mind each of these 1.6 million Turing machines we have to execute for millions of steps to find these patterns, and so it's a gigantic amount of computing power here. But cautiously, I'm optimistic that over time the human mind will evolve, given the big progress in software technology, that we can compute sigma 5, and there I'm almost 100% sure, and then over time sigma 6, and who knows what the future will then bring. So anyways, to sum up, we have presented a tiny bit of new numerical evidence for the new Gödelian argument that was brought forward by Bringsford, and is based on the assumption that if the human mind can compute sigma n, it will eventually be able to compute sigma n plus 1, which basically resembles what Gödel said in his 1951 Gibbs lecture, that although the human mind at any point in time might have only a finite number of states, there is no reason why this number cannot converge to infinity. So, thank you for your attention.
Probably our time is finished, so you can discuss this session. Now somebody probably has information about